No Human Left Behind, AI. An advanced course to artificial intelligence written by Valentin Vishnyakov, published by Infinia Publishing. Introduction. Welcome, ambitious learners, to the Advanced Course to Artificial Intelligence, the second installment in our comprehensive series, No Human Left Behind, AI. In this course, we will build upon the foundational knowledge established in Course 1, delving deeper into the intricacies of artificial intelligence and exploring its cutting-edge techniques, applications, and implications. Having completed the Introduction to Artificial Intelligence course, you now possess a solid understanding of the core concepts of AI, including search and optimization, knowledge representation and reasoning, machine learning, deep learning, natural language processing, and computer vision. You have also grappled with the ethical and societal dimensions of AI, considering issues such as bias, fairness, transparency, accountability, and the impact of AI on employment, autonomy, and human well-being. In this advanced course, we will venture beyond the fundamentals, immersing ourselves in more specialized and complex topics that represent the forefront of AI research and development. We will explore the fascinating world of generative AI, uncovering the techniques that enable AI to create new content, from realistic images and videos to human-quality text and music. Explainable AI, XAI, peering into the black box of AI decision-making, developing methods for understanding and interpreting complex AI models. Multi-agent systems, investigating how multiple AI agents can interact, coordinate, cooperate, and compete to achieve individual or common goals. Robotics and embodied AI, bridging the gap between intelligent agents and the physical world, creating robots that can perceive, reason, act, and learn in complex environments. AI in specialized domains, examining the transformative applications of AI in fields such as healthcare, finance, autonomous systems, scientific discovery, and education. AI safety and robustness, delving into the critical issues surrounding the development of safe, reliable, and secure AI systems. Emerging trends and future directions, exploring cutting-edge research areas, such as neurosymbolic AI, quantum machine learning, and human-centered AI, and envisioning the future of AI and its impact on society. Throughout this course, we will maintain a strong emphasis on both the technical and ethical aspects of AI. We will not only dissect the algorithms and architectures that power advanced AI systems but also critically examine their implications for individuals, organizations, and society as a whole. We will grapple with questions regarding bias, fairness, transparency, accountability, privacy, security, and the long-term impact of AI on human life. This course is designed to challenge you, to expand your understanding of AI, and to equip you with the knowledge and skills needed to become a leader in this rapidly evolving field. It is intended for those who are passionate about AI, eager to deepen their expertise, and committed to shaping a future where AI is developed and used responsibly, ethically, and for the benefit of all humanity. Prepare to embark on an intellectually stimulating journey, one that will push the boundaries of your knowledge, ignite your imagination, and empower you to contribute to the next generation of intelligent systems. The advanced study of artificial intelligence awaits. Lesson 1, Embarking on the AI Odyssey. Welcome, future architects of intelligent systems, to the Grand Academy of Artificial Intelligence. You are embarking on a profound journey, one that delves into the very essence of intelligence, exploring how we can imbue machines with the ability to learn, reason, and solve problems in ways that were once considered the sole domain of humans. This is the inaugural lesson of an advanced course, designed to elevate your understanding of artificial intelligence, AI, from theoretical concepts to practical mastery. Prepare to challenge your assumptions, expand your knowledge, and develop the skills necessary to shape the future of this transformative technology. The dawn of the intelligent machine. The dream of creating intelligent machines has captivated humanity for centuries, weaving its way through mythology, literature, and scientific inquiry. From the mechanical automatons of ancient Greece to the sentient robots of science fiction, the desire to replicate our own cognitive abilities in artificial form has been a persistent theme. Today, that dream is rapidly becoming a reality, as AI systems begin to permeate every aspect of our lives, transforming industries, reshaping societies, and redefining what's possible. Artificial intelligence, in its essence, is the endeavor to create machines that can perform tasks typically requiring human intelligence. These tasks encompass a wide range of cognitive functions, including learning, problem-solving, decision-making, perception, and natural language understanding. The goal is not merely to mimic human intelligence but to create systems that can surpass human limitations in speed, accuracy, and scalability, unlocking new frontiers of innovation and discovery. The field of AI is not monolithic. It is a vibrant tapestry woven from various subfields, each contributing a unique thread to the overall picture. Machine learning, a dominant force in modern AI, focuses on enabling systems to learn from data without explicit programming. Deep learning, a powerful subset of machine learning, utilizes artificial neural networks with multiple layers to model complex patterns and representations. Consider the implications. This is no longer science fiction. Autonomous vehicles navigate our streets, medical diagnosis systems analyze images with superhuman accuracy, and sophisticated algorithms personalize our online experiences. AI is no longer a futuristic concept, it is a present reality, rapidly evolving and shaping the world around us. As aspiring AI practitioners, you are entering the field at a pivotal moment, poised to contribute to the next chapter of this extraordinary story. It is your duty to learn all you can. Defining the landscape of intelligence. Before we delve into the intricacies of AI algorithms and techniques, it's crucial to establish a common understanding of the fundamental concepts that underpin this field. What do we truly mean by intelligence when applied to machines? How do we differentiate between different types of AI, and what are the key milestones that have shaped the evolution of this discipline? These questions will be the focus of this section. Intelligence, in the context of AI, is often defined as the ability of a system to achieve goals in a wide range of environments. This encompasses the capacity to learn from experience, adapt to new situations, understand and reason with abstract concepts, and interact with the world in a meaningful way. This definition highlights the adaptability and general-purpose nature of intelligence, distinguishing it from specialized skills or programmed responses. Artificial Narrow Intelligence, ANI, also known as weak AI, represents the current state of the field. ANI systems are designed to perform specific tasks, such as playing chess, recognizing faces, or translating languages. While they may excel in their designated domains, they lack the general cognitive abilities of humans. For example, an AI that can beat a grandmaster at chess will not be able to drive a car. Artificial General Intelligence, AGI, or Strong AI, remains a theoretical concept. AGI refers to machines that possess human-level intelligence, capable of performing any intellectual task that a human being can. The development of AGI is a long-term goal of AI research, and its realization would have profound implications for society. There is currently no known AGI system. The journey from the early conceptualizations of AI to the sophisticated systems of today has been marked by significant milestones. The Dartmouth Workshop in 1956, often considered the birth of AI as a formal field, brought together leading researchers to explore the possibility of creating thinking machines. The development of early AI programs, such as the logic theorist and the general problem solver, demonstrated the potential of symbolic reasoning in search algorithms. Navigating the ethical frontier. As AI systems become increasingly integrated into our lives, it is imperative to consider the ethical implications of this technology. The decisions we make today in designing, developing, and deploying AI will have far-reaching consequences for the future. This section will explore some of the key ethical considerations that arise in the field of AI, prompting you to think critically about the societal impact of your work. One of the most pressing concerns is the potential for bias in AI systems. If trained on biased data, AI algorithms can perpetuate and even amplify existing societal prejudices, leading to unfair or discriminatory outcomes. For example, A facial recognition system trained primarily on images of one racial group may perform poorly when applied to individuals from other groups, potentially leading to misidentification and wrongful accusations. Another critical issue is the impact of AI on employment. As automation becomes more sophisticated, there are concerns that AI-powered systems could displace workers in various industries, leading to job losses and economic disruption. It is essential to consider strategies for mitigating these potential negative consequences, such as investing in education and retraining programs to help workers adapt to the changing job market. The question of accountability in AI systems is also paramount. When an AI system makes a mistake, who is responsible? Is it the developers, the users, or the system itself? Establishing clear lines of accountability is crucial for ensuring trust and fairness in the deployment of AI. This becomes particularly important when dealing with sensitive areas like law and medicine. Privacy is another major concern in the age of AI. As AI systems collect and analyze vast amounts of personal data, there is a risk that this information could be misused or compromised, leading to violations of individual privacy. Strong regulations are needed to protect data in this area. Finally, the development of autonomous weapons systems raises profound ethical dilemmas. Should we delegate life-or-death decisions to machines? What are the implications for international security and the future of warfare? These are difficult questions that require careful consideration and international cooperation. The building blocks of intelligent systems. Having explored the broader context of AI, let's now turn our attention to the core components that enable machines to exhibit intelligent behavior. This section will introduce you to the fundamental building blocks of AI systems, providing a conceptual framework for understanding how these systems are designed and how they function. These are concepts you will need to familiarize yourself with. At the heart of many AI systems lies the concept of representation. To reason about the world, an AI system must first be able to represent knowledge in a structured and meaningful way. This can involve using various formalisms, such as logic, semantic networks, or probabilistic models, to capture information about objects, relationships, and concepts. The choice of representation significantly impacts the system's ability to learn and make inferences. Search algorithms are another essential component of many AI systems. These algorithms enable systems to explore a space of possible solutions to find the optimal or most desirable one. From navigating a maze to finding the best move in a game, search algorithms provide a powerful mechanism for problem solving. There are many different algorithms to choose from, all with unique uses. Learning is a cornerstone of modern AI. Machine learning algorithms allow systems to improve their performance on a task based on experience, without being explicitly programmed for that task. This ability to learn from data is what distinguishes many AI systems from traditional software programs. You will study the three types of learning in the future. Planning and decision-making are crucial for enabling AI systems to act effectively in the world. Planning involves formulating a sequence of actions to achieve a specific goal, while decision-making involves selecting the best course of action from a set of alternatives. These capabilities are essential for autonomous agents, such as robots and self-driving cars. They help make AI more autonomous. Finally, the ability to interact with the world through perception and action is fundamental to many AI applications. Perception involves processing sensory input, such as images, sounds, and text, to understand the environment. Action involves taking physical actions in the world, such as moving a robot arm or generating a spoken response. These two work in tandem to create the desired effect. The spectrum of AI techniques. The field of AI encompasses a diverse array of techniques, each with its strengths and limitations. This section will provide an overview of some of the most prominent approaches, highlighting their key characteristics and applications. This will give you a glimpse into the various specializations within AI, allowing you to appreciate the breadth and depth of this rapidly evolving field. Rule-based systems, one of the earliest forms of AI, rely on a set of predefined rules to make decisions or draw conclusions. These systems are typically used in domains where expert knowledge can be explicitly encoded, such as medical diagnosis or legal reasoning. While effective in limited contexts, rule-based systems can become brittle and difficult to maintain as the complexity of the domain increases. Search and optimization algorithms are used to find solutions to problems that can be formulated as a search through a space of possibilities. These techniques are widely used in areas such as game playing, robotics, and logistics. Different search algorithms, such as breadth-first search, depth-first search, and A** search, offer different trade-offs in terms of efficiency and completeness. Machine learning, as previously mentioned, has emerged as a dominant paradigm in AI. It encompasses a wide range of algorithms that enable systems to learn from data, including supervised learning, unsupervised learning, and reinforcement learning. These techniques have proven highly effective in a variety of applications, from image recognition to natural language processing. Deep learning, a subfield of machine learning, has gained immense popularity in recent years due to its ability to learn complex patterns and representations from large datasets. Deep learning models, based on artificial neural networks with multiple layers, have achieved state-of-the-art performance in various domains, including computer vision, speech recognition, and natural language processing. Evolutionary computation draws inspiration from biological evolution to solve optimization and search problems. These techniques use mechanisms such as mutation, crossover, and selection to iteratively improve a population of candidate solutions. Evolutionary computation has been applied to a wide range of problems, including designing aircraft wings, optimizing robot control, and discovering new drugs. Tools and technologies for the AI practitioner building intelligent systems requires a robust set of tools and technologies. This section will introduce you to some of the key software libraries, programming languages, and hardware platforms that are commonly used in AI development. As you progress through this course, you will have the opportunity to gain hands-on experience with these tools, developing practical skills that are highly valued in the industry. Python has emerged as the dominant programming language for AI development, thanks to its extensive libraries, ease of use, and large community support. Libraries such as NumPy, Pandas, and scikit-learn provide powerful tools for numerical computation, data manipulation, and machine learning. Python is useful for many AI tasks. TensorFlow and PyTorch are two of the most popular deep learning frameworks. They provide high-level APIs for building and training neural networks, as well as low-level control over computational graphs. These frameworks also offer automatic differentiation, which simplifies the implementation of gradient-based optimization algorithms. Specialized hardware, such as graphics processing units, GPUs, and tensor processing units, TPUs, has become increasingly important for training large-scale AI models. These devices offer significant speedups compared to traditional CPUs, enabling researchers and practitioners to tackle more complex and computationally demanding tasks. They enable faster processing of AI tasks. Cloud computing platforms, such as Amazon Web Services, AWS, Google Cloud Platform, GCP, and Microsoft Azure, provide access to scalable computing resources, storage, and pre-trained AI models. These platforms enable developers to deploy and scale AI applications without the need for significant upfront investment in hardware infrastructure. They allow for more accessible AI tools. Version control systems, such as Git, are essential for managing code in any software development project, including AI. These systems allow developers to track changes, collaborate with others, and revert to previous versions if necessary. Git is a crucial tool for software development. Real-world applications of artificial intelligence. The impact of AI is already being felt across a wide range of industries and domains. This section will showcase some of the most compelling real-world applications of AI, demonstrating the transformative power of this technology and providing inspiration for your future projects. These examples will illustrate how AI is not just a theoretical concept but a practical tool that is solving real problems and creating new opportunities. In healthcare, AI is being used to develop new diagnostic tools, personalize treatment plans, and accelerate drug discovery. AI-powered systems can analyze medical images to detect diseases such as cancer with accuracy comparable to or exceeding that of human experts. AI can improve patient care significantly. In finance, AI is used for fraud detection, risk assessment, algorithmic trading, and customer service. Machine learning algorithms can analyze vast amounts of financial data to identify patterns and anomalies that may indicate fraudulent activity, helping to protect both institutions and individuals. AI has many uses in the finance industry. In transportation, AI is driving the development of self-driving cars, optimizing logistics and supply chains, and improving traffic flow in cities. Autonomous vehicles have the potential to revolutionize transportation, making it safer, more efficient, and more accessible. AI plays a role in all aspects of transportation. In retail, AI is used to personalize recommendations, optimize pricing, and manage inventory. By analyzing customer data, AI systems can predict demand, tailor promotions, and improve the overall shopping experience. AI can create more accurate inventories for retail. In entertainment, AI is used to create realistic computer-generated imagery, CGI, compose music, and generate scripts. AI-powered tools are also being used to personalize content recommendations and enhance user engagement on streaming platforms. AI can create new forms of entertainment. Challenges and future directions in AI. While AI has made remarkable progress, significant challenges remain. This section will explore some of the key obstacles that researchers and practitioners are currently grappling with, as well as exciting future directions that are likely to shape the field in the coming years. Understanding these challenges and opportunities will provide you with a more nuanced perspective on the current state of AI and its potential trajectory. One of the major challenges is the need for more robust and reliable AI systems. Many current AI models are brittle and can be easily fooled by adversarial examples, which are inputs that have been deliberately crafted to cause the model to make a mistake. Developing techniques to make AI systems more resilient to such attacks is an active area of research. AI models must be made more reliable. Another challenge is the black box nature of many AI systems, particularly deep learning models. It can be difficult to understand why a model made a particular decision, which can be problematic in applications where transparency and explainability are important, such as healthcare and law. Research into explainable AI, XAI, aims to address this challenge. The development of artificial general intelligence, AGI, remains a major long-term goal of the field. While there is ongoing debate about the feasibility and timeline for achieving AGI, it is clear that such a development would have profound implications for society. This would have a major impact on society. The intersection of AI with other emerging technologies, such as quantum computing and biotechnology, holds immense promise. Quantum computing could potentially accelerate the training of AI models and enable the solution of problems that are currently intractable for classical computers. Biotechnology could provide new insights into the nature of intelligence and inspire the design of novel AI architectures. These emerging tech fields could greatly impact AI. Finally, addressing the ethical and societal implications of AI is of paramount importance. As AI systems become more powerful and pervasive, it is crucial to ensure that they are developed and deployed responsibly, with careful consideration of their impact on individuals, communities, and society as a whole. This requires ongoing dialogue and collaboration between researchers, policymakers, and the public. We must always consider ethics in AI. Your role in the AI revolution. As you embark on this journey to master artificial intelligence, it is important to reflect on the role you will play in shaping the future of this transformative technology. This section serves as a call to action, encouraging you to embrace the challenges and opportunities that lie ahead, and to approach your studies with a sense of purpose and responsibility. The field of AI is rapidly evolving, and there is a growing demand for skilled professionals who can design, develop, and deploy intelligent systems. By dedicating yourself to mastering the concepts and techniques presented in this course, you are positioning yourself to become a leader in this exciting field. You will have many opportunities in the AI field. Your journey will not be without its challenges. AI is a complex and multifaceted discipline, and it will require dedication, perseverance, and a willingness to embrace continuous learning. Be prepared to grapple with difficult concepts, to experiment with new tools and technologies, and to push the boundaries of your understanding. You will need to be persistent in your studies. Remember that AI is not just about algorithms and code, it is about solving real-world problems and making a positive impact on society. As you develop your skills, consider how you can use your knowledge to address pressing challenges in areas such as healthcare, education, environmental sustainability, and social justice. AI can be used for social good. Collaboration is key in the field of AI. Seek out opportunities to work with others, to share your knowledge, and to learn from different perspectives. Engage in discussions, participate in hackathons, and contribute to open-source projects. The AI community is vibrant and welcoming, and you will find many opportunities to connect with like-minded individuals. Collaboration is encouraged in the AI community. Finally, approach your studies with a sense of ethical responsibility. The decisions you make as an AI practitioner will have consequences, both intended and unintended. Strive to develop AI systems that are fair, transparent, and accountable, and that promote human well-being. The future of AI is in your hands, and it is up to you to shape it for the better. You are the future of AI. Lesson 2, Deconstructing the Evolution of AI, a deep dive into paradigms and breakthroughs. Welcome back, esteemed scholars of artificial intelligence, to the second lesson of our advanced exploration into the intricacies of this transformative field. Having established a foundational understanding of AI's core concepts and ethical considerations in our previous discourse, we shall now embark on a more nuanced journey through the annals of AI's history. Prepare to dissect the major paradigms that have shaped the field, analyze the pivotal breakthroughs that have propelled it forward, and critically examine the limitations and challenges that have punctuated its evolution. This deep dive will equip you with a sophisticated perspective, enabling you to appreciate the intricate tapestry of progress that defines modern AI. Beyond the Dartmouth Workshop, unpacking the early years of AI research. While the Dartmouth Workshop of 1956 is rightfully celebrated as the genesis of AI as a formal discipline, the ensuing years witnessed a complex interplay of competing ideas, ambitious projects, and sobering realizations. This section will move beyond the initial euphoria, dissecting the key research programs that emerged in the early years, and analyzing their contributions and shortcomings. This period was marked by both rapid advancements and significant challenges, setting the stage for the future evolution of the field. The Logic Theorist, developed by Alan Newell and Herbert Simon, was a groundbreaking program that demonstrated the potential of symbolic reasoning. It could prove theorems in propositional logic, showcasing the ability of computers to perform tasks previously considered the exclusive domain of human intellect. This program provided early evidence that machines could be capable of logical reasoning. The General Problem Solver, GPS, also developed by Newell and Simon, aimed to create a universal problem-solving machine. While GPS ultimately fell short of this ambitious goal, it introduced important concepts such as means-ends analysis, a problem-solving technique that involves identifying the differences between the current state and the goal state and selecting actions to reduce those differences. GPS introduced valuable concepts. Early work on machine translation, fueled by the Cold War's demand for automated translation of Russian documents, demonstrated the challenges of natural language processing. Initial approaches, based on simple word-for-word substitution, proved inadequate for capturing the nuances of human language. This exposed the complexities of language. The development of the first expert systems, such as Dendrol for identifying chemical structures and Mycin for diagnosing bacterial infections, showcased the potential of AI in specialized domains. These systems, based on encoding expert knowledge into a set of rules, demonstrated the practical value of AI in solving real-world problems. They were very effective for specific tasks. However, these early successes were often followed by periods of disillusionment. Progress was slower than initially anticipated, and many early AI systems proved to be brittle and unable to generalize beyond their narrow domains. The limitations of these early approaches became increasingly apparent, leading to a reassessment of the field's direction. There were many obstacles to overcome. The rise and fall of expert systems, a cautionary tale. The 1980s witnessed the commercialization of AI, driven largely by the rise of expert systems. These systems, designed to emulate the decision-making abilities of human experts, promised to revolutionize various industries. This section will examine the factors that contributed to the initial success of expert systems, analyze the reasons for their eventual decline, and extract valuable lessons about the challenges of translating AI research into practical applications. It is important to learn from the past. The appeal of expert systems lay in their ability to capture and codify the specialized knowledge of human experts. This knowledge, often acquired through years of experience, could be made accessible to a wider audience through these systems, potentially improving efficiency and consistency in decision-making. Companies saw great value in this. Expert systems found applications in diverse fields, including medical diagnosis, financial analysis, and manufacturing. They were used to diagnose diseases, assess loan applications, and control industrial processes. Their ability to provide explanations for their reasoning, based on the rules they applied, contributed to their acceptance in some domains. They had many practical uses. However, the development and maintenance of expert systems proved to be a significant challenge. The process of knowledge acquisition, extracting and encoding expert knowledge, was often slow, expensive, and prone to errors. Experts often found it difficult to articulate their knowledge in a precise and complete manner. The process was very labor-intensive. Furthermore, expert systems were often brittle and unable to adapt to changing circumstances. They lacked common sense reasoning and struggled with situations that fell outside their predefined rules. Their inability to learn from new data also limited their long-term effectiveness. They struggled with novel situations. By the late 1980s and early 1990s, the limitations of expert systems had become apparent. The initial hype gave way to disillusionment as many projects failed to deliver on their promises. The AI winter that followed saw a decline in funding and interest in AI research, particularly in expert systems. This was a difficult period for AI. The connectionist reawakening, neural networks make a comeback while expert systems dominated the AI landscape in the 1980s. A different approach, inspired by the structure of the human brain, was gradually gaining momentum. This section will explore the resurgence of connectionism and the rise of neural networks, analyzing the key developments that propelled this paradigm shift and transformed the field of AI. Connectionism provided a new path forward. Connectionism, with its emphasis on distributed representations and parallel processing, offered a stark contrast to the symbolic approach of expert systems. Neural networks, the computational embodiment of connectionist principles, promised to learn from data, adapt to new situations, and generalize to unseen examples. They offered a more flexible approach. The development of the backpropagation algorithm in the mid-1980s was a pivotal moment for neural networks. This algorithm provided an efficient way to train multi-layered networks, overcoming a major limitation of earlier models like the perceptron. Backpropagation enabled networks to learn complex patterns and relationships from data. This was a major breakthrough. However, the computational resources required to train large neural networks were not widely available at the time. It would take further advances in hardware, particularly the development of powerful GPUs, to fully unlock the potential of deep learning, a subfield of machine learning focused on deep neural networks. Hardware limitations were a bottleneck. Despite these challenges, research on neural networks continued, driven by a dedicated community of researchers who recognized their potential. This persistence laid the groundwork for the deep learning revolution that would transform the field in the 21st century. Their work paved the way for future success. The re-emergence of neural networks also highlighted the cyclical nature of AI research. Ideas that were once marginalized or dismissed can be revitalized with new algorithms, increased computational power, and the availability of larger datasets. This underscores the importance of maintaining a diverse range of research approaches within the field. It is important to explore different ideas. The data deluge and the triumph of machine learning. The dawn of the 21st century witnessed an unprecedented explosion in the amount of data being generated and collected. This section will examine the impact of this data deluge on the field of AI, exploring how it fueled the rise of machine learning, particularly deep learning, as the dominant paradigm. We will also analyze the challenges and opportunities presented by this new era of data-driven AI. Data has become the lifeblood of AI. The proliferation of the Internet, the rise of social media, and the increasing digitization of our lives created a vast ocean of data. This data, encompassing text, images, videos, and sensor readings, provided a rich training ground for machine learning algorithms. The more data, the better the algorithms perform. Machine learning, with its ability to automatically learn patterns and relationships from data, was ideally suited to harness the power of big data. Deep learning, in particular, demonstrated a remarkable ability to improve its performance as the amount of training data increased. This scalability made it a powerful tool for a wide range of applications. Deep learning thrives on data. The availability of large datasets, coupled with advances in computing power and algorithmic improvements, led to breakthroughs in various domains. Deep learning models achieved superhuman performance in image recognition, natural language processing, and game playing, surpassing previous benchmarks and capturing the public's imagination. These breakthroughs garnered significant attention. However, the reliance on massive datasets also raises concerns about data privacy, security, and bias. Ensuring that AI systems are trained on representative and unbiased data is crucial for developing fair and equitable applications. These concerns must be addressed proactively. Addressing these issues is essential. The age of big data and machine learning has transformed the landscape of AI, shifting the focus from handcrafted rules to data-driven models. This paradigm shift has opened up new possibilities for AI applications, but it also requires a new set of skills and a deeper understanding of the ethical implications of data-driven decision-making. This requires a new skill set. The deep learning revolution, architectures, applications, and limitations. Deep learning, a subfield of machine learning based on artificial neural networks with multiple layers, has emerged as a dominant force in contemporary AI. This section will delve deeper into the intricacies of deep learning, examining the various architectures, exploring the breadth of its applications, and critically analyzing its limitations and challenges. This will provide a comprehensive understanding of this powerful yet complex technology. Deep learning is powerful but complex. Convolutional neural networks, CNNs, have revolutionized computer vision. Their ability to automatically learn hierarchical features from images has led to breakthroughs in image classification, object detection, and image segmentation. CNNs are inspired by the structure of the visual cortex and have proven highly effective in processing visual data. They are a cornerstone of computer vision. Recurrent neural networks, RNNs, particularly long short-term memory, LSTM, networks, are designed to process sequential data, such as text and time series. They have achieved remarkable results in natural language processing tasks, including machine translation, text generation, and sentiment analysis. RNNs excel at understanding sequences. Generative adversarial networks, GANs, represent a novel approach to generative modeling. GANs consist of two networks, a generator and a discriminator, that are trained in an adversarial manner. The generator learns to create realistic data samples, while the discriminator tries to distinguish between real and generated samples. GANs have shown impressive results in generating images, videos, and text. They can create new content. Despite their successes, deep learning models have limitations. They often require vast amounts of labeled data, which can be expensive and time-consuming to acquire. They can also be computationally expensive to train, requiring specialized hardware such as GPUs. Furthermore, their black box nature makes it difficult to understand their decision-making processes, raising concerns about transparency and accountability. They can be difficult to interpret. Active research areas in deep learning include developing more data-efficient learning algorithms, improving the interpretability of deep models, and exploring new architectures and training techniques. Addressing these challenges is crucial for realizing the full potential of deep learning and ensuring its responsible deployment. There is ongoing research to improve them. Probabilistic graphical models, a complementary approach. While deep learning has captured much of the limelight, probabilistic graphical models, PGMs, offer a complementary approach to representing and reasoning with uncertainty. This section will explore the principles of PGMs, highlighting their strengths in handling structured data, incorporating prior knowledge, and providing interpretable models. Understanding PGMs will broaden your perspective on the diverse landscape of AI techniques. They offer a different perspective. PGMs provide a framework for representing complex probability distributions using graphs. Nodes in the graph represent random variables, while edges represent probabilistic dependencies between these variables. This graphical representation allows for efficient inference and learning algorithms. They visually represent relationships. Bayesian networks and Markov random fields are two major classes of PGMs. Bayesian networks use directed graphs to represent causal relationships between variables, while Markov random fields use undirected graphs to represent more general dependencies. Both are used to model relationships. PGMs offer several advantages. They can naturally incorporate prior knowledge into the model, which can be particularly useful when data is scarce. They also provide a degree of interpretability, as the graph structure reveals the relationships between variables. Furthermore, they can handle missing data and reason under uncertainty in a principled manner. They are good at handling uncertainty. However, inference and learning in PGMs can be computationally challenging, especially for complex models with many variables. Approximation techniques, such as variational inference and Markov chain Monte Carlo, MCMC, are often used to address these computational challenges. These techniques make them more practical. There are methods to make them efficient. PGMs have found applications in various domains, including bioinformatics, computer vision, and natural language processing. They are particularly useful when dealing with structured data, such as gene regulatory networks or social networks, and when interpretability and uncertainty quantification are important. They are useful for structured data. Reinforcement learning, learning through interaction. Reinforcement learning, RL, is a powerful paradigm for training agents to make decisions in an environment through trial and error. This section will explore the core concepts of RL, including agents, environments, rewards, and policies. We will also examine key algorithms, such as Q-learning and SURSA, and discuss the challenges and opportunities in this rapidly evolving area of AI. This will introduce a dynamic learning approach. In RL, an agent interacts with an environment by taking actions and receiving rewards. The agent's goal is to learn a policy, a mapping from states to actions, that maximizes its cumulative reward over time. This learning process is driven by the feedback received from the environment in the form of rewards. The agent learns to maximize rewards. Key concepts in RL include states, actions, rewards, and policies. The state represents the current situation of the agent in the environment. Actions are the choices available to the agent at each state. Rewards are scalar feedback signals that indicate the desirability of an action. The policy is the agent's strategy for selecting actions. The policy is key to learning. Q-learning and SURSA are two fundamental algorithms in RL. Q-learning is an off-policy algorithm that learns an action value function, Q, S, A, which estimates the expected cumulative reward for taking action. A in state S. SIRSA is an on-policy algorithm that learns the value of following the current policy. Both algorithms learn from experience. RL has achieved remarkable success in game playing, robotics, and control systems. AlphaGo, an RL-based program, defeated a world champion Go player, demonstrating the potential of RL to master complex strategic tasks. RL is also being used to develop autonomous robots that can navigate and interact with the real world. It has shown great potential. However, RL also faces significant challenges. These include the need for a large number of interactions with the environment, the difficulty of designing appropriate reward functions, and the problem of exploration versus exploitation. Addressing these challenges is an active area of research in the RL community. Researchers are actively working on these issues. The frontier of AI, emerging trends and future directions. The field of AI is in a constant state of flux, with new ideas, techniques, and applications emerging at a rapid pace. This section will explore some of the most exciting and promising trends that are shaping the future of AI, providing a glimpse into the cutting-edge research that is pushing the boundaries of what's possible. This will give you a forward-looking perspective on the field. This will prepare you for the future. Explainable AI, XAI, is a growing area of research that aims to make AI systems more transparent and understandable. As AI systems are increasingly used in high-stakes domains such as healthcare and finance, it is crucial to be able to explain their decisions and build trust in their outputs. XAI techniques aim to provide insights into the inner workings of complex models. This makes AI more trustworthy. Federated learning is a novel approach to training AI models that addresses privacy concerns by allowing multiple parties to collaboratively train a model without sharing their raw data. This technique has the potential to unlock the value of data that is currently siloed due to privacy regulations or competitive concerns. It enables collaborative learning while preserving privacy. It protects sensitive data. Neurosymbolic AI seeks to bridge the gap between symbolic reasoning and neural networks. This approach aims to combine the strengths of both paradigms, leveraging the ability of neural networks to learn from data and the ability of symbolic systems to perform logical reasoning and provide explanations. It combines the best of both worlds. It creates a powerful hybrid approach. Quantum machine learning explores the intersection of quantum computing and artificial intelligence. Quantum computers, which leverage the principles of quantum mechanics, have the potential to solve certain computational problems that are intractable for classical computers. This could lead to significant speedups in training and inference for certain types of AI models. This is a very new area of research. The development of artificial general intelligence, AGI, machines with human-level or even superhuman intelligence, remains a long-term goal for some researchers. While the feasibility and timeline for AGI are subject to debate, its potential impact on society is undeniable. It is important to consider the ethical and societal implications of AGI. It could change everything. The ethical and societal dimensions of advanced AI's AI systems become increasingly sophisticated and integrated into our lives. It is imperative to engage in a thoughtful and ongoing discussion about their ethical and societal implications. This section will delve deeper into the complex ethical challenges posed by advanced AI, encouraging you to think critically about the potential consequences of this technology and your role in shaping its future. This is a crucial aspect of AI development. The potential for AI to exacerbate existing inequalities is a major concern. If AI systems are trained on biased data or deployed in a way that favors certain groups over others, they can perpetuate and even amplify societal biases. This could have far-reaching consequences in areas such as hiring, lending, and criminal justice. We must ensure fairness in AI. The impact of AI on the future of work is another critical issue. While AI has the potential to create new jobs and increase productivity, it also poses a threat to workers in certain industries. It is important to consider strategies for mitigating the negative impacts of automation, such as investing in education and retraining programs. We must prepare for changes in the job market. The workforce must be prepared for these changes. The development of autonomous weapons systems raises profound ethical questions about the nature of warfare and the role of humans in decision-making. Should machines be allowed to make life-or-death decisions without human intervention? What are the implications for international security and the potential for unintended escalation? These questions need careful consideration. The increasing use of AI for surveillance and social control raises concerns about privacy and civil liberties. Facial recognition technology, for example, can be used to track individuals' movements and activities without their knowledge or consent. It is crucial to establish safeguards to prevent the misuse of these technologies and protect fundamental rights. We must protect individual freedoms. These technologies must be used responsibly. Ultimately, the future of AI will be shaped by the choices we make today. As researchers, developers, and citizens, we have a responsibility to engage in a thoughtful and informed dialogue about the ethical and societal implications of AI. By working together, we can harness the transformative power of AI for the benefit of all humanity. We must all contribute to this discussion. We must work together to ensure a positive future. Lesson 3: Mastering Machine Learning, Algorithms, Techniques, and Applications. Welcome back, astute learners, to the third lesson of our advanced expedition into the realm of artificial intelligence. Having charted the historical evolution and ethical dimensions of AI in our previous sessions, we now turn our attention to a core pillar of modern AI, machine learning. In this lesson, we will dissect the fundamental concepts of machine learning, explore a diverse array of algorithms and techniques, and examine the transformative applications of this powerful technology across various domains. Prepare to deepen your understanding of how machines learn from data, enabling them to make predictions, automate decisions, and unlock new frontiers of innovation. The essence of machine learning, learning from data at its core. Machine learning is about enabling computers to learn from data without being explicitly programmed. This section will delve into the fundamental principles of machine learning, exploring the different types of learning, the key components of a machine learning system, and the overarching goals of this transformative field. By grasping these foundational concepts, you will be well equipped to navigate the intricacies of various machine learning algorithms and techniques. This is a new way of thinking. Traditional programming relies on explicitly defining rules and instructions for a computer to follow. In contrast, machine learning algorithms learn patterns and relationships from data, allowing them to make predictions or decisions on new, unseen data. This ability to generalize from experience is a hallmark of intelligent behavior. It is a fundamental shift in programming. Supervised learning, unsupervised learning, and reinforcement learning are the three main paradigms of machine learning. In supervised learning, the algorithm is trained on labeled data, where each input is paired with a corresponding output. In unsupervised learning, the algorithm is trained on unlabeled data and must discover patterns and structures on its own. Reinforcement learning involves an agent learning to interact with an environment through trial and error, guided by rewards. Each approach has different strengths. A typical machine learning system consists of several key components: data, a model, a learning algorithm, and an evaluation metric. The data provides the raw material for learning. The model represents the learned patterns or relationships. The learning algorithm adjusts the model based on the data. The evaluation metric measures the performance of the model on unseen data. Each component plays a vital role. The overarching goal of machine learning is to build models that can generalize well to new, unseen data. This means that the model should not simply memorize the training data but should capture the underlying patterns and relationships that enable it to make accurate predictions on data it has never encountered before. Generalization is key to the success of machine learning. Generalization is a difficult but vital task. Delving into supervised learning, regression and classification. Supervised learning is a powerful paradigm for training models to predict an output variable based on one or more input variables. This section will explore two fundamental supervised learning tasks, regression and classification. We will examine key algorithms, such as linear regression, logistic regression, and support vector machines, and discuss their strengths, limitations, and applications. This will give you practical tools. Regression involves predicting a continuous output variable. For example, predicting the price of a house based on its size, location, and other features is a regression problem. Linear regression is a simple yet widely used algorithm that models the relationship between the input and output variables using a linear equation. It is often the first algorithm learned. Classification involves predicting a categorical output variable. For example, classifying an email as spam or not spam is a classification problem. Logistic regression, despite its name, is a classification algorithm that models the probability of an input belonging to a particular class. It is a powerful classification tool. Support vector machines, SVMs, are another powerful class of supervised learning algorithms. SVMs aim to find the optimal hyperplane that separates different classes in the input space, maximizing the margin between the classes. They can be used for both regression and classification tasks and are particularly effective in high-dimensional spaces. They are versatile and effective. Decision trees are a nonparametric supervised learning method used for both classification and regression. They learn a hierarchy of if/else questions, leading to a decision. They are easy to understand and interpret, making them a popular choice for many applications. Their transparency is a key advantage. These algorithms are used in a wide range of applications, including medical diagnosis, financial modeling, and natural language processing. Understanding their principles and limitations is crucial for effectively applying them to real-world problems. They have numerous practical uses. Unveiling patterns with unsupervised learning, clustering and dimensionality reduction. Unlike supervised learning, unsupervised learning deals with unlabeled data, where the goal is to discover hidden patterns, structures, and relationships within the data. This section will explore two major categories of unsupervised learning, clustering and dimensionality reduction. We will examine popular algorithms such as k-means clustering, hierarchical clustering, principal component analysis, PCA, and t-distributed stochastic neighbor embedding, TSNE, uncovering their inner workings and practical applications. This teaches how to find structure in data. Clustering aims to group similar data points together based on their inherent characteristics. K-means clustering is a widely used algorithm that partitions data into k-clusters, where each data point belongs to the cluster with the nearest mean. Hierarchical clustering, on the other hand, builds a hierarchy of clusters either in a bottom-up, agglomerative, or top-down, divisive, manner. It is an intuitive approach to grouping data. Dimensionality reduction techniques aim to reduce the number of variables in a dataset while preserving essential information. Principal component analysis, PCA, is a linear technique that finds a new set of orthogonal variables, called principal components, that capture the maximum variance in the data. It is often used for visualization and as a pre-processing step for other machine learning algorithms. PCA is a fundamental technique. T-distributed stochastic neighbor embedding, TSNE, is a nonlinear dimensionality reduction technique that is particularly well suited for visualizing high-dimensional data in a low-dimensional space, such as 2D or 3D. It aims to preserve local neighborhood structures in the data, making it useful for exploring clusters and patterns in complex datasets. TSNE is great for visualization. These unsupervised learning techniques find applications in various domains. Customer segmentation, anomaly detection, image compression, and topic modeling are just a few examples where clustering and dimensionality reduction play a crucial role. They can reveal hidden insights in data. Unsupervised learning presents unique challenges. Evaluating the quality of clusters or reduced dimension representations can be subjective, as there are no ground truth labels to compare against. Choosing the right algorithm and parameters often requires domain expertise and experimentation. It requires careful consideration, The dynamics of reinforcement learning, agents, rewards, and policies. Reinforcement learning, RL, offers a powerful framework for training agents to make sequential decisions in an environment through trial and error. This section will delve deeper into the core concepts of RL, exploring the interplay between agents, environments, rewards, and policies. We will also examine advanced RL algorithms, such as deep Q networks, DQN, and policy gradients, and discuss their applications in areas such as robotics, game playing, and control systems. This will provide a more in-depth understanding of this dynamic learning paradigm. RL is a powerful tool. The agent-environment interaction is central to RL. The agent takes actions in an environment, receives feedback in the form of rewards, and learns to adjust its policy to maximize cumulative rewards over time. This iterative process of trial and error allows the agent to learn optimal or near-optimal strategies for interacting with the environment. The agent learns through experience. The concept of a Markov decision process, MDP, provides a formal mathematical framework for modeling RL problems. An MDP is defined by a set of states, a set of actions, a transition function that specifies the probability of moving from one state to another given an action, and a reward function that assigns a reward to each state-action pair. MDPs provide a solid foundation for RL. They are a key concept to learn. Deep Q networks, DQN, combine Q-learning with deep neural networks to approximate the action value function. DQN achieved a breakthrough by demonstrating superhuman performance in playing Atari games, showcasing the power of combining deep learning with reinforcement learning. DQN has significantly advanced the field. It showed the power of deep RL. Policy gradient methods offer another approach to RL, where the policy is directly parameterized and optimized using gradient ascent. These methods can handle continuous action spaces and have shown promise in complex control tasks. They provide a different way to learn policies. Policy gradients are useful for continuous actions. RL has found applications in diverse domains, including robotics, where it can be used to train robots to perform complex tasks such as grasping and manipulation, game playing, where it has achieved superhuman performance in games like Go and chess, and control systems, where it can be used to optimize the performance of industrial processes. It has many practical applications. RL has great potential in many fields. The power of ensemble methods. Combining models for improved performance. Ensemble methods combine multiple individual models to create a more powerful and robust predictive system. This section will explore the principles of ensemble learning, examining popular techniques such as bagging, boosting, and stacking. We will analyze how these methods can improve model accuracy, reduce variance, and enhance generalization ability. This will introduce you to a powerful approach for enhancing model performance. Ensemble methods leverage diversity. The core idea behind ensemble methods is that by combining the predictions of multiple models, we can often achieve better performance than any single model could achieve on its own. This is analogous to seeking multiple opinions before making an important decision. Diversity among the models is key to the success of ensemble methods. Combining models reduces errors. Bagging, bootstrap aggregating, involves training multiple models on different subsets of the training data, sampled with replacement. The predictions of these models are then combined, typically through averaging for regression or voting for classification. Random forest is a popular example of a bagging-based algorithm that uses an ensemble of decision trees. Bagging reduces variance. Boosting, on the other hand, trains models sequentially, where each new model focuses on correcting the errors made by the previous models. Eta boost and gradient boosting are two widely used boosting algorithms. Boosting algorithms are known for their high accuracy but can be prone to overfitting if not carefully tuned. Boosting improves accuracy. Stacking takes ensemble learning to another level by training a metalearner to combine the predictions of the base learners. This metalearner is trained on the outputs of the base learners, allowing it to learn how to best combine their predictions. Stacking can be very powerful. Ensemble methods have proven highly effective in various applications, including winning machine learning competitions. They are often used when high accuracy is paramount and computational resources are not a major constraint. They are a valuable tool in the machine learning practitioner's toolkit. Ensemble methods are often used in competitions. Deep dive into deep learning architectures, CNNs, RNNs, and transformers. Deep learning, with its multi-layered neural networks, has revolutionized many areas of AI. This section will provide a deeper exploration of specific deep learning architectures, including convolutional neural networks, CNNs, recurrent neural networks, RNNs, and the more recent transformer networks. We will analyze their unique structures, strengths, and limitations, and examine their applications in computer vision, natural language processing, and other domains. This will provide a more specialized understanding. CNNs are particularly well suited for processing grid-like data, such as images. Their architecture incorporates convolutional layers that learn spatial hierarchies of features, pooling layers that reduce dimensionality, and fully connected layers that perform classification or regression. CNNs have achieved remarkable success in various computer vision tasks. They are essential for image data. RNNs are designed to handle sequential data, such as text or time series. They maintain a hidden state that is updated at each time step, allowing them to capture dependencies between elements in the sequence. LSTMs and GRUs are variants of RNNs that address the vanishing gradient problem, enabling them to learn long-range dependencies. RNNs are crucial for sequential data. Transformers, introduced in the paper "Attention is All You Need," have emerged as a powerful alternative to RNNs for sequence-to-sequence tasks. They rely on a mechanism called self-attention, which allows the model to weigh the importance of different parts of the input sequence when making predictions. Transformers have achieved state-of-the-art results in machine translation and other NLP tasks. They have transformed NLP. Each of these architectures has its strengths and weaknesses. CNNs excel at spatial data but may not be ideal for sequential data. RNNs are well suited for sequences but can be difficult to train and may struggle with very long sequences. Transformers are powerful but can be computationally expensive. Choosing the right architecture is crucial. The field of deep learning is constantly evolving, with new architectures and techniques being developed at a rapid pace. Staying abreast of these developments is essential for anyone working in this dynamic area of AI. It is a rapidly changing field. Deep learning is constantly advancing. Evaluating and tuning machine learning models, best practices and techniques. Building a machine learning model is an iterative process that involves not only training the model but also carefully evaluating its performance and tuning its parameters to optimize its effectiveness. This section will explore best practices for evaluating and tuning machine learning models, covering topics such as cross-validation, hyperparameter optimization, and common evaluation metrics. This will equip you with the skills to build robust and reliable models. This ensures model quality. Cross-validation is a crucial technique for assessing the generalization ability of a model. It involves partitioning the data into multiple folds, training the model on a subset of the folds, and evaluating it on the remaining fold. This process is repeated multiple times, and the results are averaged to provide a more reliable estimate of the model's performance on unseen data. Cross-validation is essential for reliable evaluation. Hyperparameter tuning involves selecting the optimal values for the parameters that control the learning process itself, such as the learning rate in gradient descent or the number of trees in a random forest. Techniques such as grid search and random search can be used to automate this process. Proper hyperparameter tuning can significantly improve model performance. It can make a big difference. Choosing appropriate evaluation metrics is essential for assessing the performance of a machine learning model. Accuracy, precision, recall, F1, score, and area under the ROC curve, AUC, are common metrics for classification tasks. Mean squared error, MSE, root mean squared error, RMSE, and mean absolute error, MAE, are common metrics for regression tasks. The choice of metric depends on the task. Regularization techniques, such as L1 and L2 regularization, can help prevent overfitting by adding a penalty term to the loss function that discourages large weights. These techniques can improve the generalization ability of the model, particularly when the amount of training data is limited. Regularization helps prevent overfitting. Model selection involves choosing the best model from a set of candidate models. This can be done by comparing the performance of different models on a validation set or using cross-validation. It is important to choose a model that is both accurate and interpretable, depending on the specific application. Choosing the right model is crucial. The ethical considerations of machine learning, bias, fairness, and transparency as machine learning systems are increasingly deployed in real-world applications. It is crucial to consider the ethical implications of these technologies. This section will delve into the critical issues of bias, fairness, and transparency in machine learning, exploring how these factors can impact individuals and society and discussing strategies for mitigating potential harms. This will encourage you to think critically about the societal impact of your work. Ethical considerations are paramount. Machine learning models can inherit and amplify biases present in the data they are trained on. For example, a facial recognition system trained primarily on images of one racial group may perform poorly on individuals from other groups, potentially leading to discriminatory outcomes. It is essential to carefully examine training data for potential biases. Bias can lead to unfair outcomes. Fairness in machine learning is a complex and multifaceted concept. Different definitions of fairness may conflict with each other, and it is important to consider the specific context and potential impacts on different groups when evaluating the fairness of a model. There is no single definition of fairness. It is a complex issue. Transparency and interpretability are also crucial, particularly in high-stakes applications such as healthcare and criminal justice. Understanding why a model made a particular decision can help build trust, identify potential errors, and ensure accountability. Explainable AI, XAI, is an active area of research that aims to address this challenge. Transparency builds trust. It is important to understand model decisions. Addressing these ethical challenges requires a multifaceted approach. This includes developing techniques for detecting and mitigating bias in data and models, establishing guidelines for fair and transparent AI systems, and fostering a broader societal dialogue about the responsible development and deployment of AI. It requires a collective effort. We all have a role to play. Regulations and standards are also beginning to emerge to address the ethical concerns surrounding AI. The European Union's General Data Protection Regulation, GDPR, for example, includes provisions related to automated decision-making and profiling. Staying informed about these developments is essential for anyone working in the field of AI. Regulations are evolving. We must stay informed. Cutting-edge research and future directions in machine learning. The field of machine learning is constantly evolving, with researchers pushing the boundaries of what's possible and exploring new frontiers of innovation. This section will highlight some of the most exciting and promising areas of current research, providing a glimpse into the future directions of machine learning. This will give you a forward-looking perspective, inspiring you to contribute to the next generation of intelligent systems. The field is constantly advancing. One active area of research is unsupervised representation learning, which aims to learn meaningful representations from unlabeled data. This is particularly important in domains where labeled data is scarce or expensive to obtain. Techniques such as autoencoders and generative adversarial networks, GANs, are being used to learn rich and informative representations that can be used for downstream tasks. This can unlock the value of unlabeled data. Transfer learning, where knowledge gained from one task is applied to a different but related task, is another area of growing interest. Transfer learning can significantly reduce the amount of data required to train a model on a new task, making it particularly useful in domains where data is limited. It leverages knowledge gained from other tasks. It is efficient and practical. Meta-learning, or learning to learn, aims to develop algorithms that can learn how to learn more effectively. This could involve learning optimal learning rates, network architectures, or even entire learning algorithms. Meta-learning has the potential to significantly accelerate the development of new AI systems. It could revolutionize how we train models. Explainable AI, XAI, as previously discussed, is another crucial area of research, aiming to make machine learning models more transparent and understandable. This is particularly important in applications where trust and accountability are paramount, such as healthcare and finance. XAI seeks to open the black box of AI. The intersection of machine learning with other fields, such as neuroscience and cognitive science, is also a promising area of research. By drawing inspiration from the human brain, researchers are developing new architectures and learning algorithms that could lead to more powerful and general-purpose AI systems. This interdisciplinary approach holds great potential. It bridges the gap between AI and the human mind. Finally, the development of more robust and reliable machine learning systems is a key challenge. This includes addressing issues such as adversarial examples, which are inputs that have been deliberately crafted to fool a model, and ensuring that models are robust to noise and uncertainty in the data. Building trustworthy AI is crucial. It is essential for real-world deployment. These are just a few of the many exciting research directions in machine learning. As you continue your journey in AI, you will have the opportunity to contribute to these and other advancements, shaping the future of this rapidly evolving field. The possibilities are vast. The future of machine learning is bright. Lesson 4: Unlocking the power of deep learning, architectures, applications, and advanced techniques. Welcome back, dedicated scholars of AI, to the fourth lesson in our advanced exploration of artificial intelligence. Building upon our understanding of machine learning fundamentals, we now venture into the fascinating realm of deep learning, a subfield that has revolutionized the landscape of AI in recent years. In this lesson, we will dissect the core architectures of deep learning, explore its transformative applications across diverse domains, and delve into advanced techniques that are pushing the boundaries of what's possible. Prepare to unravel the intricacies of neural networks, understand their power, and gain insights into the cutting-edge research that is shaping the future of this dynamic field. The rise of deep learning, a paradigm shift in AI. Deep learning has emerged as a dominant force in AI, achieving remarkable success in areas that were once considered the exclusive domain of human intelligence. This section will explore the factors that have contributed to the rise of deep learning, highlighting the key differences between deep learning and traditional machine learning approaches. By understanding the unique capabilities of deep learning, you will appreciate its transformative impact on the field of AI. This will set the stage for a deeper dive. The success of deep learning can be attributed to several factors. The availability of massive datasets, such as ImageNet, has provided the fuel for training complex deep learning models. Advances in hardware, particularly the development of powerful GPUs, have made it computationally feasible to train these models. And the development of new architectures and training techniques has further improved their performance and efficiency. These factors converge to create a revolution. Unlike traditional machine learning, which often relies on hand-engineered features, deep learning algorithms can automatically learn hierarchical representations from raw data. This ability to learn features directly from data eliminates the need for manual feature engineering, a time-consuming and often domain-specific process. Deep learning automates feature extraction. This is a significant advantage. Deep learning models, particularly deep neural networks, are characterized by their depth, i.e., the number of layers in the network. Each layer learns to extract increasingly complex features from the input data, building a hierarchy of representations that capture intricate patterns and relationships. This depth is what gives deep learning its power. Depth enables complex learning. The development of powerful deep learning frameworks, such as TensorFlow and PyTorch, has democratized access to these techniques, enabling researchers and practitioners to build and deploy sophisticated models more easily. These frameworks provide high-level APIs and automatic differentiation, simplifying the development process. They have made deep learning more accessible. The impact of deep learning is evident across a wide range of applications, from image recognition and natural language processing to robotics and drug discovery. Its ability to learn from vast amounts of data and achieve superhuman performance in certain tasks has made it a cornerstone of modern AI. Deep learning is transforming many fields. It is a powerful tool for innovation. Convolutional neural networks, mastering visual data. Convolutional neural networks, CNNs, have revolutionized the field of computer vision, achieving breakthrough results in tasks such as image classification, object detection, and image segmentation. This section will delve into the architecture of CNNs, exploring the key components, such as convolutional layers, pooling layers, and activation functions. We will also examine popular CNN architectures, such as AlexNet, VGG, and ResNet, and discuss their applications in various domains. This will provide a thorough understanding of CNNs. CNNs are specifically designed to process grid-like data, such as images. Their architecture is inspired by the organization of the animal visual cortex, where neurons respond to specific regions of the visual field. This structure allows CNNs to efficiently learn spatial hierarchies of features. They are biologically inspired. Convolutional layers are the core building blocks of CNNs. These layers apply a set of learnable filters to the input image, producing feature maps that highlight specific patterns, such as edges, corners, and textures. Each filter learns to detect a particular feature. Convolution extracts spatial features. Pooling layers reduce the spatial dimensions of the feature maps, decreasing the number of parameters and computation in the network. Max pooling and average pooling are two commonly used pooling operations. Pooling also helps to make the network more robust to small variations in the input. It reduces dimensionality and adds robustness. Activation functions introduce nonlinearity into the network, enabling it to learn complex, nonlinear relationships between the input and output. Popular activation functions include ReLU, rectified linear unit, sigmoid, and tan. Nonlinearity is essential for learning complex patterns. Activation functions are crucial. Popular CNN architectures, such as AlexNet, VGG, and ResNet, have achieved state-of-the-art results on benchmark computer vision datasets. These architectures differ in their depth, the types of layers they use, and their connectivity patterns. They have pushed the boundaries of what's possible in computer vision. Each architecture has unique strengths. Recurrent neural networks, unlocking the secrets of sequential data. While CNNs excel at processing spatial data, recurrent neural networks, RNNs, are designed to handle sequential data, where the order of the data points matters. This section will explore the architecture of RNNs, including their ability to maintain a hidden state that captures information from previous time steps. We will also examine popular variants of RNNs, such as long short-term memory, LSTM, networks and gated recurrent units, GRUs, and discuss their applications in natural language processing, speech recognition, and time series analysis. This will provide a comprehensive understanding of RNNs. RNNs process sequential data by maintaining a hidden state that is updated at each time step. This hidden state acts as a memory, allowing the network to retain information from previous inputs in the sequence. The output at each time step is a function of the current input and the hidden state. RNNs are dynamic systems. They are ideal for language and time series. A key challenge in training RNNs is the vanishing gradient problem, where gradients become very small as they are propagated back through time. This makes it difficult for the network to learn long-range dependencies in the sequence. The vanishing gradient problem hinders learning. It is a major challenge in training RNNs. LSTM networks and GRUs are variants of RNNs that address the vanishing gradient problem by introducing gating mechanisms. These gates control the flow of information into and out of the hidden state, allowing the network to selectively remember or forget information over time. LSTMs and GRUs can learn long-range dependencies. They are more powerful than basic RNNs. RNNs have revolutionized natural language processing, NLP, achieving state-of-the-art results in tasks such as machine translation, text summarization, and sentiment analysis. They are also used in speech recognition, handwriting recognition, and time series forecasting. RNNs are powerful tools for sequential data. They have many applications in NLP. Despite their success, RNNs face challenges. They can be computationally expensive to train, particularly for very long sequences. They can also be difficult to parallelize, as the computations at each time step depend on the previous time step. Researchers are exploring alternative architectures, such as transformers, to address these limitations. There are ongoing efforts to improve them. There is still much room for improvement. Transformer networks, a new paradigm for sequence modeling. Transformer networks, introduced in a seminal paper, Attention is All You Need, have emerged as a powerful alternative to RNNs for sequence modeling tasks. This section will explore the architecture of transformers, focusing on the self-attention mechanism that allows them to capture long-range dependencies without the need for recurrence. We will also discuss the applications of transformers in natural language processing and other domains, and examine their strengths and limitations compared to RNNs. This will introduce a cutting-edge architecture. Transformers are based on the attention mechanism, which allows the model to weigh the importance of different parts of the input sequence when making predictions. Self-attention, a key innovation in transformers, enables the model to attend to different parts of the input sequence itself, capturing relationships between words or tokens in the sequence. Attention is a powerful mechanism. It allows for better understanding of context. Unlike RNNs, transformers do not process the input sequence sequentially. Instead, they process the entire sequence in parallel, making them more computationally efficient and easier to parallelize on modern hardware like GPUs. This parallel processing is a major advantage. It allows for faster training. The transformer architecture consists of an encoder and a decoder. The encoder processes the input sequence and generates a set of hidden representations. The decoder then uses these representations to generate the output sequence. Both the encoder and decoder use multiple layers of self-attention and feed-forward networks. The encoder-decoder structure is very effective. Transformers have achieved state-of-the-art results in various natural language processing tasks, including machine translation, text summarization, and question answering. They have also been applied to other domains, such as image generation and music composition. Their versatility makes them a powerful tool. They are setting new standards in NLP. Despite their advantages, transformers can be computationally expensive, particularly for very long sequences. The memory requirements of the self-attention mechanism scale quadratically with the sequence length. Researchers are exploring techniques to reduce the computational cost of transformers, such as sparse attention and linear attention. There are ongoing efforts to make them more efficient. There are always ways to improve. Generative adversarial networks, creating realistic data. Generative adversarial networks, GANs, represent a novel approach to generative modeling, where two networks, a generator and a discriminator, are trained in an adversarial manner. This section will explore the architecture and training dynamics of GANs, highlighting their ability to generate realistic data samples, such as images, text, and audio. We will also discuss various applications of GANs in areas such as image synthesis, style transfer, and data augmentation, and examine the challenges associated with training and evaluating these powerful models. This will introduce a fascinating area of deep learning. The generator network in a GAN is responsible for creating synthetic data samples that resemble the real data distribution. The discriminator network, on the other hand, is trained to distinguish between real data samples and those generated by the generator. These two networks are trained simultaneously in a game-theoretic framework. The generator tries to fool the discriminator. The discriminator tries to identify the fakes. The training process of a GAN can be viewed as a minimax game, where the generator tries to minimize the discriminator's ability to distinguish between real and generated samples, while the discriminator tries to maximize its ability to correctly classify the samples. This adversarial training process leads to a dynamic equilibrium where the generator produces increasingly realistic samples. It's a constant battle between the two networks. This leads to continuous improvement. GANs have demonstrated remarkable capabilities in generating high-quality images, videos, and audio. They have been used for image super-resolution, image-to-image translation, style transfer, and even for creating realistic synthetic faces. Their ability to generate new data has significant implications for various creative applications. They can create entirely new content. However, training GANs can be challenging. They are often difficult to stabilize and can suffer from issues such as mode collapse, where the generator produces only a limited variety of samples. Researchers are actively developing new techniques and architectures to address these challenges and improve the stability and quality of GAN training. Training GANs requires expertise. There are many tricks to learn. Evaluating the quality of generated samples is another challenge in GAN research. Traditional metrics may not adequately capture the perceptual quality of the generated data. New evaluation metrics and techniques are being developed to better assess the performance of GANs. Evaluating GANs is an active area of research. It is crucial for progress. Autoencoders, learning-efficient data representations. Autoencoders are a type of neural network that learns to efficiently compress and reconstruct data. This section will explore the architecture of autoencoders, including the encoder and decoder components, and discuss their applications in dimensionality reduction, feature learning, and anomaly detection. We will also examine variations of autoencoders, such as variational autoencoders, VAEs, and denoising autoencoders, and discuss their unique capabilities and use cases. This will introduce a powerful technique for representation learning. An autoencoder consists of two main parts, an encoder and a decoder. The encoder maps the input data to a lower-dimensional latent representation, often called the bottleneck or code. The decoder then reconstructs the original input from this latent representation. The network is trained to minimize the reconstruction error between the input and the output. The encoder compresses, the decoder decompresses. This creates a compact representation. Autoencoders can be used for dimensionality reduction, similar to principal component analysis, PCA, but with the added ability to learn nonlinear transformations. By forcing the network to reconstruct the input from a lower-dimensional representation, the autoencoder learns to capture the most important features of the data. They can learn complex mappings. Variational autoencoders, VAEs, are a probabilistic extension of autoencoders. Instead of encoding the input into a fixed-length vector, VAEs encode the input into a probability distribution over the latent space. This allows VAEs to generate new data samples by sampling from this distribution. VAEs are powerful generative models. They can create new data similar to the training data. Denoising autoencoders are trained to reconstruct the original input from a corrupted version of the input, such as an input with added noise. This forces the network to learn robust features that are not easily affected by noise. Denoising autoencoders can be used for feature extraction and pre-training deep networks. They learn to filter out noise. They are useful for robust learning. Autoencoders have found applications in various domains. They can be used for anomaly detection by identifying data points that are poorly reconstructed by the network. They can also be used for feature learning, where the learned latent representations are used as input to other machine learning models. They have many practical uses. They are a versatile tool. Advanced training techniques, optimization, regularization, and hyperparameter tuning. Training deep learning models is a complex process that involves more than just feeding data to a network. This section will explore advanced training techniques, including optimization algorithms, regularization methods, and hyperparameter tuning strategies. We will examine techniques such as stochastic gradient descent with momentum, ATOM, L1 and L2 regularization, dropout, and early stopping, and discuss how these techniques can improve the training process, prevent overfitting, and enhance the generalization ability of deep models. This will provide practical skills for building better models. Stochastic gradient descent, SGD, is a fundamental optimization algorithm for training deep learning models. However, vanilla SGD can be slow to converge and can get stuck in local optima. Techniques such as momentum and ATOM add momentum terms to the updates, allowing the optimizer to escape shallow local optima and converge faster. Momentum helps accelerate learning. ATOM adapts the learning rate for each parameter. Regularization techniques are crucial for preventing overfitting, a phenomenon where the model learns the training data too well and performs poorly on unseen data. L1 and L2 regularization add penalty terms to the loss function that discourage large weights. Dropout randomly drops out units during training, forcing the network to learn more robust features. Regularization improves generalization. It is essential for real-world performance. Early stopping is another effective technique for preventing overfitting. It involves monitoring the performance of the model on a validation set during training and stopping the training process when the performance on the validation set starts to degrade. This prevents the model from overfitting to the training data. Early stopping finds the sweet spot. It is a simple but powerful technique. Hyperparameter tuning is the process of finding the optimal values for the hyperparameters of a model, such as the learning rate, the number of layers, and the number of units in each layer. Techniques such as grid search, random search, and Bayesian optimization can be used to automate this process. Proper hyperparameter tuning is crucial. It can significantly impact performance. These advanced training techniques are essential for building high-performing deep learning models. They require a deep understanding of the underlying principles and careful experimentation to find the best settings for a given task and dataset. Mastering these techniques is key. It is a crucial part of the deep learning process. Deep reinforcement learning, combining deep learning with reinforcement learning. Deep reinforcement learning, DRL, combines the power of deep learning with the trial-and-error learning paradigm of reinforcement learning. This section will explore the exciting field of DRL, examining how deep neural networks can be used to approximate value functions or policies in complex, high-dimensional environments. We will discuss key algorithms such as deep Q networks, DQN, and their applications in game playing, robotics, and other domains. We will also address the challenges and future directions in this rapidly evolving area of AI. This will introduce a cutting-edge field. DRL has achieved remarkable success in recent years, with algorithms such as DQN demonstrating superhuman performance in playing Atari games and AlphaGo defeating world champions in the game of Go. These successes have showcased the potential of DRL to solve complex sequential decision-making problems. DRL has captured public imagination. It has shown the power of AI. In DRL, deep neural networks are used to approximate the value function, which estimates the expected cumulative reward for a given state or state-action pair, or the policy, which maps states to actions. The use of deep networks allows DRL agents to learn directly from raw sensory input, such as pixels in an image or sensor readings from a robot. Deep networks enable end-to-end learning. They can handle high-dimensional inputs. One of the key challenges in DRL is the exploration-exploitation dilemma. The agent must balance between exploring the environment to discover new strategies and exploiting its current knowledge to maximize rewards. Various techniques, such as epsilon-greedy exploration and entropy regularization, are used to address this challenge. Balancing exploration and exploitation is crucial. It is a fundamental challenge in RL. Another challenge is the instability of training deep reinforcement learning agents. The use of techniques such as experience replay, where the agent stores its experiences in a memory buffer and samples from it during training, and target networks, which provide a stable target for the Q-value updates, can help stabilize the training process. Stabilizing training is important. It leads to more reliable learning. DRL has shown promise in various applications beyond game playing, including robotics, where it can be used to train robots to perform complex manipulation tasks, and control systems, where it can be used to optimize the performance of industrial processes. As research in DRL continues to advance, we can expect to see even more impressive applications in the years to come. DRL has a bright future. It is a rapidly developing field. The ethical and societal implications of deep learning. As deep learning becomes increasingly powerful and pervasive, it is crucial to consider its ethical and societal implications. This section will delve into the critical issues surrounding the responsible development and deployment of deep learning systems, including concerns about bias, fairness, transparency, accountability, and the potential impact on employment and human autonomy. This will encourage a thoughtful and responsible approach to AI development. Deep learning models, like other machine learning systems, can inherit and amplify biases present in the training data. For instance, a deep learning model trained on a dataset of images that underrepresent certain demographics may perform poorly on those demographics, potentially leading to discriminatory outcomes. Addressing bias in data and models is crucial. It requires careful data curation and algorithmic fairness techniques. Ensuring fairness in deep learning systems is a complex challenge. Different definitions of fairness may conflict with each other, and it is important to consider the specific context and potential impacts on different groups when evaluating the fairness of a model. Developing fair and unbiased deep learning systems requires interdisciplinary collaboration and ongoing research. It is a multifaceted problem. Transparency and interpretability are also essential, particularly in high-stakes applications. Understanding why a deep learning model made a particular decision can help build trust, identify potential errors, and ensure accountability. Explainable AI, XAI, techniques for deep learning are being developed to address this challenge. Transparency is key for trust and accountability. It is crucial for critical applications. The potential impact of deep learning on employment is another important consideration. As deep learning-powered automation becomes more sophisticated, there are concerns that it could displace workers in various industries. It is crucial to consider strategies for mitigating these potential negative consequences, such as investing in education and retraining programs. The future of work must be considered. We need to adapt to these changes. Finally, the increasing autonomy of deep learning systems raises questions about human control and oversight. As these systems become more capable of making decisions without human intervention, it is important to establish appropriate safeguards and mechanisms for human oversight to ensure that they are used responsibly and ethically. Maintaining human oversight is essential. We must ensure responsible use of AI. These ethical and societal considerations highlight the need for a multifaceted approach to the development and deployment of deep learning systems. This includes technical solutions, such as bias detection and mitigation techniques, as well as broader societal discussions about the values we want to embed in these systems and the kind of future we want to create with them. It requires a collective effort. We must shape the future of AI responsibly. Lesson 5. Natural Language Processing, Bridging the Gap Between Human Language and Machine Understanding. Welcome back, dedicated learners, to the 5th lesson in our advanced exploration of artificial intelligence. In this lesson, we embark on a journey into the fascinating world of natural language processing, NLP, a field at the intersection of computer science, linguistics, and artificial intelligence that focuses on enabling computers to understand, interpret, and generate human language. We will explore the fundamental concepts, key techniques, and transformative applications of NLP, while also delving into the challenges and ethical considerations that arise when machines interact with the nuances of human communication. Prepare to unravel the complexities of language and discover how AI is bridging the gap between human expression and machine understanding. The essence of natural language processing, understanding human language. Natural language processing, NLP, is a transformative field of AI that empowers computers to interact with human language in a meaningful way. This section will explore the core concepts of NLP, highlighting its interdisciplinary nature and the challenges inherent in processing the complexities and ambiguities of human language. We will also examine the fundamental tasks that underpin many NLP applications, setting the stage for a deeper dive into specific techniques and algorithms. This provides a foundational understanding of NLP. At its heart, NLP aims to enable computers to understand, interpret, generate, and respond to human language, both in written and spoken forms. This involves bridging the gap between the structured, formal language of computers and the rich, nuanced, and often ambiguous nature of human communication. NLP draws upon insights from linguistics, computer science, and cognitive psychology. It is a truly interdisciplinary field. Human language is inherently complex. It is characterized by ambiguity, where words and phrases can have multiple meanings, variability, where the same meaning can be expressed in different ways, and context dependence, where the meaning of an utterance is influenced by the surrounding text or the situation in which it is used. These characteristics pose significant challenges for NLP systems. Ambiguity is a major hurdle. Context is crucial for understanding. Several fundamental tasks form the building blocks of many NLP applications. Tokenization involves breaking down text into individual words or units. Part-of-speech tagging identifies the grammatical role of each word, such as noun, verb, or adjective. Named entity recognition identifies and classifies named entities, such as people, organizations, and locations. These tasks provide a foundation for more complex analyses. They are essential preprocessing steps. Parsing involves analyzing the grammatical structure of a sentence, often represented as a parse tree. Sentiment analysis aims to determine the emotional tone or opinion expressed in a piece of text. Machine translation involves automatically translating text from one language to another. These tasks represent higher-level NLP capabilities. They enable a deeper understanding of language. Despite the challenges, NLP has made significant progress in recent years, driven by advances in machine learning, particularly deep learning, and the availability of large amounts of text data. These advancements have enabled the development of sophisticated NLP systems that can perform a wide range of language-related tasks with increasing accuracy and fluency. Progress has been rapid. The field is constantly evolving. Tokenization and text preprocessing, preparing text for machine consumption before text data can be analyzed by NLP algorithms, it must be preprocessed and transformed into a suitable format. This section will explore the crucial steps involved in text preprocessing, including tokenization, stemming, lemmatization, stop word removal, and handling punctuation and capitalization. We will also discuss techniques for representing text as numerical vectors, such as bag of words and TF-IDF, which are essential for many machine learning algorithms. This prepares text for analysis. Tokenization is the process of breaking down a text into individual words or tokens. This may seem simple, but it can be complex for languages that do not use spaces to separate words or for text that contains contractions, hyphenated words, or other special characters. Proper tokenization is crucial. It is the first step in text processing. Stemming and lemmatization are techniques for reducing words to their root form. Stemming typically involves removing suffixes, while lemmatization uses a dictionary to map words to their base form or lemma. For example, the stem of running might be run, while its lemma is also run. These techniques reduce redundancy. They help to group related words. Stop words are common words, such as the, a, and is, that are often removed from text before analysis, as they typically do not carry much meaning. However, the decision of whether or not to remove stop words depends on the specific application. Stop word removal can improve efficiency. It can also remove important context. Handling punctuation and capitalization can also impact the performance of NLP models. For example, converting all text to lowercase can help to reduce the vocabulary size, but it may also lose important information, such as the distinction between proper nouns and common nouns. These choices depend on the task. They require careful consideration. Representing text as numerical vectors is essential for applying machine learning algorithms to text data. The bag of words model represents a document as a collection of words and their frequencies, ignoring word order. TF-IDF, term frequency inverse document frequency, is a more sophisticated technique that weights words based on their importance in a document and across the entire corpus. These techniques create numerical representations. They enable the use of machine learning. Part-of-speech tagging and named entity recognition, extracting meaning from structure. Understanding the grammatical structure of a sentence and identifying key entities within the text are crucial steps in many NLP applications. This section will delve into the techniques of part-of-speech, POS, tagging and named entity recognition, NR, exploring how these methods can be used to extract meaning from text and provide valuable input for downstream tasks. We will also discuss the challenges associated with these tasks and the role of machine learning in achieving accurate and robust performance. These techniques unlock deeper understanding. POS tagging involves assigning a grammatical label, such as noun, verb, adjective, or adverb, to each word in a sentence. This provides information about the syntactic role of each word and can be used to disambiguate word senses and understand the relationships between words. POS tagging is fundamental. It provides grammatical context. Hidden Markov models, HMMs, and conditional random fields, CRFs, are statistical models commonly used for POS tagging. These models learn the probabilities of different tag sequences and can be trained on annotated corpora. Deep learning models, such as recurrent neural networks, RNNs, have also been successfully applied to POS tagging, achieving state-of-the-art results. Machine learning improves accuracy. It enables more robust tagging. NER involves identifying and classifying named entities in text, such as persons, organizations, locations, dates, and times. This information can be used for various purposes, such as information extraction, knowledge base population, and question answering. NER is crucial for understanding key entities. It has many practical applications. Rule-based systems and machine learning models, including CRFs and deep learning architectures, are used for NER. These models learn to recognize patterns in the text that indicate the presence of named entities, such as capitalization, surrounding words, and prefixes or suffixes. Accurate NER is challenging. Context is crucial for accurate recognition. Both POS tagging and NER face challenges, such as ambiguity, where a word can have multiple possible tags or an entity can have different interpretations depending on the context, and variability, where the same entity can be expressed in different ways. Addressing these challenges requires sophisticated models that can capture the nuances of language and leverage contextual information. Ambiguity and variability are major hurdles. They require sophisticated solutions. Syntactic parsing and dependency grammar, unveiling the structure of sentences. Understanding the grammatical relationships between words in a sentence is essential for many NLP tasks, including machine translation, question answering, and information extraction. This section will explore the concepts of syntactic parsing and dependency grammar, examining how these techniques can be used to unveil the underlying structure of sentences and represent the relationships between words in a hierarchical manner. We will also discuss different parsing algorithms and the role of machine learning in building accurate and efficient parsers. This allows for deeper linguistic analysis. Syntactic parsing aims to analyze the grammatical structure of a sentence and represent it as a parse tree. The parse tree shows the hierarchical relationships between words and phrases, revealing the underlying syntactic structure of the sentence. Parsing is essential for understanding sentence structure. It reveals how words relate to each other. Constituency parsing and dependency parsing are two main approaches to syntactic parsing. Constituency parsing represents the sentence structure using a tree of nested phrases, where each phrase is a constituent, such as a noun phrase or a verb phrase. Dependency parsing, on the other hand, represents the sentence structure as a set of directed relationships between words, where each word depends on another word, called its head. Each approach has its strengths. They offer different perspectives on sentence structure. Various algorithms are used for parsing, including the CKY algorithm for context-free grammars and transition-based parsers for dependency parsing. These algorithms use dynamic programming or greedy approaches to efficiently search for the most likely parse tree given a set of grammar rules or a statistical model. Parsing algorithms are complex. They require efficient search strategies. Machine learning has played an increasingly important role in parsing, particularly in the development of statistical parsers that learn from annotated corpora. These parsers use features extracted from the sentence, such as word embeddings and POS tags, to predict the most likely parse tree. Deep learning models have also been successfully applied to parsing, achieving state-of-the-art results. Machine learning improves parsing accuracy. It enables data-driven approaches. Accurate parsing is crucial for many downstream NLP applications. For example, in machine translation, parsing can help to disambiguate sentence structure and improve the quality of translations. In information extraction, parsing can be used to identify relationships between entities and extract relevant information from text. Parsing is a fundamental building block. It enables more advanced NLP tasks. Word embeddings and semantic analysis, capturing the meaning of words while understanding the grammatical structure of language is important. Capturing the meaning of words and their relationships is equally crucial for many NLP tasks. This section will explore the concept of word embeddings, which represent words as dense vectors in a continuous vector space, capturing semantic and syntactic relationships between words. We will examine popular word embedding techniques, such as word-to-vec and glove, and discuss their applications in semantic analysis, similarity measurement, and analogy detection. This allows for a deeper understanding of meaning. Word embeddings are a powerful technique for representing the meaning of words in a way that can be used by machine learning algorithms. In a word embedding model, each word is represented as a dense vector in a high-dimensional space, where semantically similar words are located close to each other. These vectors capture semantic relationships. They encode word meanings. Word-to-vec and glove are two widely used algorithms for learning word embeddings. Word-to-vec uses a neural network to predict the context words given a target word, continuous bag of words model, or to predict the target word given the context words, skipgram model. Glove, on the other hand, constructs a co-occurrence matrix of words and factorizes it to obtain word vectors. These algorithms learn from large text corpora. They capture statistical patterns in language. Word embeddings have been shown to capture various semantic and syntactic relationships between words. For example, the vector difference between king and man is similar to the vector difference between queen and woman, capturing the concept of gender. Word embeddings can also be used to measure word similarity, identify analogies, and perform other semantic analysis tasks. They reveal hidden relationships between words. They are useful for various NLP tasks. Word embeddings can be used as input features for various downstream NLP tasks, such as text classification, sentiment analysis, and machine translation. By representing words as dense vectors, these models can leverage the semantic information captured in the embeddings to improve their performance. They are a powerful tool for many applications. They enhance the performance of other models. Despite their success, word embeddings have limitations. They can be sensitive to biases present in the training data, and they may not capture all the nuances of word meaning, such as polysemy, where a word can have multiple meanings. Researchers are actively working on addressing these limitations and developing more sophisticated and nuanced word representations. There is ongoing research to improve them. They are constantly being refined. Sentiment analysis and opinion mining, gauging the emotional tone of text. Understanding the sentiment or opinion expressed in text is crucial for various applications, such as brand monitoring, customer feedback analysis, and social media analysis. This section will explore the field of sentiment analysis and opinion mining, examining techniques for automatically determining the emotional tone or attitude expressed in a piece of text. We will discuss lexicon-based approaches, machine learning methods, and the challenges associated with analyzing nuanced and subjective language. This allows for understanding public opinion. Sentiment analysis, also known as opinion mining, aims to automatically determine the sentiment expressed in a piece of text, typically classifying it as positive, negative, or neutral. More fine-grained analysis can also be performed, such as detecting specific emotions, e.g., joy, anger, sadness, or identifying the target of the sentiment. Sentiment analysis has many practical applications. It can provide valuable insights. Lexicon-based approaches to sentiment analysis rely on a predefined dictionary of words and their associated sentiment scores. These scores can be manually created by experts or automatically derived from existing resources. The overall sentiment of a text is then calculated by aggregating the sentiment scores of its constituent words. Lexicon-based methods are simple and interpretable. They rely on existing resources. Machine learning approaches to sentiment analysis typically involve training a classifier on a labeled dataset of text, where each text is annotated with its corresponding sentiment. Various features can be used, such as bag of words, n-grams, word embeddings, and linguistic features. Deep learning models, such as recurrent neural networks and convolutional neural networks, have achieved state-of-the-art results in sentiment analysis. Machine learning offers greater accuracy. It can learn complex patterns. Sentiment analysis faces several challenges. Sarcasm, irony, and figurative language can be difficult to detect automatically. Negation and other linguistic phenomena can also affect the sentiment of a sentence. Furthermore, sentiment can be subjective and context-dependent, making it challenging to develop universally applicable models. These challenges require sophisticated solutions. Context and nuance are difficult to capture. Despite these challenges, sentiment analysis has found numerous applications in various domains. Businesses use it to monitor brand reputation, analyze customer feedback, and understand public opinion about their products or services. It is also used in social sciences to study public opinion, political discourse, and social trends. It has become an important tool. It provides valuable insights into public sentiment. Machine translation, breaking down language barriers. Machine translation, MT, is one of the oldest and most challenging applications of NLP, aiming to automatically translate text or speech from one language to another. This section will explore the evolution of MT, from early rule-based systems to modern neural machine translation, NMT, approaches. We will examine the key concepts and techniques used in NMT, such as sequence-to-sequence models, attention mechanisms, and the use of large parallel corpora. We will also discuss the challenges and limitations of current MT systems and explore future directions in this rapidly advancing field. This allows for communication across languages. Early approaches to MT were primarily rule-based, relying on handcrafted linguistic rules and bilingual dictionaries to translate between languages. These systems were often brittle, difficult to maintain, and struggled with the complexities and nuances of natural language. Rule-based MT was limited in its capabilities. It required extensive manual effort. Statistical machine translation, SMT, emerged in the 1990s as a data-driven approach to MT. SMT systems learn translation models from large parallel corpora, which are collections of texts in two languages that are translations of each other. Phrase-based SMT, which translates phrases rather than individual words, became the dominant paradigm in SMT. SMT was a major advancement. It leveraged data to improve translation quality. Neural machine translation, NMT, has revolutionized the field of MT in recent years. NMT systems use deep neural networks, typically sequence-to-sequence models with attention mechanisms, to directly learn a mapping from the source language to the target language. NMT models can capture long-range dependencies and produce more fluent and accurate translations compared to previous approaches. NMT has significantly improved translation quality. It is the current state of the art. The availability of large parallel corpora, such as those created by the European Parliament and the United Nations, has been crucial for training NMT systems. However, obtaining high-quality parallel data for all language pairs remains a challenge, particularly for low-resource languages. Data scarcity is a major bottleneck. It limits the applicability of NMT. Despite the impressive progress in NMT, challenges remain. Current systems still struggle with issues such as rare words, domain adaptation, and maintaining consistency and coherence in long translations. Researchers are actively working on addressing these challenges and developing more robust and versatile NMT systems. There is ongoing research to improve NMT. It is a constantly evolving field. Topic modeling and document clustering. Discovering themes in text. Topic modeling and document clustering are unsupervised learning techniques that aim to discover hidden thematic structures in large collections of text. This section will explore popular topic modeling algorithms, such as latent Dirichlet allocation, LDA, and discuss how they can be used to identify latent topics in a corpus and represent documents as mixtures of these topics. We will also examine techniques for document clustering and discuss the applications of these methods in information retrieval, text summarization, and exploratory data analysis. This allows for discovering hidden structures in text. Topic modeling is a technique for discovering abstract topics that occur in a collection of documents. A topic is typically represented as a probability distribution over words, where words that are more likely to belong to the topic have higher probabilities. Topic models can be used to summarize large text collections, identify themes, and organize documents. Topic modeling reveals underlying themes. It provides a high-level overview of a corpus. Latent Dirichlet allocation, LDA, is a widely used probabilistic topic model. LDA assumes that each document is a mixture of topics, and each topic is a distribution over words. Given a corpus of documents, LDA aims to infer the underlying topic structure that generated the documents. LDA is a generative model. It is based on probabilistic assumptions. The inference process in LDA involves estimating the topic distribution for each document and the word distribution for each topic. This is typically done using techniques such as Gibbs sampling or variational inference. The output of LDA is a set of topics, each represented as a distribution over words, and a set of topic proportions for each document. LDA provides a probabilistic representation. It captures the thematic structure of the corpus. Document clustering, on the other hand, aims to group similar documents together based on their content. Traditional clustering algorithms, such as k-means and hierarchical clustering, can be applied to text data by representing documents as vectors, using techniques such as TF-IDF or word embeddings. Clustering can be used to organize large document collections, identify related documents, and discover subtopics within a corpus. Document clustering groups similar documents. It helps in organizing and navigating large text collections. Topic modeling and document clustering have numerous applications. In information retrieval, they can be used to improve search results by grouping related documents or identifying documents that are relevant to a particular topic. In text summarization, they can be used to identify the most important topics in a document or a collection of documents. They can also be used for exploratory data analysis, helping researchers to understand the main themes and patterns in a large text corpus. They have many practical uses. They are valuable tools for text analysis. However, topic modeling and document clustering also face challenges. The quality of the results can be sensitive to the choice of parameters, such as the number of topics or clusters. Evaluating the quality of the discovered topics or clusters can also be subjective and challenging. Researchers are developing new techniques and evaluation metrics to address these challenges and improve the robustness and interpretability of these methods. There is ongoing research to refine these techniques. They are constantly being improved. Advanced NLP techniques and future directions. Pushing the boundaries of language understanding. The field of NLP is rapidly evolving, with researchers constantly developing new techniques and pushing the boundaries of what's possible. This section will explore some of the advanced techniques and future directions in NLP, including transfer learning, multitask learning, and the quest for more robust and generalizable language understanding. We will also discuss the potential impact of these advancements on various applications and the challenges that lie ahead. This provides a glimpse into the future of NLP. Transfer learning has emerged as a powerful technique in NLP, allowing models to leverage knowledge learned from one task or domain to improve performance on another. Large pre-trained language models, such as BERT and GPT, have achieved remarkable success in various NLP tasks by first pre-training on massive text corpora and then fine-tuning on specific downstream tasks. Transfer learning reduces the need for large labeled datasets. It leverages pre-existing knowledge. Multitask learning is another promising direction, where a single model is trained to perform multiple NLP tasks simultaneously. This can improve the model's generalization ability and efficiency by leveraging the shared representations and knowledge across different tasks. Multitask learning can also help to address the problem of data scarcity for individual tasks. It leverages synergies between different tasks. It is a more holistic approach to learning. Researchers are also exploring ways to make NLP models more robust and generalizable. This includes developing techniques for handling noisy or adversarial inputs, improving the ability of models to generalize to new domains or languages, and developing more sophisticated methods for incorporating common sense reasoning and world knowledge into NLP systems. Robustness and generalizability are key challenges. They are essential for real-world applications. The development of more powerful and efficient hardware, such as specialized AI chips, is also driving progress in NLP. These advancements enable the training and deployment of larger and more complex models, pushing the boundaries of what's possible in terms of language understanding and generation. Hardware advancements are crucial. They enable more powerful models. Despite the impressive progress, significant challenges remain in NLP. Achieving truly human-like language understanding, with its nuances, ambiguities, and reliance on context and world knowledge, is still a distant goal. Addressing these challenges will require interdisciplinary research, drawing upon insights from linguistics, cognitive science, computer science, and other fields. The quest for human-level language understanding continues. It is a grand challenge for AI. The future of NLP holds immense promise. As NLP techniques continue to improve, we can expect to see even more transformative applications in areas such as human-computer interaction, education, healthcare, and scientific discovery. NLP has the potential to revolutionize the way we interact with technology and with each other, bridging the gap between human language and machine understanding. The future of NLP is bright. It holds immense potential for positive impact. Lesson 6, Computer Vision, Enabling Machines to See and Understand the Visual World. Welcome back, esteemed scholars of AI, to the 6th lesson in our advanced exploration of artificial intelligence. In this lesson, we venture into the captivating domain of computer vision, a field that empowers machines to perceive, interpret, and understand the visual world, much like humans do. We will explore the fundamental concepts, key techniques, and transformative applications of computer vision, while also delving into the challenges and ethical considerations that arise when machines are granted the power of sight. Prepare to unravel the intricacies of visual perception and discover how AI is enabling machines to not just see, but truly understand the visual data that surrounds us. The essence of computer vision, from pixels to percepts. Computer vision is a multidisciplinary field that aims to enable computers to gain a high-level understanding from digital images or videos. This section will explore the core concepts of computer vision, highlighting its relationship to human vision and the challenges inherent in replicating the complex processes of visual perception. We will also examine the fundamental tasks that underpin many computer vision applications, setting the stage for a deeper dive into specific techniques and algorithms. This provides a foundational understanding of computer vision. At its core, computer vision seeks to automate tasks that the human visual system can do. This involves not just capturing images, but also processing, analyzing, and understanding them to extract meaningful information and make decisions. Computer vision draws upon insights from computer science, mathematics, engineering, and cognitive science. It is an interdisciplinary endeavor. Human visual perception is a remarkably complex process, involving intricate interactions between the eyes, the visual cortex, and other parts of the brain. Replicating this process in machines is a formidable challenge, requiring the development of sophisticated algorithms that can handle the variability, ambiguity, and complexity of visual data. Human vision is a remarkable feat. It is difficult to replicate artificially. Several fundamental tasks form the building blocks of many computer vision applications. Image classification involves assigning a label to an entire image, such as cat or dog. Object detection involves identifying and localizing objects within an image, typically by drawing bounding boxes around them. Image segmentation involves partitioning an image into meaningful regions, often corresponding to different objects or surfaces. These tasks provide a foundation for more complex analyses. They are essential for visual understanding. Other important computer vision tasks include object tracking, which involves following the movement of objects over time in a video sequence, depth estimation, which involves inferring the distance of objects from the camera, and image restoration, which involves removing noise or other artifacts from images. These tasks enable a deeper understanding of the visual world. They have many practical applications. Despite the challenges, computer vision has made significant progress in recent years, driven by advances in machine learning, particularly deep learning, and the availability of large-scale image and video datasets. These advancements have enabled the development of sophisticated computer vision systems that can perform a wide range of tasks with increasing accuracy and robustness. Progress has been rapid. The field is constantly evolving. Image formation and representation, capturing and encoding visual data. Before visual data can be processed by computer vision algorithms, it must be captured and represented in a digital format. This section will explore the process of image formation, including the role of cameras and sensors in capturing light and converting it into digital signals. We will also discuss different image representations, such as RGB and grayscale, and examine techniques for encoding and compressing images. This provides a foundation for understanding how images are captured and processed. Image formation typically involves using a camera or other sensor to capture light reflected from a scene. The camera lens focuses the light onto a sensor, which converts the light intensity into electrical signals. These signals are then digitized and stored as an array of pixel values. Cameras capture light and convert it to digital signals. This is the first step in image processing. Digital images are typically represented as a two-dimensional array of pixels, where each pixel represents the color or intensity at a specific location in the image. Color images are often represented using the RGB color model, where each pixel is represented by 3 values corresponding to the intensity of red, green, and blue light. Grayscale images, on the other hand, use a single value to represent the intensity of each pixel. Images can be represented in various formats. Each format has its own advantages. Image compression techniques are used to reduce the size of image files while preserving essential information. Lossless compression methods, such as PNG, allow the original image to be perfectly reconstructed from the compressed data. Lossy compression methods, such as JPEG, discard some information to achieve higher compression ratios, but may introduce artifacts into the image. Compression is important for efficient storage and transmission. It involves trade-offs between file size and image quality. Image preprocessing techniques are often applied to enhance the quality of images or to extract relevant features. These techniques can include noise reduction, contrast enhancement, edge detection, and color space transformations. Preprocessing can improve the performance of downstream computer vision algorithms. It is an important step in many applications. Understanding the process of image formation and representation is crucial for developing effective computer vision systems. The choice of camera, sensor, image format, and preprocessing techniques can all have a significant impact on the performance of downstream algorithms. These choices must be made carefully. They depend on the specific application. Feature detection and description. Identifying key points in images. Feature detection and description are fundamental steps in many computer vision applications, enabling the identification and representation of salient points or regions in an image. This section will explore various feature detection algorithms, such as Harris corner detection, SIFT, scale invariant feature transform, and SURF, speeded up robust features, and discuss how these features can be used for tasks such as object recognition, image matching, and 3D reconstruction. We will also examine the properties of good feature detectors and descriptors, such as invariance to scale, rotation, and illumination changes. This enables robust visual recognition. Feature detection aims to identify points or regions in an image that are distinctive and informative, such as corners, edges, or blobs. These features can be used as building blocks for more complex tasks, such as object recognition and image stitching. Feature detection is a crucial step. It provides a compact representation of the image. The Harris corner detector is a classic algorithm that identifies corners by looking for points where the image gradient changes significantly in multiple directions. SIFT and SURF are more advanced algorithms that detect key points that are invariant to scale, rotation, and illumination changes. These algorithms also compute descriptors that capture the local appearance around each key point. These detectors are robust to various transformations. They are widely used in practice. Good feature detectors should be repeatable, meaning that they should detect the same features under different viewing conditions. They should also be distinctive, meaning that different features should have different descriptors. Good feature descriptors should be invariant to scale, rotation, and illumination changes, allowing features to be matched across different images. These properties are essential for reliable matching. They ensure robustness to variations in viewpoint. Feature detection and description have numerous applications. In object recognition, features can be used to match objects across different images, even if they appear at different scales or orientations. In image stitching, features can be used to align and combine multiple images into a panorama. In 3D reconstruction, features can be used to estimate the camera pose and reconstruct the 3D structure of a scene. They have many practical uses. They are essential for many computer vision tasks. Despite their success, feature detection and description still face challenges. Detecting features that are both distinctive and invariant to various transformations is a difficult problem. Furthermore, the computational cost of feature detection and description can be high, particularly for high-resolution images. Researchers are actively working on developing more efficient and robust feature detection and description algorithms. There is ongoing research to improve these techniques. They are constantly being refined. Object recognition and classification, identifying and categorizing objects and images. Object recognition and classification are central tasks in computer vision, enabling machines to identify and categorize objects within images. This section will explore various approaches to object recognition, including template matching, feature-based methods, and deep learning-based techniques. We will examine how convolutional neural networks, CNNs, have revolutionized object recognition, achieving state-of-the-art performance on benchmark datasets. We will also discuss the challenges and limitations of current object recognition systems and explore future directions in this rapidly evolving field. This enables machines to understand the content of images. Early approaches to object recognition relied on template matching, where a predefined template of an object is compared to different regions of an image to find a match. However, template matching is sensitive to variations in scale, rotation, and viewpoint, making it impractical for many real-world scenarios. Template matching is simple but limited. It is not robust to variations in appearance. Feature-based methods, which use feature detectors and descriptors such as SIFT and SURF, offer a more robust approach to object recognition. These methods extract features from an image and compare them to features extracted from a database of known objects. Object recognition can be performed by finding the object in the database that has the most matching features. Feature-based methods are more flexible. They can handle variations in appearance. Deep learning, particularly CNNs, has dramatically improved the accuracy and robustness of object recognition. CNNs can learn hierarchical features directly from raw pixel data, eliminating the need for hand-engineered features. They have achieved state-of-the-art performance on benchmark datasets such as ImageNet, demonstrating their ability to recognize a wide range of objects with high accuracy. Deep learning has revolutionized object recognition. It has enabled significant improvements in accuracy. Despite the impressive progress, object recognition still faces challenges. Recognizing objects under significant variations in viewpoint, illumination, and occlusion remains a difficult problem. Furthermore, current object recognition systems often struggle with fine-grained classification, where the goal is to distinguish between similar object categories. These challenges require further research. They are active areas of investigation. The future of object recognition is likely to involve the development of more sophisticated deep learning architectures, the incorporation of 3D information and contextual cues, and the use of unsupervised or weakly supervised learning to reduce the reliance on large labeled datasets. These advancements will enable the development of more robust, accurate, and versatile object recognition systems. The field is constantly pushing boundaries. It is moving towards more general visual understanding. Object detection and localization, finding and pinpointing objects in images, while object recognition focuses on classifying entire images. Object detection aims to identify and localize multiple objects within an image. This section will explore various object detection algorithms, including region-based methods like RCNN, Fast RCNN, and Faster RCNN, as well as single-shot detectors like YOLO, You Only Look Once, and SSD, Single-Shot Multibox Detector. We will examine how these algorithms balance accuracy and speed, and discuss their applications in various domains, such as autonomous driving, surveillance, and robotics. This enables machines to locate objects within a scene. Object detection involves not only classifying objects but also determining their location within the image, typically by drawing a bounding box around each object. This is a more challenging task than image classification, as it requires the system to simultaneously identify multiple objects and determine their spatial extent. Object detection is a complex task. It requires both classification and localization. Region-based methods, such as the RCNN family of detectors, first propose a set of candidate regions in the image that may contain objects. These regions are then classified using a CNN, and their bounding boxes are refined. Faster RCNN, a more advanced version, uses a region proposal network, RPN, to generate region proposals, making the detection process more efficient. Region-based methods are accurate but can be slow. They involve multiple stages of processing. Single-shot detectors, such as YOLO and SSD, perform object detection in a single pass through the network, making them significantly faster than region-based methods. These detectors divide the image into a grid and predict bounding boxes and class probabilities for each grid cell. They are well suited for real-time applications where speed is crucial. Single-shot detectors are fast and efficient. They are ideal for real-time applications. Object detection has numerous applications in various domains. In autonomous driving, object detection is used to identify pedestrians, vehicles, and other objects on the road. In surveillance, it can be used to detect and track people or objects of interest. In robotics, it can be used to enable robots to perceive and interact with their environment. It has many practical uses. It is essential for many real-world applications. Despite the progress in object detection, challenges remain. Detecting small objects, handling occlusions, and achieving real-time performance on resource-constrained devices are active areas of research. Researchers are developing new architectures and techniques to address these challenges and improve the accuracy, speed, and robustness of object detection systems. There is ongoing research to improve these systems. They are constantly being refined. Image segmentation, partitioning images into meaningful regions. Image segmentation goes beyond object detection by assigning a label to every pixel in an image, effectively partitioning the image into meaningful regions or segments. This section will explore different approaches to image segmentation, including traditional methods like thresholding and region growing, as well as more advanced techniques like fully convolutional networks, FCNs, and UNet. We will discuss the challenges of accurate and efficient segmentation and examine the applications of this technique in areas such as medical image analysis, autonomous driving, and scene understanding. This enables a more detailed understanding of image content. Image segmentation aims to partition an image into a set of non-overlapping regions, where each region corresponds to a different object or part of an object. This is a more fine-grained analysis than object detection, as it provides a pixel-level understanding of the image content. Image segmentation provides detailed information. It is a powerful tool for image analysis. Traditional image segmentation methods include thresholding, which segments an image based on pixel intensity values, and region growing, which starts with a seed pixel and iteratively adds neighboring pixels that satisfy certain criteria. These methods are relatively simple but may not be effective for complex images with varying illumination or texture. Traditional methods are simple but limited. They may not be suitable for complex images. Fully convolutional networks, FCNs, have revolutionized image segmentation by enabling end-to-end learning of pixel-level labels. FCNs replace the fully connected layers in a traditional CNN with convolutional layers, allowing them to output a segmentation map of the same size as the input image. They can learn complex patterns and relationships. They are effective for semantic segmentation. UNet is another popular architecture for image segmentation, particularly in biomedical applications. It consists of a contracting path that captures context and an expanding path that enables precise localization. The two paths are connected by skip connections that help to preserve fine-grained details. UNet is known for its accuracy and efficiency. It is widely used in medical image analysis. Image segmentation has numerous applications. In medical image analysis, it can be used to segment organs, tumors, and other structures of interest. In autonomous driving, it can be used to segment the road, pedestrians, and vehicles. In scene understanding, it can be used to segment different objects and surfaces in a scene. It has many important applications. It is a crucial tool in various domains. Video analysis and action recognition, understanding motion and events. While much of computer vision research has focused on static images, analyzing video data presents unique challenges and opportunities. This section will explore techniques for video analysis, including motion estimation, object tracking, and action recognition. We will examine how recurrent neural networks, RNNs, and 3D convolutional neural networks, 3D CNNs, can be used to process video data and recognize actions and events. We will also discuss the applications of video analysis in areas such as surveillance, sports analysis, and human-computer interaction. This enables machines to understand dynamic scenes. Video analysis involves processing sequences of images to understand motion, track objects, and recognize actions and events. This is a more complex task than static image analysis, as it requires the system to consider the temporal dimension in addition to the spatial information. Video analysis requires temporal understanding. It is a challenging but important area. Motion estimation techniques, such as optical flow, aim to estimate the motion of pixels or regions between consecutive frames in a video. This information can be used for various tasks, such as video stabilization, object tracking, and action recognition. Motion estimation provides insights into the dynamics of a scene. It is a fundamental component of video analysis. Object tracking involves following the movement of specific objects over time in a video sequence. This can be challenging due to occlusions, changes in appearance, and fast motion. Various algorithms, such as Kalman filtering and particle filtering, are used for object tracking. Object tracking enables monitoring of objects over time. It has applications in surveillance and robotics. Action recognition aims to identify and classify actions performed by humans or other agents in a video. This can be approached using techniques such as RNNs, which can model temporal dependencies in sequential data, and 3D CNNs, which can capture both spatial and temporal information in video volumes. Action recognition is crucial for understanding human behavior. It has applications in human-computer interaction and video surveillance. Video analysis has numerous applications. In surveillance, it can be used to detect unusual or suspicious activities. In sports analysis, it can be used to track players, analyze their movements, and generate statistics. In human-computer interaction, it can be used to enable gesture recognition and other forms of nonverbal communication. It has many practical uses. It is a rapidly growing field. Ethical considerations and societal impact of computer vision. As computer vision systems become increasingly powerful and pervasive, it is essential to consider their ethical implications and societal impact. This section will explore the critical issues surrounding the responsible development and deployment of computer vision technologies, including concerns about privacy, surveillance, bias, and the potential impact on employment and human autonomy. This encourages a thoughtful and responsible approach to computer vision development. One of the primary concerns is the potential for computer vision to be used for mass surveillance, infringing on individuals' privacy rights. Facial recognition technology, in particular, has raised concerns about its potential for misuse by governments and law enforcement agencies. It is crucial to establish safeguards and regulations to prevent the use of these technologies. Privacy is a major concern. It must be protected. Bias in computer vision systems is another critical issue. If these systems are trained on biased data, they can perpetuate and even amplify existing societal biases, leading to unfair or discriminatory outcomes. For example, facial recognition systems have been shown to be less accurate for people with darker skin tones, potentially leading to misidentification and wrongful accusations. Bias can lead to unfair outcomes. It must be addressed proactively. The impact of computer vision on employment is also a concern. As computer vision systems become more capable of performing tasks that were previously done by humans, such as object recognition, inspection, and surveillance, there are concerns about job displacement in certain industries. It is important to consider strategies for mitigating these potential negative impacts. The future of work must be considered. We need to adapt to these changes. The increasing autonomy of computer vision systems raises questions about human control and oversight. As these systems are deployed in safety-critical applications, such as autonomous driving and medical diagnosis, it is essential to ensure that they are reliable, robust, and accountable. Establishing clear lines of responsibility and mechanisms for human intervention is crucial. Human oversight is essential. We must ensure responsible use of these systems. The potential for computer vision to be used for malicious purposes, such as deepfakes and the creation of realistic but fabricated videos, is another growing concern. These technologies can be used to spread misinformation, damage reputations, and erode trust in visual media. Developing techniques to detect and counter these threats is an urgent priority. The potential for misuse must be addressed. We need safeguards against malicious use. Addressing these ethical and societal challenges requires a multifaceted approach. This includes technical solutions, such as developing methods for detecting and mitigating bias in computer vision systems, as well as broader societal discussions about the values we want to embed in these technologies and the kind of future we want to create with them. It requires a collective effort. We must shape the future of computer vision responsibly. Future directions and emerging trends in computer vision. The field of computer vision is rapidly advancing, with new techniques and applications emerging at an accelerating pace. This section will explore some of the most promising future directions and emerging trends in computer vision, including the development of more general and robust visual understanding systems, the integration of vision with other modalities, and the use of computer vision to address pressing societal challenges. This provides a glimpse into the future of computer vision. One major trend is the development of more general and robust visual understanding systems. Current computer vision systems are often specialized for specific tasks, such as object recognition or image segmentation. Researchers are working towards developing systems that can perform a wider range of visual tasks and generalize to new, unseen scenarios, similar to how humans can understand and reason about a wide variety of visual inputs. General visual understanding is a key goal. It is a major challenge for the field. The integration of vision with other modalities, such as language and audio, is another important direction. This involves developing systems that can understand and reason about information from multiple sources, enabling more natural and intuitive human-computer interaction. For example, a system that can understand both spoken instructions and visual cues would be more versatile and user-friendly than a system that relies on only one modality. Multimodal understanding is crucial for richer interaction. It enables more natural communication with machines. The use of computer vision to address pressing societal challenges, such as climate change, healthcare, and education, is a growing area of research. For example, computer vision can be used to analyze satellite imagery to monitor deforestation or track the movement of glaciers. It can also be used to develop assistive technologies for people with visual impairments or to create personalized learning experiences in education. Computer vision can have a positive impact. It can be used to address important societal challenges. The development of more efficient and scalable computer vision systems is also a key area of research. This includes developing techniques for training models with less data, reducing the computational cost of inference, and deploying models on resource-constrained devices such as mobile phones and embedded systems. Efficiency and scalability are crucial for real-world deployment. They enable wider adoption of computer vision technologies. Finally, the increasing availability of large-scale datasets and the development of new deep learning architectures and training techniques are likely to continue to drive progress in computer vision. As these trends converge, we can expect to see even more transformative applications of computer vision in the years to come, further blurring the lines between human and machine perception. The future of computer vision is bright. It holds immense potential for innovation. Lesson 7, Reinforcement Learning, Mastering the Art of Decision-Making Through Interaction. Welcome back, dedicated learners, to the 7th lesson in our advanced exploration of artificial intelligence. In this lesson, we embark on a journey into the dynamic realm of reinforcement learning, RL, a powerful paradigm that enables agents to learn optimal behaviors through interaction with an environment. We will explore the fundamental concepts of RL, including agents, environments, rewards, and policies, and delve into key algorithms such as Q-learning, SURSA, and deep Q networks. We will also examine the applications of RL in diverse domains, from game playing and robotics to resource management and personalized recommendations, while considering the challenges and future directions of this exciting field. Prepare to master the art of decision-making through interaction and discover how RL is shaping intelligent systems that can learn, adapt, and thrive in complex environments. The essence of reinforcement learning, learning through trial and error. Reinforcement learning, RL, is a subfield of machine learning where an agent learns to make decisions by interacting with an environment and receiving feedback in the form of rewards or penalties. 2. This section will explore the core concepts of RL, highlighting its unique characteristics and contrasting it with other machine learning paradigms. We will also discuss the key components of an RL system, including the agent, environment, state, action, reward, and policy, and examine the fundamental goal of RL, which is to learn an optimal policy that maximizes cumulative rewards over time. This provides a foundational understanding of RL. Unlike supervised learning, where the agent learns from labeled examples, or unsupervised learning, where the agent learns from unlabeled data, RL involves an agent learning through trial and error. The agent takes actions in an environment, observes the consequences of those actions, and learns to adjust its behavior to maximize future rewards. This makes RL particularly well suited for sequential decision-making problems. RL learns from experience. It is a dynamic learning process. The agent is the learner and decision-maker in an RL system. It interacts with the environment by taking actions and receiving observations and rewards. The environment is the external system with which the agent interacts. It can be a simulated world, a game, or a real-world system such as a robot or a stock market. The agent and environment interact continuously. The agent's actions affect the environment. The state represents the current situation of the agent in the environment. It is a summary of the information that is relevant for making decisions. The action is a choice made by the agent at a particular state. The reward is a scalar feedback signal that indicates the desirability of an action or a state. The policy is a mapping from states to actions, representing the agent's behavior strategy. These are the key elements of RL. They define the interaction between agent and environment. The fundamental goal of RL is to learn an optimal policy, which is a policy that maximizes the expected cumulative reward over time. This involves finding a balance between exploration, trying out new actions to discover their consequences, and exploitation, taking actions that are known to yield high rewards. The exploration-exploitation dilemma is a central challenge in RL. Finding the optimal policy is the ultimate goal. It requires balancing exploration and exploitation. RL has its roots in optimal control theory and animal learning psychology. It has evolved into a powerful framework for solving complex decision-making problems in various domains, from game playing and robotics to resource management and personalized recommendations. RL is inspired by both engineering and biology. It has a rich history and diverse applications. Markov decision processes, a formal framework for sequential decision-making. To rigorously study and solve reinforcement learning problems, we need a formal mathematical framework. This section introduces Markov decision processes, MDPs, which provide a mathematical framework for modeling sequential decision-making problems under uncertainty. We will define the key components of an MDP, including states, actions, transition probabilities, and reward functions, and discuss the concepts of value functions and Bellman equations, which are central to understanding and solving MDPs. This provides a theoretical foundation for RL. An MDP is defined by a tuple, S, A, P, R, gamma, where S is a set of states, A is a set of actions, P is a state transition probability matrix, R is a reward function, and gamma is a discount factor. The state transition probability matrix specifies the probability of transitioning from one state to another after taking a particular action. The reward function assigns a numerical reward to each state or state-action pair. MDPs provide a formal model. They capture the essential elements of an RL problem. The discount factor, gamma, determines the present value of future rewards. A discount factor between 0 and 1 indicates that future rewards are worth less than immediate rewards. This reflects the fact that immediate rewards are often more certain and valuable than rewards that are received in the distant future. The discount factor balances short-term and long-term rewards. It influences the agent's behavior. A value function assigns a value to each state or state action pair, representing the expected cumulative reward that can be obtained from that state or state action pair onwards, following a particular policy. The value function can be used to evaluate the goodness of a policy and to guide the search for an optimal policy. Value functions are crucial for evaluating policies. They provide a measure of long-term value. The Bellman equation is a fundamental equation in RL that expresses the relationship between the value of a state and the values of its successor states. It provides a recursive decomposition of the value function, which can be used to compute the optimal value function and derive the optimal policy. The Bellman equation is a cornerstone of RL theory. It provides a way to solve for optimal values. Solving an MDP involves finding the optimal policy, which is a policy that maximizes the expected cumulative reward from any starting state. Various algorithms, such as value iteration and policy iteration, can be used to solve MDPs. These algorithms iteratively improve the value function and policy until they converge to the optimal solution. Solving MDPs leads to optimal decision-making. It is the core objective of many RL algorithms. Model-free reinforcement learning, Q-learning and SRSA. While MDPs provide a powerful framework for modeling RL problems, they require knowledge of the environment's transition probabilities and reward function, which may not be available in many real-world scenarios. This section explores model-free reinforcement learning algorithms, such as Q-learning and SRSA, which can learn optimal policies directly from experience without requiring a model of the environment. We will examine the mechanics of these algorithms, compare their on-policy and off-policy learning characteristics, and discuss their strengths and limitations. This enables learning without a model of the environment. Model-free RL algorithms learn directly from experience, by interacting with the environment and observing the resulting states and rewards. They do not require a model of the environment's dynamics, making them applicable to a wider range of problems. Model-free methods are more flexible. They can be applied when the environment is unknown. Q-learning is a popular off-policy model-free RL algorithm. It learns an action value function, Q, S, A, which estimates the expected cumulative reward for taking action A in state S and following the optimal policy thereafter. Q-learning updates the Q values iteratively, using the Bellman equation and the observed rewards and next states. Q-learning learns the optimal action value function. It is an off-policy algorithm. SRSA, State Action Reward State Action, is an on-policy model-free RL algorithm. Unlike Q-learning, which learns the value of the optimal policy, SRSA learns the value of the policy that the agent is currently following. SRSA updates the Q values based on the actual action taken in the next state, rather than the action that maximizes the Q value. SRSA learns the value of the current policy. It is an on-policy algorithm. Both Q-learning and SRSA have their strengths and weaknesses. Q-learning can learn the optimal policy even when following a suboptimal exploratory policy, but it can be more susceptible to overestimation bias. SRSA, on the other hand, is less prone to overestimation bias but may converge to a suboptimal policy if the exploration policy is poor. The choice between Q-learning and SRSA depends on the specific problem. They offer different trade-offs. Model-free RL algorithms have been successfully applied to various domains, including game playing, robotics, and control systems. They are particularly useful when the environment is complex or unknown, making it difficult to construct an accurate model. Model-free methods are versatile and powerful. They have demonstrated impressive results in various applications. Deep reinforcement learning, combining deep learning with reinforcement learning. The combination of deep learning with reinforcement learning, known as deep reinforcement learning, DRL, has led to significant breakthroughs in recent years. This section explores how deep neural networks can be used to approximate value functions or policies in complex, high-dimensional environments. We will examine key DRL algorithms, such as deep Q networks, DQN, and their extensions, and discuss their applications in challenging domains like game playing and robotics. We will also address the challenges and limitations of DRL, such as sample inefficiency and instability. This represents a powerful synergy between two fields. DRL leverages the power of deep neural networks to represent and learn complex value functions or policies. Deep networks can automatically learn hierarchical features from raw sensory input, such as pixels in an image or sensor readings from a robot, enabling DRL agents to operate in high-dimensional and complex environments. Deep learning enables end-to-end learning in RL. It allows for learning directly from raw inputs. Deep Q networks, DQN, were one of the first successful DRL algorithms. DQN uses a deep convolutional neural network to approximate the Q function, allowing it to learn to play Atari games directly from pixel inputs. DQN introduced several key innovations, such as experience replay and target networks, which helped to stabilize the learning process. DQN was a landmark achievement. It demonstrated the potential of DRL. Experience replay involves storing the agent's experiences in a memory buffer and sampling from this buffer during training. This breaks the temporal correlations between consecutive experiences and allows the agent to learn from a more diverse set of experiences. Target networks are used to provide a stable target for the Q value updates, reducing oscillations and improving convergence. These techniques improve stability and efficiency. They are crucial for training deep RL agents. Since the introduction of DQN, various extensions and improvements have been proposed, such as double DQN, dueling DQN, and prioritized experience replay. These extensions address issues such as overestimation bias, improve the learning of state values, and prioritize important experiences for more efficient learning. The field of DRL is constantly evolving. There are continuous improvements being made. DRL has achieved remarkable results in various domains, including game playing, where it has surpassed human-level performance in games like Go, chess, and many video games, and robotics, where it has been used to train robots to perform complex manipulation tasks. DRL has also shown promise in other areas, such as natural language processing and computer vision. It has demonstrated superhuman performance in some domains. It is a powerful tool for complex control tasks. Policy gradient methods, directly optimizing the policy while Q-learning and its variants focus on learning value functions. Policy gradient methods directly parameterize and optimize the policy. This section will explore the principles of policy gradient methods, including the reinforce algorithm and its extensions. We will examine how policy gradients can be used to learn stochastic policies and discuss the advantages and disadvantages of policy gradient methods compared to value-based methods. We will also explore advanced techniques such as actor-critic methods, which combine the strengths of both value-based and policy-based approaches. This offers a different approach to reinforcement learning. Policy gradient methods directly parameterize the policy, typically using a neural network, and optimize its parameters to maximize the expected cumulative reward. The policy is often represented as a probability distribution over actions, allowing for stochastic behavior. Policy gradient methods directly optimize the policy. They learn a mapping from states to actions. The reinforce algorithm is a fundamental policy gradient method. It uses Monte Carlo sampling to estimate the gradient of the expected cumulative reward with respect to the policy parameters and updates the policy parameters in the direction of the gradient. Reinforce is a simple and widely used algorithm. It is based on the policy gradient theorem. One of the challenges of policy gradient methods is the high variance of the gradient estimates, which can lead to unstable learning. Various techniques, such as using a baseline to reduce the variance and using trust region methods to constrain the policy updates, have been proposed to address this issue. Reducing variance is crucial for stable learning. It is an active area of research. Actor-critic methods combine the advantages of both value-based and policy-based methods. The actor represents the policy and is responsible for selecting actions, while the critic represents the value function and is used to evaluate the actions taken by the actor. The critic provides feedback to the actor, guiding its learning process. Actor-critic methods are more stable than pure policy gradient methods. They leverage the strengths of both approaches. Policy gradient methods have several advantages over value-based methods. They can handle continuous action spaces more naturally, and they can learn stochastic policies, which can be beneficial for exploration and for dealing with partially observable environments. However, they can also be less sample efficient than value-based methods. They have their own strengths and weaknesses. The choice depends on the specific problem. Inverse reinforcement learning, learning from expert demonstrations in many real-world scenarios, it can be difficult to specify a reward function that accurately captures the desired behavior of an agent. This section explores inverse reinforcement learning, IRL, a paradigm where the goal is to infer the reward function from expert demonstrations. We will examine different approaches to IRL, including feature-based methods and maximum entropy IRL, and discuss the challenges and limitations of learning from demonstrations. We will also explore applications of IRL in areas such as robotics and autonomous driving. This allows for learning from expert behavior. IRL aims to recover the underlying reward function that an expert is optimizing, given a set of demonstrations of the expert's behavior. This is in contrast to traditional RL, where the reward function is assumed to be known. IRL is useful when the reward function is difficult to specify manually. It allows for learning from observed behavior. One approach to IRL is to assume that the reward function can be expressed as a linear combination of known features. The goal is then to find the weights of these features that best explain the expert's behavior. This approach is relatively simple but may not be able to capture complex reward functions. Feature-based IRL is limited by the choice of features. It assumes a linear reward function. Maximum entropy IRL is another popular approach that aims to find the reward function that maximizes the entropy of the distribution over trajectories induced by the expert's policy, subject to matching feature expectations with the expert demonstrations. This approach can handle more complex reward functions and provides a probabilistic interpretation of the learned reward function. Maximum entropy IRL is more flexible. It can model a wider range of behaviors. IRL faces several challenges. The problem is often ill-posed, as multiple reward functions can explain the same expert behavior. Furthermore, IRL algorithms are typically sensitive to the quality and quantity of the expert demonstrations. Addressing these challenges requires careful consideration of the assumptions and limitations of different IRL methods. IRL is a challenging problem. It requires careful consideration of the expert demonstrations. IRL has found applications in various domains. In robotics, IRL can be used to learn control policies from expert demonstrations, enabling robots to acquire complex skills without explicit programming. In autonomous driving, IRL can be used to learn driving styles from human drivers, leading to more natural and human-like behavior in autonomous vehicles. It has many practical applications. It is a powerful tool for learning from demonstrations. Multi-agent reinforcement learning, learning in the presence of other agents. Many real-world scenarios involve multiple agents interacting with each other, either cooperatively or competitively. This section explores multi-agent reinforcement learning, MARL, where multiple agents learn simultaneously in a shared environment. We will examine the challenges that arise in MARL, such as the non-stationarity of the environment and the need for coordination and communication. We will also discuss different approaches to MARL, including independent learning, centralized learning, and decentralized learning, and explore applications in areas such as multi-robot systems, traffic control, and economics. This extends RL to multi-agent settings. In MARL, each agent learns its own policy while interacting with other agents in a shared environment. This introduces new challenges compared to single-agent RL, as the environment becomes non-stationary from the perspective of each agent due to the changing policies of the other agents. The presence of multiple agents adds complexity. It requires considering the interactions between agents. One approach to moral is independent learning, where each agent treats the other agents as part of the environment and learns its own policy independently. This approach is simple but can suffer from instability and may not lead to optimal joint policies, as agents may not be able to coordinate effectively. Independent learning is simple but may be suboptimal. It does not explicitly consider the actions of other agents. Centralized learning, on the other hand, involves learning a joint policy for all agents, typically by using a central controller that has access to the observations and actions of all agents. This approach can lead to optimal joint policies but may be computationally expensive and may not be feasible in decentralized settings where agents cannot communicate or share information. Centralized learning can be optimal but is often impractical. It requires a central controller. Decentralized learning aims to learn policies that can be executed independently by each agent while still achieving good joint performance. This often involves learning communication protocols or developing mechanisms for agents to share information or coordinate their actions. Decentralized learning is more realistic for many applications. It allows for autonomous decision-making. Moral has found applications in various domains, including multi-robot systems, where it can be used to coordinate the actions of multiple robots to achieve a common goal, traffic control, where it can be used to optimize traffic flow in a network of intersections, and economics, where it can be used to model the interactions of multiple economic agents. It has many practical applications. It is a powerful tool for modeling multi-agent systems. The ethical and societal implications of reinforcement learning. As reinforcement learning systems become more capable and autonomous, it is crucial to consider their ethical and societal implications. This section will explore the critical issues surrounding the responsible development and deployment of RL systems, including concerns about safety, accountability, value alignment, and the potential impact on decision-making and human autonomy. This encourages a thoughtful and responsible approach to RL development and deployment. One of the primary concerns is the safety of RL systems, particularly when they are deployed in safety-critical domains such as autonomous driving or medical diagnosis. Ensuring that RL agents behave safely and reliably in complex and unpredictable environments is a major challenge. Safety is paramount in real-world applications. It requires rigorous testing and verification. Accountability is another important issue. When an RL system makes a mistake or causes harm, it can be difficult to determine who is responsible. Is it the developer of the algorithm, the provider of the training data, or the user of the system? Establishing clear lines of accountability is crucial for building trust and ensuring responsible use of RL. Accountability is crucial for trust and responsibility. It is a complex issue in autonomous systems. Value alignment is the challenge of ensuring that the goals and values of RL systems are aligned with human values and societal norms. As RL agents become more autonomous and capable, it is essential to ensure that they are pursuing goals that are beneficial to humans and do not inadvertently cause harm. Value alignment is a fundamental challenge. It requires careful consideration of the goals and values embedded in RL systems. The increasing use of RL in decision-making processes raises concerns about the potential impact on human autonomy and agency. As RL systems become more sophisticated, they may be used to make decisions that were previously made by humans, potentially leading to a loss of human control and oversight. It is important to consider the appropriate balance between automation and human decision-making. Human autonomy must be preserved. We need to maintain meaningful human control. Addressing these ethical and societal challenges requires a multidisciplinary approach, involving not only technical solutions but also broader societal discussions about the values we want to embed in these systems and the kind of future we want to create with them. It requires collaboration between researchers, policymakers, ethicists, and the public. We must shape the future of RL responsibly. It is a collective responsibility. Future directions and emerging trends in reinforcement learning. The field of reinforcement learning is rapidly advancing, with researchers constantly developing new techniques and exploring new applications. This section will highlight some of the most promising future directions and emerging trends in RL, including the development of more sample-efficient and generalizable algorithms, the integration of RL with other areas of AI, and the use of RL to address pressing societal challenges. This provides a glimpse into the future of RL. One major research direction is the development of more sample-efficient RL algorithms. Current DRL algorithms often require a large amount of data or interaction with the environment to learn effective policies. Improving sample efficiency is crucial for applying RL to real-world problems where data collection is expensive or time-consuming. Sample efficiency is key for real-world applications. It is an active area of research. Another important trend is the development of more generalizable RL algorithms. Current RL systems are often specialized for specific tasks or environments. Researchers are working towards developing algorithms that can generalize to new, unseen environments and tasks, similar to how humans can adapt their knowledge and skills to new situations. Generalization is crucial for robust RL. It is a major challenge for the field. The integration of RL with other areas of AI, such as computer vision, natural language processing, and robotics, is a promising direction. This involves developing systems that can combine perception, reasoning, and decision-making in a unified framework, enabling more intelligent and autonomous agents. Integrating RL with other AI fields is essential. It leads to more capable and versatile systems. The use of RL to address pressing societal challenges, such as climate change, healthcare, and resource management, is a growing area of research. For example, RL can be used to optimize energy consumption in buildings, manage traffic flow in cities, or personalize medical treatments based on patient data. RL can have a positive impact on society. It can be used to address important challenges. Finally, the development of more robust, reliable, and interpretable RL systems is a key priority. This includes addressing issues such as safety, accountability, and value alignment, as discussed in the previous section. As RL systems become more integrated into our lives, it is essential to ensure that they are trustworthy and aligned with human values. Building trustworthy RL is crucial. It is essential for responsible deployment. The future of reinforcement learning is bright, with many exciting research directions and potential applications on the horizon. As you continue your journey in AI, you will have the opportunity to contribute to these advancements and shape the future of this dynamic field. The possibilities are vast. The future of RL is full of potential. Lesson 8, Robotics and Embodied AI, Bridging the Gap Between Intelligent Agents and the Physical World. Welcome back, inquisitive learners, to the 8th lesson in our advanced exploration of artificial intelligence. In this lesson, we venture into the captivating realm of robotics and embodied AI, where intelligent agents are no longer confined to the digital realm but are brought to life in physical form, capable of interacting with and manipulating the real world. We will explore the fundamental concepts of robotics, including perception, actuation, and control, and examine how AI techniques, such as computer vision, reinforcement learning, and planning, are enabling the development of increasingly sophisticated and autonomous robots. We will also discuss the challenges and opportunities of embodied AI, and consider the ethical implications of creating intelligent machines that can act in and impact the physical environment. Prepare to bridge the gap between the digital and physical worlds and discover how AI is transforming robotics, creating machines that can perceive, reason, act, and learn in complex and dynamic environments. The essence of robotics, embodying intelligence in the physical world. Robotics is the interdisciplinary field that deals with the design, construction, operation, and application of robots. This section will explore the core concepts of robotics, highlighting its connection to AI and the unique challenges of creating embodied intelligent agents. We will also discuss the key components of a robotic system, including sensors, actuators, and control systems, and examine the different types of robots and their applications. This provides a foundational understanding of robotics. At its core, robotics is about creating machines that can interact with the physical world in a purposeful and autonomous way. This involves not just programming a set of instructions but also enabling the robot to perceive its environment, make decisions based on its perceptions, and act on those decisions to achieve its goals. Robotics combines engineering and AI. It is about creating intelligent physical agents. Embodied AI is a branch of AI that emphasizes the importance of the body in shaping intelligence. It argues that intelligence cannot be understood solely in terms of abstract computation but must be grounded in the interactions between an agent and its physical environment. Embodied AI is crucial for robotics. It highlights the importance of physical interaction. A typical robotic system consists of several key components. Sensors, such as cameras, LiDAR, and tactile sensors, allow the robot to perceive its environment. Actuators, such as motors and grippers, enable the robot to move and manipulate objects. The control system, which often incorporates AI algorithms, processes sensor data, makes decisions, and generates commands for the actuators. These components work together. They enable the robot to interact with the world. Robots come in various forms, from industrial robots that perform repetitive tasks in factories to mobile robots that can navigate complex environments, to humanoid robots that are designed to interact with humans. Each type of robot presents unique challenges and requires different approaches to perception, control, and decision-making. Robots are diverse and specialized. They are designed for specific tasks and environments. Robotics has a wide range of applications, including manufacturing, logistics, healthcare, agriculture, and exploration. As AI techniques continue to advance, robots are becoming increasingly autonomous and capable of performing complex tasks in unstructured environments. Robotics is transforming many industries. It is enabling new levels of automation and efficiency. Perception for robotics, enabling robots to see, hear, and feel. Perception is a crucial capability for robots, enabling them to gather information about their environment and make informed decisions. This section will explore the various perception modalities used in robotics, including vision, LiDAR, and tactile sensing. We will examine how AI techniques, such as computer vision and deep learning, are used to process sensor data and extract meaningful information about the robot's surroundings. We will also discuss the challenges of robust and reliable perception in real-world environments. This enables robots to understand their surroundings. Vision is a primary sense for many robots, allowing them to perceive the visual appearance of objects, recognize places, and navigate their environment. Computer vision techniques, such as object detection, image segmentation, and depth estimation, are used to process images from cameras and extract relevant information. Vision provides rich information about the environment. It is a key modality for many robots. Deep learning has significantly advanced the capabilities of visual perception for robots. Convolutional neural networks, CNNs, can be trained to recognize objects, estimate their pose, and segment images with high accuracy. Transfer learning, where models pre-trained on large image datasets are fine-tuned for specific robotic tasks, has also proven to be highly effective. Deep learning has revolutionized robotic vision. It has enabled significant improvements in accuracy and robustness. LiDAR, light detection and ranging, is another important sensor modality for robots, particularly for mobile robots and autonomous vehicles. LiDAR sensors use laser pulses to measure the distance to objects, creating a 3D point cloud representation of the environment. This information can be used for mapping, localization, obstacle avoidance, and object recognition. LiDAR provides accurate depth information. It is crucial for navigation and mapping. Tactile sensing, which involves using sensors to detect physical contact and pressure, is crucial for enabling robots to interact with objects and manipulate them effectively. Tactile sensors can provide information about the shape, texture, and stiffness of objects, as well as the forces being applied during manipulation. Tactile sensing is essential for manipulation. It enables robots to interact with objects safely and effectively. Perception in real-world environments presents many challenges. Robots must be able to handle variations in lighting, weather, and viewpoint, as well as occlusions and noise in the sensor data. Robust and reliable perception requires the integration of multiple sensor modalities and the use of sophisticated algorithms that can handle uncertainty and ambiguity. Perception must be robust and reliable. It is a challenging problem in real-world settings. Robotic actuation and control, moving and manipulating in the physical world, while perception provides robots with information about their environment. Actuation and control enable them to move and interact with the physical world. This section will explore the different types of actuators used in robotics, such as motors, hydraulic systems, and pneumatic systems, and discuss the principles of robotic control, including low-level control, trajectory planning, and task-level planning. We will also examine how AI techniques, such as reinforcement learning, are being used to develop more adaptive and intelligent control systems for robots. This enables robots to act upon their environment. Actuators are the devices that generate motion and forces in a robot. Electric motors are commonly used for precise and controlled movements, while hydraulic and pneumatic systems are often used for applications that require high forces or speeds. The choice of actuator depends on the specific application and the robot's design requirements. Actuators are the muscles of a robot. They enable physical interaction. Low-level control involves controlling the individual actuators to achieve desired movements or forces. This often involves using feedback control techniques, such as PID control, to ensure that the robot's movements are accurate and stable. Low-level control is essential for precise movement. It requires careful tuning and calibration. Trajectory planning involves generating a sequence of motions that will move the robot from a starting position to a goal position while avoiding obstacles and satisfying other constraints. Various algorithms, such as rapidly exploring random trees, RRTs, and probabilistic roadmaps, PRMs, are used for trajectory planning. Trajectory planning is crucial for efficient and safe movement. It requires considering the robot's dynamics and the environment. Task-level planning involves deciding on a sequence of high-level actions to achieve a specific goal, such as assembling a product or navigating to a destination. This often requires reasoning about the effects of actions and planning under uncertainty. AI techniques, such as automated planning and scheduling, are used for task-level planning. Task-level planning enables complex behavior. It requires higher-level reasoning. Reinforcement learning, RL, is increasingly being used to develop more adaptive and intelligent control systems for robots. RL allows robots to learn optimal control policies through trial and error, by interacting with their environment and receiving rewards. Deep reinforcement learning, in particular, has shown promise in learning complex control policies directly from raw sensory inputs. RL enables robots to learn from experience. It can lead to more robust and adaptable control. Robotic manipulation and grasping, interacting with objects. The ability to manipulate objects is a crucial capability for many robots, enabling them to perform tasks such as assembly, packaging, and assisting humans in various settings. This section will explore the challenges of robotic manipulation and grasping, including object perception, grasp planning, and control. We will examine how AI techniques, such as computer vision and reinforcement learning, are being used to develop more robust and versatile manipulation skills for robots. We will also discuss the different types of grippers and end effectors used in robotic manipulation. This enables robots to physically interact with objects. Robotic manipulation involves using a robotic arm and hand, or end effector, to interact with and manipulate objects in the environment. This requires the ability to perceive the object's shape, pose, and physical properties, plan a suitable grasp and trajectory, and control the robot's movements to execute the manipulation task. Manipulation is a complex task. It requires coordination of perception, planning, and control. Object perception for manipulation often involves using computer vision techniques to estimate the object's pose, shape, and other properties from visual input. This information is then used to plan a suitable grasp. Deep learning has shown promise in learning robust object representations for manipulation. Accurate object perception is crucial for successful manipulation. It provides the necessary information for planning. Grasp planning involves determining how to grasp an object with the robot's gripper or hand. This requires considering the object's shape, the gripper's capabilities, and the desired stability of the grasp. Various algorithms, such as force closure analysis and data-driven grasp planning, are used to generate and evaluate potential grasps. Grasp planning is a challenging problem. It requires considering both geometry and physics. Controlling the robot's movements during manipulation is also a complex task. The robot must be able to execute precise movements while avoiding collisions and maintaining a stable grasp on the object. Techniques such as impedance control and force/torque control are used to ensure smooth and compliant interactions with the environment. Control is essential for safe and effective manipulation. It requires careful consideration of forces and dynamics. Different types of grippers and end effectors are used for robotic manipulation, depending on the specific application. Parallel jaw grippers are commonly used for simple pick-and-place tasks, while multi-fingered hands offer greater dexterity for more complex manipulation tasks. Specialized end effectors can also be designed for specific tasks, such as grasping soft or irregularly shaped objects. The choice of gripper depends on the task. It affects the robot's manipulation capabilities. Mobile robotics, navigating and exploring the world. Mobile robots, unlike their stationary counterparts, have the ability to move around in their environment, enabling them to perform tasks such as exploration, mapping, transportation, and delivery. This section will explore the challenges of mobile robotics, including localization, mapping, navigation, and path planning. We will examine how AI techniques, such as simultaneous localization and mapping, SLAM, and reinforcement learning, are being used to develop more autonomous and adaptable mobile robots. We will also discuss different types of mobile robot platforms and their applications. This enables robots to move and operate in complex environments. Localization is the problem of determining the robot's position and orientation within its environment. This is a fundamental capability for mobile robots, as it allows them to navigate and perform tasks in a specific location. Various techniques, such as GPS, odometry, and visual localization, are used for localization. Localization is essential for navigation. It requires accurate and robust estimation of the robot's pose. Mapping is the process of creating a representation of the environment, typically in the form of a map. This map can be used for navigation, planning, and other tasks. Simultaneous localization and mapping, SLAM, is a technique that allows a robot to simultaneously build a map of its environment while localizing itself within that map. SLAM is a challenging problem. It requires solving for both the robot's pose and the map structure. Navigation involves moving the robot from one location to another while avoiding obstacles and following a desired path. Path planning algorithms, such as A** and Dijkstra's algorithm, are used to generate a collision-free path from the robot's current location to a goal location. Navigation also requires the ability to react to unexpected obstacles or changes in the environment. Navigation is a core capability for mobile robots. It requires planning and execution of motion. Reinforcement learning is increasingly being used to develop more adaptive and intelligent navigation strategies for mobile robots. RL allows robots to learn optimal navigation policies through trial and error, by interacting with their environment and receiving rewards for reaching their goals. Deep reinforcement learning, in particular, has shown promise in learning complex navigation behaviors directly from raw sensory inputs. RL enables robots to learn from experience. It can lead to more robust and adaptable navigation. Different types of mobile robot platforms are used for different applications. Wheeled robots are commonly used for indoor environments, while legged robots are better suited for rough terrain. Unmanned aerial vehicles, UAVs, or drones, are used for aerial surveillance, mapping, and delivery. Autonomous underwater vehicles, AUVs, are used for ocean exploration and monitoring. The choice of platform depends on the environment and task. It affects the robot's mobility and capabilities. Human-robot interaction, collaborating with intelligent machines as robots become more integrated into human environments, the ability for humans to interact with them naturally and intuitively becomes increasingly important. This section will explore the field of human-robot interaction, HRI, examining how AI techniques are being used to develop robots that can understand and respond to human communication, interpret human intentions, and collaborate effectively with humans in shared tasks. We will also discuss the challenges of designing robots that are socially intelligent and can adapt to different human users and contexts. This enables seamless collaboration between humans and robots. HRI aims to develop principles and techniques for designing robots that can interact with humans in a natural, intuitive, and effective manner. This involves not only understanding the technical aspects of robot design but also considering the social, cognitive, and psychological factors that influence human-robot interaction. HRI is a multidisciplinary field. It requires understanding both humans and robots. One important aspect of HRI is enabling robots to understand and respond to human communication, including speech, gestures, and facial expressions. Natural language processing, NLP, computer vision, and machine learning techniques are used to enable robots to interpret human language and nonverbal cues. Understanding human communication is crucial for HRI. It allows for natural and intuitive interaction. Another key aspect of HRI is enabling robots to understand and respond to human intentions and goals. This often involves using techniques such as plan recognition and inverse reinforcement learning to infer the underlying goals and intentions behind human actions. Understanding human intentions enables proactive behavior. It allows robots to anticipate human needs. Socially intelligent robots are designed to interact with humans in a socially appropriate and engaging manner. This involves considering factors such as social norms, etiquette, and emotional intelligence. Developing robots that can understand and respond to human emotions is an active area of research. Social intelligence is important for acceptance and trust. It enables more natural and engaging interactions. HRI presents many challenges. Designing robots that can adapt to different human users, contexts, and cultures is a difficult problem. Ensuring the safety and security of human-robot interactions is also crucial, particularly in collaborative settings where humans and robots share a physical workspace. Addressing these challenges requires careful design and evaluation. It requires considering the broader social context of HRI. Ethical considerations in robotics and embodied AI. The development and deployment of increasingly autonomous and intelligent robots raise important ethical considerations. This section will explore the critical issues surrounding the responsible development and use of robotics and embodied AI, including concerns about safety, job displacement, autonomy, and the potential impact on human relationships and society. This encourages a thoughtful and responsible approach to robotics development. One of the primary concerns is the safety of robots, particularly those that operate in close proximity to humans. Ensuring that robots do not harm humans, either through malfunction or unintended behavior, is a crucial consideration in robot design and deployment. Safety must be a top priority. It requires rigorous testing and validation. The potential impact of robotics on employment is another important issue. As robots become more capable of performing tasks that were previously done by humans, there are concerns about job displacement in certain sectors. It is important to consider strategies for mitigating these potential negative impacts, such as investing in education and retraining programs. The future of work must be considered. We need to adapt to these changes. The increasing autonomy of robots raises questions about responsibility and accountability. If a robot makes a mistake or causes harm, who is responsible? Is it the manufacturer, the owner, or the robot itself? Establishing clear legal and ethical frameworks for addressing these issues is crucial. Accountability is a complex issue in robotics. It requires careful consideration of legal and ethical implications. The potential impact of robots on human relationships and society is also a topic of debate. Some researchers have raised concerns about the potential for humans to form emotional attachments to robots, particularly social robots designed to interact with humans in a personal way. It is important to consider the potential psychological and social impacts of these technologies. The impact on human relationships must be considered. We need to understand the potential long-term effects. Addressing these ethical challenges requires a multidisciplinary approach, involving not only technical solutions but also broader societal discussions about the values we want to embed in these systems and the kind of future we want to create with them. It requires collaboration between researchers, policymakers, ethicists, and the public. We must shape the future of robotics responsibly. It is a collective responsibility. Future directions and emerging trends in robotics and embodied AI. The field of robotics is rapidly advancing, with new technologies and applications emerging at an accelerating pace. This section will explore some of the most promising future directions and emerging trends in robotics and embodied AI, including the development of more robust and adaptable robots, the integration of AI with other emerging technologies, and the use of robotics to address pressing societal challenges. This provides a glimpse into the future of robotics. One major trend is the development of more robust and adaptable robots that can operate in unstructured and dynamic environments. This involves improving the perception, planning, and control capabilities of robots, as well as developing new materials and actuation systems that are more resilient and versatile. Robustness and adaptability are key for real-world applications. They enable robots to operate in complex and unpredictable environments. The integration of AI with other emerging technologies, such as the Internet of Things, IoT, cloud computing, and 5G, is another important trend. This convergence will enable the development of distributed robotic systems that can communicate and collaborate with each other, share data and computational resources, and adapt to changing conditions in real time. The integration of AI with other technologies is transformative. It enables new levels of connectivity and intelligence. The use of robotics to address pressing societal challenges, such as aging populations, healthcare, and environmental monitoring, is a growing area of research and development. For example, assistive robots can help elderly people live more independently, while surgical robots can enable less invasive and more precise medical procedures. Robots can also be used to monitor and protect the environment, such as by detecting pollution or tracking wildlife. Robotics can have a positive impact on society. It can be used to address important challenges. The development of more human-like robots, both in terms of physical appearance and cognitive abilities, is another long-term goal of robotics research. This involves not only advances in AI and robotics but also a deeper understanding of human intelligence, social interaction, and the human body. Creating human-like robots is a grand challenge. It requires interdisciplinary research and innovation. Finally, the increasing availability of open-source hardware and software platforms for robotics is democratizing the field, making it easier for researchers, hobbyists, and entrepreneurs to develop and deploy new robotic applications. This trend is likely to accelerate innovation in robotics and lead to a wider range of applications and use cases. Open-source robotics is fostering innovation. It is making robotics more accessible. The future of robotics and embodied AI is bright, with many exciting research directions and potential applications on the horizon. As you continue your journey in AI, you will have the opportunity to contribute to these advancements and shape the future of this dynamic field, creating intelligent machines that can interact with and improve the world around us. The possibilities are vast. The future of robotics is full of potential. Lesson 9, AI Safety and Ethics, Navigating the Complex Landscape of Responsible AI Development. Welcome back, conscientious learners, to the 9th lesson in our advanced exploration of artificial intelligence. As AI systems become increasingly powerful, pervasive, and integrated into our lives, it is imperative to address the ethical and safety challenges that arise from their development and deployment. In this lesson, we will navigate the complex landscape of AI safety and ethics, examining the potential risks and harms associated with advanced AI, exploring frameworks for responsible AI development, and discussing the critical issues of bias, fairness, transparency, accountability, and value alignment. We will also consider the broader societal implications of AI and the role of researchers, policymakers, and citizens in shaping a future where AI benefits all of humanity. Prepare to engage with the ethical dimensions of AI and develop a nuanced understanding of the challenges and opportunities that lie ahead as we strive to create AI systems that are not only intelligent but also safe, ethical, and aligned with human values. The imperative of AI safety, addressing the risks of advanced AI's AI systems become more sophisticated and autonomous, ensuring their safety and robustness becomes increasingly critical. This section will explore the concept of AI safety, highlighting the unique challenges of building safe and reliable AI systems, particularly in the context of advanced AI that may exhibit unpredictable or unintended behavior. We will also discuss different approaches to AI safety, including formal verification, robustness testing, and anomaly detection, and examine the importance of a proactive and precautionary approach to AI development. This establishes the importance of safety in AI. AI safety is a multidisciplinary field that aims to ensure that AI systems are designed, developed, and deployed in a way that minimizes risks and maximizes benefits to humanity. Unlike traditional software safety, which often deals with well-defined systems and known failure modes, AI safety must address the challenges of complex, adaptive, and potentially unpredictable systems that may operate in open-ended environments. AI safety is a unique and evolving challenge. It requires new approaches and ways of thinking. One of the key challenges in AI safety is the potential for unintended behavior. As AI systems become more autonomous and capable of learning and adapting, they may exhibit behaviors that were not anticipated by their developers. This can be particularly problematic in safety-critical applications, such as autonomous driving or medical diagnosis, where errors can have serious consequences. Unintended behavior can arise from various sources. It is a major concern in safety-critical domains. Another challenge is the difficulty of specifying and verifying the desired behavior of complex AI systems. Traditional software engineering relies on formal specifications and verification techniques to ensure that systems meet their requirements. However, these techniques are often difficult to apply to AI systems, particularly those based on deep learning, due to their complexity and opacity. Specifying and verifying AI behavior is challenging. It requires new methods for complex systems. Robustness testing and anomaly detection are important techniques for improving AI safety. Robustness testing involves evaluating the performance of AI systems under a wide range of conditions, including adversarial inputs and unexpected perturbations. Anomaly detection aims to identify unusual or unexpected behavior that may indicate a safety issue. These techniques can help to identify vulnerabilities. They can improve the resilience of AI systems. A proactive and precautionary approach to AI development is essential for ensuring safety. This involves anticipating potential risks and harms early in the design process, incorporating safety considerations into the development lifecycle, and continuously monitoring and evaluating the safety of deployed systems. Safety must be a priority from the outset. It should be integrated throughout the development process. Ethical frameworks for AI, guiding principles for responsible development. In addition to safety, the ethical implications of AI must be carefully considered throughout the development and deployment lifecycle. This section will explore various ethical frameworks that have been proposed to guide the responsible development of AI, including principle-based approaches, rights-based approaches, and virtue ethics. We will examine how these frameworks can help to identify and address ethical challenges in AI, such as bias, fairness, transparency, and accountability, and discuss the importance of stakeholder engagement and public deliberation in shaping ethical AI. This provides a foundation for ethical decision-making in AI. Principle-based approaches to AI ethics typically involve defining a set of high-level principles that should guide the development and use of AI systems. For example, the principles of beneficence, doing good, non-maleficence, avoiding harm, autonomy, respecting individual freedom, and justice, promoting fairness and equity, have been proposed as core ethical principles for AI. Principle-based approaches provide a high-level framework. They can guide ethical reflection and decision-making. Rights-based approaches emphasize the importance of protecting fundamental human rights in the development and deployment of AI systems. This includes rights such as the right to privacy, the right to non-discrimination, and the right to due process. Rights-based approaches often involve translating existing human rights frameworks into the context of AI, identifying potential threats to these rights, and developing safeguards to protect them. Rights-based approaches focus on human rights. They provide a strong ethical foundation. Virtue ethics, drawing on the Aristotelian tradition, focuses on cultivating virtuous character traits in AI developers and designers, such as responsibility, integrity, and humility. This approach emphasizes the importance of ethical education and training for AI practitioners and the need to foster a culture of ethical awareness and reflection within the AI community. Virtue ethics emphasizes the role of character. It promotes ethical conduct from within. Stakeholder engagement and public deliberation are crucial for developing ethical AI. This involves engaging with a wide range of stakeholders, including researchers, developers, users, policymakers, and the public, to understand their concerns, values, and expectations regarding AI. Public deliberation can help to ensure that AI systems reflect societal values and priorities. Stakeholder engagement is essential for ethical AI. It ensures that diverse perspectives are considered. Ethical frameworks for AI provide valuable tools for navigating the complex ethical landscape of AI development. However, they are not a panacea and must be complemented by concrete technical solutions, regulatory frameworks, and ongoing critical reflection and dialogue. Ethical frameworks are a starting point. They must be combined with action and ongoing dialogue. Bias and fairness in AI, addressing unintended discrimination. One of the most pressing ethical concerns in AI is the potential for bias and discrimination. This section will explore the different sources of bias in AI systems, including data bias, algorithmic bias, and interaction bias, and examine how these biases can lead to unfair or discriminatory outcomes. We will also discuss various approaches to detecting, mitigating, and preventing bias in AI, including technical solutions, such as fairness-aware algorithms and data augmentation, as well as broader strategies for promoting diversity and inclusion in the AI workforce. This addresses a critical challenge in AI ethics. Bias in AI systems can arise from various sources. Data bias occurs when the training data used to develop an AI system is not representative of the population or context in which the system will be deployed. For example, if a facial recognition system is trained primarily on images of white faces, it may perform poorly on individuals with darker skin tones. Data bias can lead to discriminatory outcomes. It reflects and amplifies existing societal biases. Algorithmic bias refers to biases that are introduced by the design of the algorithm itself, even if the training data is unbiased. This can occur when the algorithm makes assumptions or incorporates criteria that implicitly favor certain groups over others. For example, an algorithm used for loan applications may inadvertently discriminate against certain demographic groups if it relies on factors that are correlated with those groups. Algorithmic bias can be subtle and difficult to detect. It requires careful scrutiny of the algorithm's design. Interaction bias arises from the way that users interact with an AI system. For example, if users of a search engine predominantly click on results that reinforce their existing biases, the search engine may learn to prioritize those results, creating a feedback loop that amplifies the bias. Interaction bias can be difficult to address. It requires considering the dynamics between users and AI systems. Detecting and mitigating bias in AI requires a multifaceted approach. Technical solutions include developing fairness-aware algorithms that explicitly incorporate fairness constraints into the learning process, using data augmentation techniques to balance biased datasets, and auditing AI systems for bias using various statistical measures. Technical solutions are important but not sufficient. They must be combined with broader strategies. Promoting diversity and inclusion in the AI workforce is also crucial for addressing bias. A diverse team of AI developers is more likely to identify and challenge assumptions that can lead to bias and to develop AI systems that are more inclusive and equitable. Diversity and inclusion are essential. They bring different perspectives and experiences to AI development. Transparency and explainability in AI, opening the black box's AI systems, particularly those based on deep learning, become increasingly complex. Understanding their decision-making processes can be challenging. This section will explore the importance of transparency and explainability in AI, examining how the opacity of complex AI models can create challenges for trust, accountability, and debugging. We will discuss various approaches to explainable AI, XAI, including model-agnostic methods, such as LIME and SHAP, and model-specific methods, such as attention mechanisms, and consider the trade-offs between explainability and accuracy. This promotes trust and understanding in AI systems. Transparency in AI refers to the ability to understand and explain how an AI system works and how it arrives at its decisions. This can be challenging for complex models, such as deep neural networks, which often operate as black boxes, with their internal workings opaque to human scrutiny. The lack of transparency can erode trust in AI systems. It can make it difficult to identify and correct errors. Explainability is a related concept that focuses on providing understandable explanations for the decisions made by AI systems. Explainable AI, XAI, aims to develop techniques that can provide insights into the factors that influence a model's output, making it easier for humans to understand and interpret the model's behavior. Explainability is crucial for accountability and debugging. It helps users understand why a decision was made. Model-agnostic XAI methods, such as LIME, local interpretable model-agnostic explanations, and SHAP, Shapley additive explanations, aim to provide explanations for the predictions of any machine learning model, regardless of its internal structure. These methods typically work by perturbing the input to the model and observing the changes in the output, allowing them to estimate the contribution of different input features to the prediction. Model-agnostic methods are versatile and widely applicable. They provide local explanations for individual predictions. Model-specific XAI methods are tailored to specific types of models, such as deep neural networks. For example, attention mechanisms, which are used in many state-of-the-art NLP and computer vision models, can provide insights into which parts of the input the model is focusing on when making a prediction. Visualization techniques can also be used to help understand the internal representations learned by deep networks. Model-specific methods can provide deeper insights. They are tailored to the specific architecture of the model. There is often a trade-off between explainability and accuracy. Simpler, more interpretable models, such as linear regression or decision trees, may be easier to understand but may not be as accurate as more complex models, such as deep neural networks. Finding the right balance between explainability and accuracy depends on the specific application and the needs of the users. The trade-off between explainability and accuracy is a key consideration. It depends on the specific context and requirements. Accountability and liability in AI, assigning responsibility for AI actions as AI systems become more autonomous and make decisions with real-world consequences. Questions of accountability and liability become increasingly important. This section will explore the challenges of assigning responsibility for the actions of AI systems, considering the roles of developers, users, and the systems themselves. We will examine different legal and ethical frameworks for addressing AI accountability and discuss the need for clear guidelines and regulations to ensure responsible development and deployment of AI. This addresses a critical issue in the age of autonomous systems. Determining accountability for the actions of AI systems is a complex issue. Unlike traditional software, which follows explicit instructions, AI systems, particularly those based on machine learning, can exhibit emergent behavior that is not directly programmed by their developers. This can make it difficult to trace the cause of an error or to assign responsibility for a harmful outcome. The autonomy of AI systems complicates accountability. It raises new legal and ethical questions. One approach to addressing accountability is to focus on the developers of AI systems. This could involve establishing standards of care for AI development, similar to those in other engineering disciplines, and holding developers liable for negligence or defects in their systems. However, this approach may be difficult to implement in practice, given the complexity and opacity of many AI systems. Developer liability is one approach. It requires clear standards and practices. Another approach is to focus on the users or operators of AI systems. This could involve requiring users to undergo training or certification, or establishing clear guidelines for the appropriate use of AI systems. However, this approach may not be feasible for all types of AI systems, particularly those that are designed to operate autonomously. User responsibility is important but may be limited. It depends on the level of user control. Some researchers have proposed the idea of granting legal personhood to AI systems themselves, which would allow them to be held directly accountable for their actions. However, this approach raises many philosophical and practical questions, such as how to determine the appropriate level of responsibility and how to enforce penalties against non-human entities. AI personhood is a controversial idea. It has far-reaching implications. Establishing clear legal and ethical frameworks for AI accountability is crucial for ensuring the responsible development and deployment of these technologies. This may involve updating existing laws and regulations to address the unique challenges posed by AI, as well as developing new mechanisms for assigning responsibility and resolving disputes. Clear guidelines and regulations are needed. They must address the unique aspects of AI. Value alignment in AI, ensuring AI systems share human values. As AI systems become more capable of pursuing goals and making decisions, it becomes increasingly important to ensure that their goals and values are aligned with those of humans. This section will explore the challenge of value alignment in AI, examining how misaligned goals or values can lead to unintended and potentially harmful consequences. We will discuss different approaches to value alignment, including explicit value encoding, inverse reinforcement learning, and preference learning, and consider the long-term implications of creating AI systems whose values may differ from our own. This addresses a fundamental challenge in AI development. Value alignment is the problem of ensuring that AI systems have goals, values, and behaviors that are aligned with human values and societal norms. This is a crucial consideration for the long-term safety and beneficial development of AI. Misaligned AI systems, even if unintentionally so, could pursue goals that are harmful to humans or that conflict with our values. Value alignment is essential for beneficial AI. It is a complex and multifaceted problem. One approach to value alignment is to explicitly encode human values into AI systems, either by programming them directly or by creating systems that can learn values from human input. However, this approach faces challenges, as human values are often complex, context-dependent, and difficult to articulate in a formal way. Explicit value encoding is challenging. It requires a deep understanding of human values. Inverse reinforcement learning, IRL, offers an alternative approach, where an AI system learns a reward function by observing the behavior of a human expert. The assumption is that the expert's behavior reflects their underlying values, and by learning the reward function that best explains this behavior, the AI system can infer those values. IRL can learn values from demonstrations. It is a promising approach to value alignment. Preference learning is another approach that involves learning from human preferences expressed over different outcomes or trajectories. By eliciting preferences from humans, either through explicit queries or by observing their choices, an AI system can learn a model of human values that can guide its decision-making. Preference learning leverages human judgments. It can capture more nuanced value structures. The long-term implications of value alignment are profound. As we create more advanced AI systems, ensuring that they share our values and goals will be crucial for ensuring that they remain beneficial to humanity. This requires not only technical solutions but also a broader societal conversation about what values we want to embed in these systems. Value alignment is a long-term challenge. It has significant implications for the future of AI. The societal impact of AI, transforming industries and reshaping society. The impact of AI extends far beyond the technical realm, with the potential to transform industries, reshape labor markets, and alter the fabric of society. This section will examine the broader societal implications of AI, considering its impact on employment, the economy, and social structures. We will also discuss the potential for AI to exacerbate existing inequalities or create new ones, and explore the need for policies and social adaptations to ensure that the benefits of AI are broadly shared. This examines the transformative potential of AI. AI is already having a significant impact on various industries, from manufacturing and logistics to healthcare and finance. Automation driven by AI and robotics is increasing productivity, improving efficiency, and enabling new products and services. However, it is also leading to concerns about job displacement and the need for workforce retraining and adaptation. AI is transforming industries. It has both positive and negative impacts on employment. The impact of AI on the economy is likely to be profound. Some studies predict that AI could add trillions of dollars to global GDP in the coming decades, driven by productivity gains and new innovations. However, the benefits of this growth may not be evenly distributed, potentially widening the gap between the rich and the poor. The economic impact of AI is significant. It requires careful management to ensure equitable outcomes. AI also has the potential to reshape social structures and institutions. For example, the use of AI in education could personalize learning experiences and improve educational outcomes, but it could also exacerbate existing inequalities if access to these technologies is not evenly distributed. Similarly, the use of AI in healthcare could improve diagnosis and treatment, but it could also raise concerns about privacy and access to care. AI can reshape social structures. It has both opportunities and challenges. Addressing the societal impact of AI requires proactive policies and social adaptations. This includes investing in education and retraining programs to help workers adapt to the changing demands of the labor market, considering new social safety nets to support those displaced by automation, and ensuring that the benefits of AI are broadly shared across society. Proactive policies are needed. They can help to mitigate negative impacts and promote equitable outcomes. The development and deployment of AI should be guided by ethical principles and a commitment to promoting human well-being. This requires ongoing dialogue and collaboration between researchers, policymakers, industry leaders, and the public to ensure that AI is developed and used in a way that aligns with human values and societal goals. Responsible AI development is a collective effort. It requires broad engagement and collaboration. The future of AI, towards artificial general intelligence and beyond. While most current AI research focuses on narrow AI, which excels at specific tasks. The long-term aspiration of many researchers is to develop artificial general intelligence, AGI, systems that possess human-level or even superhuman general intelligence. This section will explore the concept of AGI, discussing the potential pathways to its development, the challenges involved, and the profound implications it could have for humanity. We will also consider the potential risks and benefits of AGI and discuss the importance of foresight and responsible innovation in guiding its development. This explores the long-term aspirations and challenges of AI research. AGI is often defined as an AI system that can perform any intellectual task that a human being can, including learning, reasoning, problem-solving, and interacting with the world. Some researchers also envision superintelligence, which refers to systems that surpass human intelligence in all or most domains. AGI is a long-term goal of AI research. It represents a fundamental shift from narrow AI. The development of AGI, if achievable, could have transformative consequences for humanity. It could lead to unprecedented scientific breakthroughs, economic growth, and solutions to some of the world's most pressing problems. However, it could also pose existential risks if not developed and managed responsibly. AGI has the potential for both immense benefit and risk. It requires careful consideration of its potential impacts. One potential pathway to AGI is to continue advancing the state-of-the-art in deep learning and other current AI techniques, gradually expanding their capabilities and generality. Another approach is to focus on developing more integrated AI architectures that combine different AI techniques, such as perception, reasoning, and learning, into a unified system. There are different approaches to achieving AGI. Each has its own challenges and potential. The challenges of developing AGI are immense. They include not only technical challenges, such as developing algorithms for general-purpose learning and reasoning, but also conceptual challenges, such as understanding the nature of consciousness and intelligence itself. Developing AGI requires fundamental breakthroughs. It is a problem of unprecedented complexity. The potential risks of AGI, particularly superintelligence, have been the subject of much debate and speculation. Some researchers have warned that an uncontrolled superintelligence could pose an existential threat to humanity, either through intentional malevolence or through the pursuit of goals that are misaligned with human values. The risks of AGI must be taken seriously. They require careful consideration and proactive measures. Ensuring that AGI, if developed, is beneficial to humanity requires a concerted effort from researchers, policymakers, and the public. This includes research on value alignment, AI safety, and the ethical and societal implications of AGI, as well as the development of appropriate governance structures and international cooperation. The development of beneficial AGI is a global challenge. It requires international collaboration and foresight. The future of AI holds both immense promise and significant challenges. As we continue to advance the capabilities of AI systems, it is crucial to engage in a thoughtful and informed dialogue about the kind of future we want to create with these technologies. By combining technical expertise with ethical wisdom, we can strive to ensure that AI remains a powerful tool for human flourishing. The future of AI is in our hands. We must shape it responsibly and wisely. Lesson 10: AI in Healthcare and Medicine, Transforming Diagnosis, Treatment, and Patient Care. Welcome back, dedicated learners, to the 10th lesson in our advanced exploration of artificial intelligence. In this lesson, we delve into the transformative applications of AI in healthcare and medicine, a field where AI is poised to revolutionize the way we diagnose diseases, develop treatments, and deliver patient care. We will explore how AI techniques, such as machine learning, computer vision, and natural language processing, are being used to analyze medical images, predict patient outcomes, personalize treatments, and automate administrative tasks. We will also examine the challenges and ethical considerations associated with deploying AI in healthcare, including issues of data privacy, algorithmic bias, and the need for rigorous validation and regulation. Prepare to discover how AI is reshaping the landscape of medicine and healthcare, offering the potential for more accurate, efficient, and personalized care, while also raising important questions about the role of technology in one of the most human-centric domains. The promise of AI in healthcare, improving diagnosis, treatment, and patient outcomes. AI has the potential to transform healthcare and medicine, offering the promise of earlier and more accurate diagnoses, more effective and personalized treatments, and improved patient outcomes. This section will explore the various ways in which AI is being applied across the healthcare spectrum, from diagnostics and drug discovery to personalized medicine and patient monitoring. We will also discuss the potential benefits of AI in healthcare, including increased efficiency, reduced costs, and improved access to care. This highlights the transformative potential of AI in healthcare. One of the most promising applications of AI in healthcare is in medical imaging analysis. AI algorithms, particularly deep learning models, can be trained to analyze medical images, such as X-rays, CT scans, and MRI scans, to detect and diagnose diseases such as cancer, fractures, and other abnormalities. AI can assist radiologists and improve diagnostic accuracy. It can help detect subtle patterns that may be missed by humans. AI is also being used to develop predictive models for patient outcomes. By analyzing electronic health records, patient demographics, and other data, machine learning algorithms can predict the likelihood of a patient developing a particular disease, experiencing complications, or responding to a specific treatment. Predictive models can inform clinical decision-making. They can help identify high-risk patients and tailor interventions. Personalized medicine, also known as precision medicine, is another area where AI is making a significant impact. By analyzing a patient's genetic information, lifestyle, and other factors, AI algorithms can help to identify the most effective treatments and prevention strategies for that individual. This can lead to more targeted and effective care, reducing the need for trial and error approaches. AI enables personalized treatments. It can improve patient outcomes and reduce side effects. AI is also being used to automate administrative tasks in healthcare, such as scheduling appointments, processing insurance claims, and managing medical records. This can free up healthcare professionals to focus on more complex and patient-facing tasks, improving efficiency and reducing costs. AI can streamline administrative processes. It can improve the efficiency of healthcare delivery. The potential benefits of AI in healthcare are vast. AI can help to improve the accuracy and speed of diagnoses, personalize treatments, reduce medical errors, improve patient monitoring, and increase the efficiency of healthcare delivery. It also has the potential to expand access to care, particularly in underserved areas. AI has the potential to revolutionize healthcare. It can improve the quality and efficiency of care. Medical image analysis. Enabling AI-powered diagnosis and screening. Medical image analysis is a key area where AI, particularly deep learning, is making significant strides. This section will explore how AI algorithms are being used to analyze various types of medical images, such as X-rays, CT scans, MRI scans, and pathology slides, to assist in the diagnosis and screening of diseases. We will examine the performance of these algorithms compared to human experts, discuss the challenges of developing and deploying AI for medical imaging, and consider the regulatory and ethical implications of using AI for diagnostic purposes. This showcases a powerful application of AI in healthcare. Deep learning, particularly convolutional neural networks, CNNs, has shown remarkable performance in analyzing medical images. CNNs can be trained on large datasets of labeled medical images to automatically learn features that are relevant for detecting and classifying diseases. They have achieved radiologist-level performance in certain tasks. They can detect subtle patterns that may be missed by humans. AI algorithms are being developed to detect and diagnose a wide range of diseases from medical images. For example, AI can detect cancerous tumors in mammograms, lung nodules in CT scans, diabetic retinopathy in retinal images, and fractures in X-rays. AI can also assist in the analysis of pathology slides, helping to identify and classify different types of cancer. AI can detect and diagnose various diseases. It can assist in screening and early detection. The performance of AI algorithms in medical image analysis is often compared to that of human experts, such as radiologists and pathologists. In several studies, AI algorithms have been shown to perform at or above the level of human experts in specific diagnostic tasks. However, it is important to note that these algorithms are typically trained and evaluated on specific datasets and may not generalize well to new or different types of data. AI can match or exceed human performance in some tasks. It is important to evaluate performance rigorously. Deploying AI for medical imaging presents several challenges. These include the need for large, well-annotated datasets for training, the difficulty of interpreting the decisions made by complex deep learning models, and the need for rigorous validation and testing to ensure safety and accuracy. Addressing these challenges is crucial for clinical adoption. It requires careful consideration of data, algorithms, and evaluation. The use of AI for diagnostic purposes also raises regulatory and ethical questions. Regulatory bodies, such as the FDA in the United States, are developing guidelines for the approval and use of AI-based medical devices. Ethical considerations include the need for transparency, accountability, and human oversight in the use of AI for diagnostic decision-making. Regulation and ethical guidelines are essential. They ensure safe and responsible use of AI in diagnosis. Predictive analytics and risk modeling, forecasting patient outcomes and identifying high-risk individuals. Predictive analytics and risk modeling are powerful applications of AI in healthcare, enabling the forecasting of patient outcomes and the identification of individuals at high risk of developing certain conditions. This section will explore how machine learning algorithms can be trained on electronic health records, patient demographics, and other data to predict the likelihood of future events, such as hospital readmissions, disease progression, and treatment response. We will also discuss the use of AI for risk stratification and population health management. This allows for proactive and preventative care. Machine learning algorithms, such as regression models, decision trees, and neural networks, can be trained on historical patient data to predict future outcomes. These models learn patterns and relationships in the data that can be used to make predictions about new patients. Predictive models can be used for various outcomes. They can help to anticipate patient needs. Electronic health records, EHRs, are a rich source of data for training predictive models. EHRs contain information about patient demographics, diagnoses, medications, lab results, procedures, and other clinical data. By analyzing this data, AI algorithms can identify patterns and risk factors that may not be apparent to human clinicians. EHRs provide valuable data for training predictive models. They enable data-driven insights into patient health. Predictive models can be used for risk stratification, which involves categorizing patients into different risk groups based on their predicted likelihood of experiencing a particular outcome. This can help healthcare providers to target interventions and resources to the patients who are most likely to benefit from them. Risk stratification enables proactive care. It allows for targeted interventions for high-risk patients. AI can also be used for population health management, which involves using data and analytics to improve the health of a defined population. Predictive models can identify individuals at high risk of developing chronic diseases, allowing for early interventions and preventive care. Population health management can improve overall health outcomes. It can help to reduce healthcare costs. The use of AI for predictive analytics and risk modeling raises ethical considerations. It is important to ensure that these models are fair and unbiased, and that they do not perpetuate existing health disparities. Transparency and explainability are also crucial, as clinicians need to understand the basis for the model's predictions in order to trust and act upon them. Ethical considerations are paramount. They ensure fairness, transparency, and trust in predictive models. Personalized medicine and treatment optimization, tailoring care to individual patients. Personalized medicine, also known as precision medicine, aims to tailor medical treatment to the individual characteristics of each patient. This section will explore how AI is enabling personalized medicine by analyzing patient data, including genetic information, lifestyle factors, and treatment responses, to predict the most effective treatments and interventions for individual patients. We will discuss the use of AI in pharmacogenomics, treatment recommendation systems, and the development of personalized prevention strategies. This promises more effective and targeted treatments. AI can analyze large and complex datasets, including genomic data, to identify patterns and biomarkers that predict treatment response. This can help to identify which patients are most likely to benefit from a particular treatment and which patients may experience adverse effects. AI enables personalized treatment selection. It can improve treatment efficacy and reduce side effects. Pharmacogenomics is a field that studies how an individual's genetic makeup affects their response to drugs. AI can be used to analyze a patient's genetic information, along with other factors, to predict their response to different medications. This can help clinicians to select the most effective and safest drug for each patient, reducing the need for trial and error approaches. AI can personalize drug selection. It can optimize medication regimens based on individual genetic profiles. AI-powered treatment recommendation systems can assist clinicians in making treatment decisions by providing evidence-based recommendations tailored to individual patients. These systems can analyze patient data, medical literature, and clinical guidelines to suggest the most appropriate treatment options, taking into account the patient's specific characteristics and preferences. Treatment recommendation systems can support clinical decision-making. They can provide personalized and evidence-based recommendations. AI can also be used to develop personalized prevention strategies. By analyzing a patient's risk factors and lifestyle data, AI algorithms can identify individuals who are at high risk of developing certain diseases and recommend personalized interventions, such as lifestyle changes or preventive medications. Personalized prevention can reduce disease burden. It can empower individuals to take control of their health. The development of personalized medicine raises ethical and practical challenges. These include ensuring equitable access to these technologies, protecting patient privacy, and addressing the potential for genetic discrimination. Addressing these challenges requires careful consideration of the societal implications of personalized medicine. Ethical and practical challenges must be addressed. They are crucial for responsible implementation. Drug discovery and development, accelerating the search for new therapies. The process of drug discovery and development is traditionally long, expensive, and fraught with failure. This section will explore how AI is being used to accelerate and improve the efficiency of drug discovery, from identifying promising drug candidates to predicting their efficacy and safety. We will examine the use of AI in virtual screening, de novo drug design, and the prediction of drug-drug interactions. We will also discuss the potential of AI to repurpose existing drugs for new indications and to personalize drug development based on patient characteristics. This demonstrates how AI can revolutionize drug development. AI can be used to analyze vast libraries of molecules to identify potential drug candidates. This process, known as virtual screening, can significantly reduce the time and cost compared to traditional experimental screening methods. AI can identify promising drug candidates. It can accelerate the early stages of drug discovery. Deep learning models, such as generative adversarial networks, GANs, and variational autoencoders, VAEs, can be used for de novo drug design, which involves generating novel molecules with desired properties. These models can learn the chemical rules and patterns from existing drug databases and generate new molecules that are likely to be effective and safe. AI can design novel drug candidates. It can explore new chemical spaces beyond traditional methods. AI can also be used to predict the efficacy and safety of drug candidates. By analyzing data from preclinical studies and clinical trials, machine learning models can predict how a drug will perform in humans, helping to prioritize the most promising candidates and reduce the risk of late-stage failures. AI can predict drug efficacy and safety. It can improve the success rate of drug development. Drug repurposing, also known as drug repositioning, involves identifying new uses for existing drugs. AI can analyze data from various sources, such as gene expression data, electronic health records, and scientific literature, to identify potential new indications for approved drugs. Drug repurposing can save time and money. It can offer new treatments for diseases with unmet needs. The use of AI in drug discovery and development is still in its early stages, but it holds immense promise for accelerating the development of new therapies and improving patient outcomes. As AI techniques continue to advance and more data becomes available, we can expect to see even more significant contributions from AI in this field. AI is poised to transform drug discovery. It offers the potential for faster, cheaper, and more effective drug development. Natural language processing in healthcare, extracting insights from textual data. The vast amount of textual data in healthcare, such as electronic health records, clinical notes, and scientific literature, contains valuable information that can be harnessed to improve patient care and advance medical research. This section will explore how natural language processing, NLP, techniques are being used to extract insights from unstructured textual data in healthcare. We will examine applications such as clinical information extraction, text mining for adverse event detection, and the use of NLP to improve clinical documentation and decision support. This demonstrates how AI can unlock the value of textual data in healthcare. NLP techniques can be used to automatically extract structured information from unstructured clinical text, such as patient diagnoses, medications, lab results, and procedures. This can help to populate electronic health records, automate coding and billing processes, and support clinical research. NLP can extract valuable information from clinical text. It can transform unstructured data into structured, actionable insights. Text mining techniques, such as topic modeling and sentiment analysis, can be applied to clinical notes and patient feedback to identify trends, patterns, and potential safety issues. For example, NLP can be used to detect adverse drug events by analyzing clinical notes and identifying mentions of potential side effects. NLP can identify safety issues and improve patient care. It can analyze large volumes of text to detect subtle patterns. NLP can also be used to improve clinical documentation and decision support. For example, NLP-powered systems can automatically generate clinical notes from doctor-patient conversations, reducing the documentation burden on clinicians. They can also provide real-time decision support by analyzing patient data and suggesting relevant guidelines or alerts. NLP can improve clinical documentation and decision-making. It can provide real-time support to clinicians. The use of NLP in healthcare presents several challenges. Clinical text is often complex, containing specialized terminology, abbreviations, and jargon. It may also contain sensitive patient information, raising privacy concerns. Developing accurate and robust NLP systems for healthcare requires addressing these challenges. Clinical NLP requires specialized techniques. It must handle the complexity and sensitivity of clinical text. Despite these challenges, the potential benefits of NLP in healthcare are significant. By unlocking the value of textual data, NLP can help to improve the quality, safety, and efficiency of patient care, and accelerate medical research. NLP is a powerful tool for healthcare. It can transform the way we analyze and use clinical text data. Robotics in surgery and healthcare, assisting humans and enhancing precision. Robotics is increasingly being used in surgery and other healthcare applications to assist human clinicians and enhance the precision and safety of medical procedures. This section will explore the use of robotics in surgery, including robot-assisted surgery, telesurgery, and rehabilitation robotics. We will examine how AI techniques, such as computer vision and control algorithms, are enabling the development of more sophisticated and autonomous surgical robots. We will also discuss the benefits and challenges of robotic surgery and consider its impact on the future of healthcare. This showcases how AI-powered robots can improve surgical procedures. Robot-assisted surgery, also known as robotic surgery, involves the use of robotic systems to assist surgeons in performing surgical procedures. The most well-known example is the Da Vinci surgical system, which allows surgeons to control robotic instruments with high precision and dexterity through a console. Robotic surgery can enhance surgical precision and dexterity. It can enable minimally invasive procedures and reduce surgeon fatigue. Telesurgery is a form of robotic surgery where the surgeon and the patient are not in the same location. The surgeon controls the robotic instruments remotely, using a telecommunication system. This has the potential to expand access to specialized surgical expertise, particularly in remote or underserved areas. Telesurgery can overcome geographical barriers. It can provide access to specialized care remotely. Rehabilitation robotics involves the use of robots to assist patients in regaining motor function after an injury or illness, such as a stroke. Robotic devices can provide repetitive and customized exercises, helping patients to recover strength, coordination, and mobility. Rehabilitation robots can improve patient outcomes. They can provide personalized and intensive therapy. AI plays an important role in enhancing the capabilities of surgical robots. Computer vision techniques can be used to provide surgeons with augmented views of the surgical field, highlighting important structures or potential risks. AI-powered control algorithms can assist in stabilizing the robot's movements and preventing errors. AI can enhance the capabilities of surgical robots. It can improve safety and precision. The use of robotics in surgery offers several potential benefits, including smaller incisions, reduced blood loss, faster recovery times, and improved precision. However, it also presents challenges, such as the high cost of robotic systems, the need for specialized training for surgeons, and the potential for technical malfunctions. Robotic surgery has many potential benefits. It also presents challenges that must be addressed. Ethical considerations and challenges in AI for healthcare. The increasing use of AI in healthcare raises important ethical considerations and challenges. This section will explore the critical issues surrounding the responsible development and deployment of AI in healthcare, including concerns about data privacy and security, algorithmic bias and fairness, the impact on the patient-physician relationship, and the need for appropriate regulation and oversight. This encourages a thoughtful and ethical approach to AI in healthcare. Data privacy and security are paramount concerns in healthcare, as patient data is highly sensitive and subject to strict regulations, such as HIPAA in the United States. AI systems that use patient data must be designed and implemented in a way that protects patient privacy and complies with relevant regulations. Data privacy and security are crucial. They must be ensured when using AI in healthcare. Algorithmic bias and fairness are also critical considerations. AI systems trained on biased data can perpetuate and even amplify existing health disparities. For example, if an AI system for diagnosing skin cancer is trained primarily on images of light-skinned individuals, it may perform poorly on individuals with darker skin tones. Ensuring fairness and mitigating bias in AI for healthcare is essential. It requires careful attention to data, algorithms, and evaluation. The use of AI in healthcare may also impact the patient-physician relationship. Some researchers have raised concerns that the increasing reliance on AI could lead to a depersonalization of care, with patients feeling that they are being treated by a machine rather than a human being. It is important to maintain the human element of care. AI should augment, not replace, human interaction in healthcare. The need for appropriate regulation and oversight of AI in healthcare is widely recognized. Regulatory bodies, such as the FDA, are developing frameworks for evaluating the safety and effectiveness of AI-based medical devices. However, the rapid pace of AI development poses challenges for regulators, who must balance the need for innovation with the need to protect patient safety. Regulation and oversight are crucial. They must keep pace with technological advancements. Addressing these ethical challenges requires a multidisciplinary approach, involving not only technical solutions but also broader societal discussions about the values we want to embed in these systems and the kind of healthcare system we want to create with them. It requires collaboration between researchers, clinicians, ethicists, policymakers, and patients. We must shape the future of AI in healthcare responsibly. It is a collective responsibility. Future directions and emerging trends in AI for healthcare. The field of AI in healthcare is rapidly evolving, with new techniques and applications emerging at an accelerating pace. This section will explore some of the most promising future directions and emerging trends in AI for healthcare, including the convergence of AI with other technologies, such as genomics and the Internet of Medical Things, the development of more integrated and holistic AI systems for healthcare, and the use of AI to address global health challenges. This provides a glimpse into the future of AI in healthcare. One major trend is the convergence of AI with other emerging technologies. The integration of AI with genomics, for example, is enabling more precise and personalized medicine, allowing for the tailoring of treatments to individual genetic profiles. The combination of AI with the Internet of Medical Things, IoT, is enabling continuous monitoring of patients and the early detection of health issues. The convergence of AI with other technologies is transformative. It enables new capabilities and applications in healthcare. The development of more integrated and holistic AI systems for healthcare is another important direction. Instead of focusing on individual tasks, such as image analysis or risk prediction, researchers are working towards developing AI systems that can integrate data from multiple sources and provide a more comprehensive view of a patient's health. Holistic AI systems can provide a more complete picture. They can support more integrated and coordinated care. The use of AI to address global health challenges, such as pandemics and healthcare disparities, is a growing area of research and development. AI can be used to model the spread of infectious diseases, optimize resource allocation, and develop new diagnostic and treatment tools that are accessible and affordable in low-resource settings. AI can address global health challenges. It has the potential to improve health equity worldwide. The development of more robust, reliable, and interpretable AI systems for healthcare is also a key priority. This includes addressing issues such as algorithmic bias, data privacy, and the need for rigorous validation and testing. As AI systems become more integrated into clinical practice, ensuring their safety, effectiveness, and trustworthiness is paramount. Robustness, reliability, and interpretability are essential. They are crucial for clinical adoption and patient trust. Finally, the increasing availability of large-scale health data and the development of new AI techniques, such as federated learning and transfer learning, are likely to continue to drive progress in AI for healthcare. As these trends converge, we can expect to see even more transformative applications of AI in healthcare in the years to come, leading to improved patient outcomes and a more efficient and equitable healthcare system. The future of AI in healthcare is bright. It holds immense potential for improving human health. Lesson 11, AI in Finance and FinTech, Revolutionizing Financial Services and Decision-Making. Welcome back, astute learners, to the 11th lesson in our advanced exploration of artificial intelligence. In this lesson, we venture into the dynamic world of finance and FinTech, a sector where AI is rapidly transforming the way financial institutions operate, make decisions, and interact with customers. We will explore how AI techniques, such as machine learning, natural language processing, and robotic process automation, are being used to automate tasks, detect fraud, assess risk, optimize portfolios, and personalize financial services. We will also examine the challenges and ethical considerations associated with deploying AI in finance, including issues of data privacy, algorithmic bias, and the need for transparency and accountability. Prepare to discover how AI is revolutionizing the financial industry, offering the potential for more efficient, data-driven, and customer-centric financial services, while also raising important questions about the role of technology in shaping our economic and financial systems. The rise of AI in finance, automating processes and enhancing decision-making. The financial industry is undergoing a profound transformation driven by the increasing adoption of AI technologies. This section will explore the key drivers behind the rise of AI in finance, highlighting the potential benefits of AI in automating processes, improving decision-making, and enhancing customer experience. We will also discuss the different areas within finance where AI is making a significant impact, from investment management and trading to risk management and regulatory compliance. This sets the stage for understanding the transformative role of AI in finance. Several factors are driving the adoption of AI in finance. The availability of vast amounts of financial data, coupled with the increasing computational power and the development of sophisticated AI algorithms, has created unprecedented opportunities for financial institutions to leverage AI for competitive advantage. Data, computing power, and algorithms are key drivers. They enable AI to unlock new value in finance. AI can automate many of the repetitive and time-consuming tasks that are traditionally performed by humans in the financial industry. This includes tasks such as data entry, document processing, and customer service. Automation can improve efficiency, reduce costs, and free up human employees to focus on more complex and strategic tasks. AI can automate routine tasks. It can improve operational efficiency. AI can also enhance decision-making in finance by providing data-driven insights and predictions. Machine learning algorithms can analyze large datasets to identify patterns, trends, and anomalies that may not be apparent to human analysts. This can lead to more informed investment decisions, better risk management, and more accurate pricing of financial products. AI can enhance decision-making. It provides data-driven insights and predictions. The customer experience in finance is also being transformed by AI. AI-powered chatbots can provide 24/7 customer support, answering questions, resolving issues, and guiding customers through various financial processes. Personalized financial advice and product recommendations can be delivered through AI-powered platforms, tailored to individual customer needs and preferences. AI can personalize the customer experience. It can provide tailored services and support. The use of AI in finance is growing rapidly across various domains, including investment management, algorithmic trading, risk management, fraud detection, customer service, and regulatory compliance. As AI technologies continue to mature and become more integrated into financial operations, we can expect to see even more significant transformations in the years to come. AI is transforming many areas of finance. It is becoming a core technology in the industry. Algorithmic trading and quantitative finance, leveraging AI for investment strategies. Algorithmic trading and quantitative finance are areas where AI is having a particularly significant impact, enabling the development of sophisticated trading strategies that can analyze vast amounts of data and execute trades at high speeds. This section will explore how machine learning algorithms are being used to develop and optimize trading strategies, predict market movements, and manage portfolios. We will also discuss the challenges of using AI in trading, including the need for robust models, the risk of overfitting, and the potential impact on market stability. This showcases a high-impact application of AI in finance. Algorithmic trading, also known as algo trading or black box trading, involves the use of computer algorithms to automate trading decisions. These algorithms can analyze market data, identify trading opportunities, and execute trades automatically, often at speeds and volumes that are impossible for human traders. Algorithmic trading automates trading decisions. It enables high-frequency and high-volume trading. Machine learning, particularly reinforcement learning and deep learning, is increasingly being used to develop and optimize trading strategies. These algorithms can learn complex patterns in market data and adapt to changing market conditions, potentially outperforming traditional rule-based trading systems. AI can learn and adapt trading strategies. It can potentially outperform traditional approaches. AI can also be used to predict market movements by analyzing various data sources, such as financial news, social media sentiment, and economic indicators. These predictions can inform trading decisions and help to manage risk. However, predicting market movements is a challenging task, and the accuracy of these predictions can vary. AI can predict market movements. It is a challenging but valuable application. Quantitative finance, or quant finance, is a field that uses mathematical and statistical models to analyze financial markets and develop investment strategies. AI is increasingly being integrated into quant finance, enabling the development of more sophisticated models that can capture complex market dynamics and identify profitable trading opportunities. AI enhances quantitative finance. It enables more complex and data-driven models. The use of AI in trading and quantitative finance presents several challenges. One challenge is the need for robust and reliable models that can perform well in a wide range of market conditions. Overfitting, where a model performs well on historical data but poorly on new data, is a significant risk. Robustness and generalization are key challenges. They require careful model development and testing. Another challenge is the potential impact of AI-driven trading on market stability. Some researchers have raised concerns that the widespread use of algorithmic trading could increase market volatility and the risk of flash crashes. It is important to monitor and manage the systemic risks associated with AI in trading. The impact on market stability must be considered. It requires careful monitoring and regulation. Credit scoring and risk assessment. Improving lending decisions with AI. Credit scoring and risk assessment are crucial functions in the financial industry, determining who gets access to credit and at what terms. This section will explore how AI is being used to improve the accuracy and efficiency of credit scoring and risk assessment, enabling lenders to make better informed decisions and potentially expand access to credit for underserved populations. We will also discuss the challenges of using AI in lending, including the potential for bias and the need for transparency and fairness. This demonstrates how AI can enhance lending and credit decisions. Traditional credit scoring models rely on a limited number of factors, such as credit history, income, and employment status, to assess the creditworthiness of borrowers. These models may not accurately reflect the true risk of lending to certain individuals, particularly those with limited credit history or unconventional employment patterns. Traditional credit scoring has limitations. It may exclude some creditworthy borrowers. AI-powered credit scoring models can incorporate a wider range of data sources, such as alternative data like utility bill payments, rental history, and even social media activity, to provide a more comprehensive assessment of creditworthiness. This can potentially expand access to credit for individuals who may have been excluded by traditional models. AI can incorporate alternative data. It can provide a more holistic view of creditworthiness. Machine learning algorithms can also be used to develop more accurate and nuanced risk models. These models can identify complex patterns and relationships in the data that may not be captured by traditional statistical methods, leading to more precise risk assessments. AI can improve the accuracy of risk models. It can capture complex patterns in data. However, the use of AI in credit scoring and risk assessment raises concerns about bias and fairness. If the training data reflects existing societal biases, the AI models may perpetuate and even amplify these biases, leading to discriminatory outcomes. It is crucial to ensure that AI-powered credit scoring models are fair and unbiased. Bias and fairness are critical concerns. They require careful attention and mitigation. Transparency and explainability are also important in the context of AI-powered lending decisions. Borrowers have a right to understand how their creditworthiness is being assessed and what factors are influencing the lending decision. Developing interpretable AI models and providing clear explanations to borrowers is essential for building trust and ensuring accountability. Transparency and explainability are essential. They are crucial for trust and fairness in lending. Addressing these challenges requires a combination of technical solutions, such as fairness-aware algorithms and bias detection techniques, and regulatory frameworks that promote fairness, transparency, and accountability in AI-powered lending. It also requires ongoing monitoring and auditing of these systems to ensure that they are performing as intended and are not producing discriminatory outcomes. A multifaceted approach is needed. It requires technical, regulatory, and ethical considerations. Fraud detection and anti-money laundering. Protecting financial systems with AI. Fraud detection and anti-money laundering, AML, are critical functions for financial institutions, helping to protect their customers and maintain the integrity of the financial system. This section will explore how AI is being used to enhance fraud detection and AML efforts, enabling institutions to identify and prevent fraudulent transactions and illicit financial flows more effectively. We will also discuss the challenges of using AI in these domains, including the constantly evolving nature of fraud and the need for robust and adaptable models. This showcases how AI can enhance security and compliance in finance. Fraudulent transactions and money laundering activities can have devastating consequences for individuals, businesses, and the financial system as a whole. Traditional rule-based systems for detecting fraud and AML violations are often slow, inefficient, and prone to false positives, requiring significant manual review. Fraud and money laundering are major threats. They require sophisticated detection and prevention methods. Particularly machine learning, can significantly enhance fraud detection and AML efforts. Machine learning algorithms can analyze vast amounts of transaction data to identify patterns and anomalies that may indicate fraudulent activity or money laundering. These algorithms can adapt to new fraud patterns and learn from past cases, improving their accuracy over time. AI can detect complex patterns of fraud. It can adapt to evolving fraud techniques. AI can be used to detect various types of fraud, including credit card fraud, identity theft, and account takeover. It can also be used to identify suspicious patterns of transactions that may indicate money laundering, such as structuring, layering, and the use of shell companies. AI can detect various types of financial crime. It can identify suspicious patterns and anomalies. One of the key advantages of using AI for fraud detection and AML is its ability to process and analyze data in real time. This allows financial institutions to detect and prevent fraudulent transactions before they are completed, minimizing potential losses. Real-time detection is crucial. It can prevent fraud before it causes damage. However, the use of AI in these domains also presents challenges. Fraudsters are constantly developing new techniques to evade detection, requiring AI models to be continuously updated and retrained. The need for large amounts of labeled data to train these models can also be a challenge, as fraudulent transactions are relatively rare compared to legitimate ones. AI models must be constantly updated. They must adapt to new fraud techniques. The use of AI for fraud detection and AML also raises ethical considerations, particularly regarding privacy and the potential for false positives. It is important to balance the need for security with the protection of individual rights and to ensure that AI systems are used responsibly and ethically in these sensitive areas. Ethical considerations are paramount. They require a careful balance between security and privacy. Customer service and chatbots. Enhancing customer experience with AI. Customer service is a critical function for financial institutions, and AI is increasingly being used to enhance and automate customer interactions. This section will explore how AI-powered chatbots and virtual assistants are transforming customer service in finance, providing 24/7 support, answering queries, and guiding customers through various financial processes. We will also discuss the benefits and limitations of AI-powered customer service and the importance of maintaining a human touch in customer interactions. This demonstrates how AI can improve customer service in finance. AI-powered chatbots and virtual assistants can provide instant and personalized customer service, answering frequently asked questions, resolving simple issues, and guiding customers through various processes, such as opening an account, applying for a loan, or making a payment. Chatbots can provide 24/7 support. They can handle a large volume of inquiries simultaneously. Natural language processing, NLP, is a key technology that enables chatbots to understand and respond to customer queries in a natural and intuitive way. NLP allows chatbots to parse customer requests, extract relevant information, and generate appropriate responses. NLP is essential for chatbot understanding. It enables natural language interaction. Machine learning allows chatbots to learn from past interactions and improve their performance over time. By analyzing customer data and feedback, chatbots can be trained to provide more accurate and relevant responses, personalize their interactions, and even anticipate customer needs. Machine learning improves chatbot performance. It enables adaptation and personalization. The use of chatbots in financial services offers several benefits. They can reduce wait times for customers, improve customer satisfaction, and free up human agents to handle more complex or sensitive issues. They can also help to reduce operational costs for financial institutions. Chatbots offer many benefits. They improve efficiency and customer satisfaction. However, chatbots also have limitations. They may struggle with complex or ambiguous queries, and they may not be able to handle sensitive or emotional situations that require human empathy and judgment. It is important to design chatbots carefully and to provide clear pathways for escalation to human agents when needed. Chatbots have limitations. They are not a replacement for human agents in all situations. Maintaining a human touch in customer interactions is crucial, even as AI-powered chatbots become more prevalent. Many customers still prefer to interact with a human agent, particularly for complex or sensitive issues. Financial institutions must strike a balance between automation and human interaction to provide the best possible customer experience. The human touch remains important. It is essential for building trust and rapport with customers. Robo-advisors and personalized financial planning. Democratizing investment advice with AI robo-advisors are automated investment platforms that use AI algorithms to provide personalized financial advice and manage investment portfolios. This section will explore how robo-advisors are making investment advice more accessible and affordable, particularly for individuals with smaller amounts to invest. We will examine the different types of robo-advisors, the algorithms they use, and the benefits and limitations of relying on AI for investment decisions. We will also discuss the potential impact of robo-advisors on the traditional financial advisory industry. This illustrates how AI is democratizing access to financial advice. Robo-advisors use algorithms to create and manage diversified investment portfolios based on a client's risk tolerance, investment goals, and time horizon. They typically charge lower fees than traditional human financial advisors, making them an attractive option for many investors. Robo-advisors automate investment management. They offer a low-cost alternative to traditional advisors. There are different types of robo-advisors, ranging from fully automated platforms that require minimal human intervention to hybrid models that combine algorithmic advice with access to human advisors. The choice of robo-advisor depends on the individual investor's needs and preferences. Robo-advisors offer different levels of automation and human interaction. They cater to a range of investor needs. The algorithms used by robo-advisors typically rely on modern portfolio theory, MPT, and other established investment principles to construct and rebalance portfolios. They may also incorporate machine learning techniques to adapt to changing market conditions and personalize the portfolio allocation based on individual client characteristics. Robo-advisor algorithms are based on established investment principles. They may also incorporate machine learning for adaptation. Robo-advisors offer several benefits, including low fees, accessibility, and convenience. They can be particularly beneficial for individuals who are new to investing or who have smaller amounts to invest and may not have access to traditional financial advisors. Robo-advisors democratize access to investment advice. They make it more affordable and accessible. However, robo-advisors also have limitations. They may not be suitable for investors with complex financial situations or those who prefer a more personalized, hands-on approach. They may also be less effective in navigating periods of extreme market volatility or unexpected events that require human judgment and experience. Robo-advisors have limitations. They may not be suitable for all investors or all market conditions. The rise of robo-advisors has the potential to disrupt the traditional financial advisory industry, putting pressure on fees and increasing competition. However, it is likely that human advisors will continue to play an important role, particularly for high-net-worth individuals and those with complex financial planning needs. Robo-advisors are transforming the financial advisory industry. They are creating both opportunities and challenges for traditional advisors. Regulatory compliance and RegTech, streamlining compliance with AI. The financial industry is subject to a complex and ever-changing regulatory environment, and ensuring compliance with these regulations is a major challenge for financial institutions. This section will explore how AI is being used to streamline and automate regulatory compliance processes, a field known as RegTech, regulatory technology. We will examine how AI can help with tasks such as regulatory reporting, compliance monitoring, and risk management, and discuss the benefits and challenges of using AI for regulatory compliance. This demonstrates how AI can improve efficiency and accuracy in compliance. Regulatory compliance involves adhering to a wide range of rules and regulations, including those related to anti-money laundering, AML, Know Your Customer, KYC, requirements, data privacy, and consumer protection. Manual compliance processes are often time-consuming, expensive, and prone to errors. Compliance is a major challenge for financial institutions. It requires significant resources and expertise. AI can help to automate and streamline many aspects of regulatory compliance. For example, NLP techniques can be used to analyze regulatory documents and extract relevant information, helping institutions to stay up to date with changing regulations. Machine learning can be used to monitor transactions and identify patterns that may indicate non-compliance. AI can automate and enhance compliance processes. It can improve accuracy and reduce manual effort. AI can also assist with regulatory reporting by automatically generating reports that meet specific regulatory requirements. This can save time and reduce the risk of errors in reporting. AI can also be used to assess and manage compliance risks, by identifying areas where the institution may be vulnerable to non-compliance and suggesting remediation measures. AI can streamline regulatory reporting. It can improve risk management and compliance. The use of AI for regulatory compliance offers several benefits, including increased efficiency, reduced costs, improved accuracy, and better risk management. It can also help financial institutions to adapt more quickly to changing regulations and avoid penalties for non-compliance. AI offers significant benefits for compliance. It can transform the way institutions manage regulatory requirements. However, the use of AI in RegTech also presents challenges. Ensuring the accuracy and reliability of AI models is crucial, as errors or biases in these models could have serious consequences. The need for transparency and explainability is also important, as regulators and auditors need to understand how AI-based compliance systems work and how they arrive at their conclusions. Accuracy, reliability, and explainability are crucial. They are essential for trust and regulatory acceptance. The field of RegTech is rapidly evolving, with new AI-powered solutions being developed to address a wide range of compliance challenges. As regulations continue to evolve and become more complex, the role of AI in regulatory compliance is likely to become even more important in the years to come. RegTech is a growing field. It is driven by the increasing need for efficient and effective compliance solutions. Ethical considerations and challenges in AI for finance. The increasing use of AI in finance raises important ethical considerations and challenges. This section will explore the critical issues surrounding the responsible development and deployment of AI in finance, including concerns about data privacy and security, algorithmic bias and fairness, the impact on employment and the workforce, and the need for transparency and accountability in AI-driven financial decision-making. This encourages a thoughtful and ethical approach to AI in finance. Data privacy and security are paramount concerns in finance, as financial institutions handle vast amounts of sensitive customer data. AI systems that use this data must be designed and implemented in a way that protects customer privacy and complies with relevant regulations, such as the General Data Protection Regulation, GDPR, in Europe. Data privacy and security are crucial in finance. They require robust safeguards and compliance with regulations. Algorithmic bias and fairness are also critical considerations in the context of financial AI systems. Biased algorithms can perpetuate and even amplify existing inequalities in access to credit, investment opportunities, and other financial services. Ensuring fairness and mitigating bias in financial AI systems requires careful attention to data, algorithms, and evaluation metrics. Bias and fairness are major ethical challenges. They require proactive measures to ensure equitable outcomes. The impact of AI on employment in the financial industry is another important issue. While AI can automate many routine tasks, potentially leading to job displacement in some areas, it can also create new roles and opportunities that require different skill sets. Managing this transition and ensuring that the workforce is prepared for the changing demands of the industry is a key challenge. The impact on employment must be considered. It requires proactive measures for workforce adaptation. Transparency and accountability are essential for building trust in AI-driven financial systems. Customers, regulators, and other stakeholders need to understand how these systems work and how decisions are being made. Developing explainable AI, XAI, techniques for finance is an active area of research and development. Transparency and accountability are crucial for trust. They are essential for responsible deployment of AI in finance. Addressing these ethical challenges requires a multifaceted approach, involving not only technical solutions but also broader societal discussions about the values we want to embed in these systems and the kind of financial system we want to create with them. It requires collaboration between researchers, industry practitioners, policymakers, and the public. We must shape the future of AI in finance responsibly. It is a collective responsibility. Future directions and emerging trends in AI for finance. The field of AI in finance is rapidly evolving, with new techniques and applications emerging at an accelerating pace. This section will explore some of the most promising future directions and emerging trends in AI for finance, including the increasing use of alternative data, the development of more sophisticated and explainable AI models, and the convergence of AI with other technologies such as blockchain and quantum computing. This provides a glimpse into the future of AI in finance. One major trend is the increasing use of alternative data in financial decision-making. Alternative data refers to data that is not typically used in traditional financial analysis, such as satellite imagery, social media sentiment, and web traffic data. AI algorithms can analyze these unconventional data sources to identify new investment opportunities, assess risks, and gain a competitive edge. Alternative data is becoming increasingly important. It provides new insights and opportunities for financial analysis. The development of more sophisticated and explainable AI models is another key direction. As AI systems become more complex, the need for transparency and interpretability becomes even more pressing. Researchers are developing new techniques for explaining the decisions of AI models and for building more inherently interpretable models. Explainability is crucial for trust and adoption. It is an active area of research and development. The convergence of AI with other emerging technologies, such as blockchain and quantum computing, is also likely to shape the future of finance. Blockchain technology can enhance the security and transparency of financial transactions, while quantum computing has the potential to revolutionize areas such as portfolio optimization and risk modeling. The convergence of AI with other technologies is transformative. It offers new possibilities for innovation in finance. The increasing use of AI in decentralized finance, DeFi, is another emerging trend. DeFi platforms use blockchain technology and smart contracts to create decentralized financial applications that operate without intermediaries. AI can be used to optimize these platforms, automate decision-making, and manage risks. AI is playing a role in decentralized finance. It is enabling new forms of financial applications. Finally, the growing importance of environmental, social, and governance, ESG, factors in investment decision-making is creating new opportunities for AI. AI algorithms can analyze vast amounts of ESG data to identify companies that are well-positioned for long-term sustainability and to help investors align their portfolios with their values. AI can support sustainable investing. It can help to integrate ESG factors into financial decision-making. The future of AI in finance is bright, with many exciting research directions and potential applications on the horizon. As you continue your journey in AI, you will have the opportunity to contribute to these advancements and shape the future of this dynamic field, creating intelligent systems that can transform the financial industry and improve financial outcomes for individuals and society. The possibilities are vast. The future of AI in finance is full of potential. Lesson 12, AI-driven autonomous systems, self-driving cars, drones, and the future of autonomy. Welcome back, ambitious learners, to the 12th lesson in our advanced exploration of artificial intelligence. In this lesson, we venture into the exciting and rapidly evolving domain of AI-driven autonomous systems, focusing on two prominent examples, self-driving cars and drones. We will examine how AI techniques, such as computer vision, deep learning, reinforcement learning, and sensor fusion, are enabling the development of vehicles and aircraft that can navigate and operate in complex environments without human intervention. We will also explore the challenges and limitations of autonomous systems, including safety, reliability, and public acceptance, and discuss the ethical and societal implications of deploying these technologies at scale. Prepare to delve into the world of autonomous systems and discover how AI is reshaping transportation, logistics, and other industries, while also raising important questions about the future of human-machine interaction and the role of autonomy in our society. The rise of autonomous systems, from science fiction to reality. Autonomous systems, capable of operating and making decisions without direct human control, have long been a staple of science fiction. Today, they are rapidly becoming a reality, driven by advances in AI and related technologies. This section will explore the factors that have contributed to the rise of autonomous systems, highlighting the key technological enablers and the potential benefits of these systems in various domains. We will also discuss the different levels of autonomy and the challenges of transitioning from human-controlled to fully autonomous systems. This sets the stage for understanding the transformative potential of autonomous systems. Several factors have converged to enable the development of autonomous systems. Advances in AI, particularly in areas such as computer vision, deep learning, and reinforcement learning, have provided the necessary intelligence for these systems to perceive their environment, make decisions, and act autonomously. AI is the brain of autonomous systems. It enables perception, decision-making, and control. The availability of powerful and affordable sensors, such as cameras, LiDAR, radar, and GPS, has provided autonomous systems with the ability to perceive their surroundings with increasing accuracy and detail. These sensors provide the raw data that AI algorithms need to understand the environment and make informed decisions. Sensors are the eyes and ears of autonomous systems. They provide crucial information about the environment. Advances in computing hardware, particularly the development of specialized AI chips and the increasing power of GPUs, have made it possible to process the vast amounts of data generated by sensors and run complex AI algorithms in real time. This is essential for autonomous systems that need to make decisions quickly and react to changing conditions. Computing power is essential for real-time processing. It enables fast and efficient decision-making. The potential benefits of autonomous systems are vast. In transportation, self-driving cars have the potential to improve road safety, reduce traffic congestion, and increase fuel efficiency. In logistics, autonomous drones and robots can streamline delivery and warehousing operations. In agriculture, autonomous systems can optimize planting, harvesting, and crop management. Autonomous systems promise increased safety, efficiency, and productivity. They have the potential to transform various industries. The Society of Automotive Engineers, SAE, has defined 6 levels of driving automation, ranging from level 0, no automation, to level 5, full automation. These levels provide a framework for understanding the different degrees of autonomy in self-driving cars, from driver assistance features like adaptive cruise control to fully autonomous vehicles that require no human intervention. The SAE levels define the spectrum of autonomy. They provide a common language for discussing autonomous driving capabilities. The transition from human-controlled to fully autonomous systems presents many challenges, including ensuring the safety and reliability of these systems, addressing public concerns and building trust, and navigating the complex legal and regulatory landscape. The transition to full autonomy is complex. It requires addressing technical, social, and legal challenges. Self-driving cars, navigating the complexities of autonomous driving. Self-driving cars, also known as autonomous vehicles, AVs, are one of the most visible and anticipated applications of AI-driven autonomous systems. This section will delve into the technologies that enable self-driving cars, including computer vision, sensor fusion, localization and mapping, path planning, and control. We will examine how these technologies work together to enable a car to perceive its environment, make driving decisions, and navigate safely and efficiently without human intervention. We will also discuss the challenges and limitations of self-driving technology. This provides an in-depth look at the technology behind self-driving cars. Computer vision is a crucial component of self-driving cars, enabling them to see and interpret their surroundings. Cameras, often combined with deep learning algorithms, are used to detect and classify objects such as pedestrians, other vehicles, traffic lights, and lane markings. Computer vision provides visual understanding. It enables the car to perceive its environment. Sensor fusion is the process of combining data from multiple sensors to create a more complete and accurate understanding of the environment. In addition to cameras, self-driving cars use LiDAR, radar, and ultrasonic sensors to measure distances to objects, detect their speed and direction, and create a 3D map of the surroundings. Sensor fusion provides a comprehensive view. It combines data from multiple sources for robust perception. Localization and mapping are essential for self-driving cars to know where they are and how to navigate to their destination. High-definition maps, combined with GPS, inertial measurement units, IMUs, and visual odometry, are used to precisely locate the vehicle on the map and track its movement over time. Localization and mapping provide spatial awareness. They enable the car to know its location and plan its route. Path planning involves generating a safe and efficient trajectory for the car to follow, taking into account the vehicle's dynamics, the rules of the road, and the presence of other objects. This often involves using optimization algorithms to find the best path that minimizes travel time, fuel consumption, or other criteria. Path planning generates a trajectory for the car. It ensures safe and efficient navigation. Control systems are responsible for executing the planned path by controlling the vehicle's steering, acceleration, and braking. These systems must be able to react quickly and accurately to changing conditions, such as unexpected obstacles or changes in the road surface. Control systems execute the planned actions. They are crucial for safe and stable driving. Despite the significant progress in self-driving technology, many challenges remain. Ensuring the safety and reliability of these systems in all driving conditions, including adverse weather, complex urban environments, and unexpected situations, is a major challenge. Addressing these challenges requires extensive testing, validation, and ongoing research and development. Safety and reliability are paramount. They are ongoing challenges for self-driving cars. Drones and unmanned aerial vehicles, taking autonomy to the skies. Drones, also known as unmanned aerial vehicles, UAVs, are another rapidly growing application of AI-driven autonomous systems. This section will explore the technologies that enable drones to fly autonomously, including GPS, inertial navigation, computer vision, and control systems. We will examine how AI techniques, such as deep learning and reinforcement learning, are being used to develop more intelligent and adaptable drones that can perform a wide range of tasks, from aerial photography and surveillance to package delivery and infrastructure inspection. This highlights the expanding role of drones in various applications. Drones rely on a combination of technologies to achieve autonomous flight. GPS provides global positioning information, allowing the drone to know its location in the world. Inertial navigation systems, INS, use accelerometers and gyroscopes to track the drone's movement and orientation. These systems work together to provide accurate positioning and navigation. GPS and INS provide positioning and orientation. They are essential for autonomous flight. Computer vision is increasingly being used in drones to enable them to perceive and understand their environment. Cameras, combined with deep learning algorithms, can be used for tasks such as obstacle avoidance, object recognition, and visual tracking. Computer vision enhances situational awareness. It enables drones to react to their surroundings. Control systems are responsible for maintaining the stability of the drone and executing flight commands. These systems use feedback from the sensors to adjust the speed and direction of the drone's rotors, keeping it on the desired flight path. Control systems are crucial for stable flight. They enable precise maneuvering. AI techniques, such as deep learning and reinforcement learning, are being used to develop more intelligent and adaptable drones. Deep learning can be used to train drones to recognize objects, navigate complex environments, and make decisions based on visual input. Reinforcement learning can be used to train drones to perform complex maneuvers and optimize their flight paths. AI enhances drone capabilities. It enables more autonomous and intelligent behavior. Drones have a wide range of applications, including aerial photography and videography, surveillance and security, infrastructure inspection, precision agriculture, and package delivery. As drone technology continues to advance, we can expect to see even more innovative applications in the years to come. Drones have diverse applications. They are transforming various industries. The development and deployment of autonomous drones also raise important challenges and concerns. Ensuring the safety and reliability of these systems, particularly in shared airspace, is crucial. Addressing privacy concerns related to aerial surveillance and data collection is also important. Safety, privacy, and regulation are key challenges. They must be addressed for responsible drone deployment. The challenges of safety and reliability in autonomous systems. Ensuring the safety and reliability of autonomous systems is a critical challenge, particularly as these systems are increasingly deployed in safety-critical applications such as transportation and healthcare. This section will explore the unique challenges of building safe and reliable autonomous systems, including the need for rigorous testing and validation, the difficulty of handling unexpected or adversarial situations, and the importance of designing systems that can fail gracefully and safely. We will also discuss different approaches to ensuring safety, such as formal methods, simulation, and redundancy. This addresses a fundamental concern in autonomous systems development. Autonomous systems must be able to operate safely and reliably in a wide range of conditions, including unexpected or adversarial situations. This requires rigorous testing and validation, which can be challenging for complex AI-driven systems that may exhibit unpredictable behavior. Ensuring safety and reliability is a major challenge. It requires extensive testing and validation. One approach to ensuring safety is to use formal methods, which involve mathematically proving that a system meets certain safety requirements. However, applying formal methods to complex AI systems can be difficult and may not be feasible for all types of systems. Formal methods provide strong guarantees but are challenging to apply. They are an active area of research for AI safety. Simulation is another important tool for testing and validating autonomous systems. By creating realistic virtual environments, developers can test their systems in a wide range of scenarios, including rare or dangerous situations that would be difficult or impossible to test in the real world. Simulation enables extensive testing in a safe environment. It can help to identify potential safety issues. Redundancy, which involves using multiple independent systems or components to perform the same function, can also improve safety and reliability. If one component fails, another can take over, ensuring that the system as a whole continues to operate safely. Redundancy improves fault tolerance. It is a common approach in safety-critical systems. Autonomous systems must also be designed to fail gracefully and safely. This means that if a system encounters a situation that it cannot handle, it should be able to safely disengage or alert a human operator to take over. Designing systems that can recognize their own limitations and respond appropriately is a key challenge in AI safety. Fail-safe mechanisms are crucial. They ensure that the system can handle unexpected situations. Addressing the safety and reliability challenges of autonomous systems requires a multidisciplinary approach, combining techniques from AI, software engineering, control theory, and other fields. It also requires ongoing research and development to create new methods and tools for building and evaluating these complex systems. Safety and reliability require a holistic approach. They are ongoing challenges for the field. Ethical and societal implications of autonomous systems. The increasing deployment of autonomous systems raises important ethical and societal implications. This section will explore the critical issues surrounding the responsible development and use of autonomous systems, including concerns about job displacement, liability, decision-making authority, and the potential impact on human skills and autonomy. We will also discuss the need for public dialogue and engagement in shaping the future of autonomous systems and ensuring that they are aligned with human values and societal goals. This encourages a thoughtful and responsible approach to the development of autonomous systems. One of the primary concerns is the potential for autonomous systems to displace human workers in various industries, such as transportation, logistics, and manufacturing. While these systems can increase efficiency and productivity, they may also lead to job losses and require significant workforce retraining and adaptation. The impact on employment must be considered. It requires proactive measures to address potential job displacement. Another important issue is the question of liability when autonomous systems make mistakes or cause harm. Determining who is responsible, the manufacturer, the owner, the operator, or the system itself, is a complex legal and ethical challenge. Establishing clear legal frameworks for liability is crucial for the responsible deployment of these technologies. Liability is a complex issue for autonomous systems. It requires new legal and ethical frameworks. The increasing autonomy of these systems also raises questions about decision-making authority and the appropriate balance between human and machine control. In safety-critical applications, such as self-driving cars, it is important to consider when and how human operators should be able to override the system's decisions. Maintaining appropriate human oversight is essential. It requires careful consideration of the roles of humans and machines. The widespread use of autonomous systems may also have broader societal impacts, such as potentially reducing the need for certain human skills and potentially impacting human autonomy and agency. It is important to consider these potential impacts and to design systems that enhance rather than diminish human capabilities. The impact on human skills and autonomy must be considered. We need to design systems that support human flourishing. Addressing these ethical and societal implications requires a broad and inclusive dialogue involving researchers, policymakers, industry leaders, ethicists, and the public. It is important to engage in a thoughtful and informed discussion about the kind of future we want to create with these technologies and to ensure that they are developed and used in a way that aligns with human values and societal goals. Public dialogue and engagement are crucial. They are essential for shaping a positive future with autonomous systems. The future of autonomous systems, towards greater autonomy and integration. The field of autonomous systems is rapidly advancing, with new capabilities and applications emerging at an accelerating pace. This section will explore some of the most promising future directions and emerging trends in autonomous systems, including the development of more sophisticated and general-purpose autonomous systems, the increasing integration of these systems into our daily lives, and the potential for autonomous systems to collaborate and interact with each other in complex, interconnected networks. This provides a glimpse into the future of autonomous systems. One major trend is the development of more sophisticated and general-purpose autonomous systems. While current systems are often designed for specific tasks or environments, researchers are working towards creating systems that can adapt to a wider range of situations and perform multiple tasks, similar to how humans can apply their intelligence and skills across various domains. General-purpose autonomy is a key goal. It is a major challenge for the field. The increasing integration of autonomous systems into our daily lives is another important trend. We are likely to see more autonomous systems in our homes, workplaces, and public spaces, performing tasks such as cleaning, cooking, providing assistance to the elderly or disabled, and managing infrastructure. Autonomous systems will become more integrated into daily life. They will transform the way we live and work. The potential for autonomous systems to collaborate and interact with each other is also a significant area of development. For example, fleets of self-driving cars could communicate and coordinate with each other to optimize traffic flow and avoid collisions. Swarms of drones could work together to perform complex tasks such as search and rescue or environmental monitoring. Collaboration between autonomous systems is a powerful concept. It enables new capabilities and efficiencies. Advances in AI, particularly in areas such as deep reinforcement learning, multi-agent systems, and human-robot interaction, will be crucial for enabling these future developments. Continued progress in sensor technology, computing hardware, and robotics will also play an important role. Advances in AI and related technologies are essential. They will drive the development of more capable autonomous systems. However, realizing the full potential of autonomous systems will also require addressing the technical, ethical, and societal challenges discussed in previous sections. Ensuring the safety, reliability, and trustworthiness of these systems, as well as their alignment with human values and societal goals, will be crucial for their successful integration into our lives. Addressing the challenges is crucial. It is essential for realizing the full potential of autonomous systems. The future of autonomous systems holds immense promise, with the potential to transform industries, improve our quality of life, and create new opportunities for innovation and discovery. As you continue your journey in AI, you will have the opportunity to contribute to these advancements and shape the future of this dynamic field, creating intelligent systems that can interact with the world in increasingly sophisticated and beneficial ways. The possibilities are vast. The future of autonomous systems is full of potential. Lesson 13, Explainable AI, XAI Unraveling the Mysteries of Machine Decisions. Welcome back, discerning learners, to the 13th lesson in our advanced exploration of artificial intelligence. As AI systems, particularly those based on deep learning, become more complex and opaque, the need for transparency and interpretability has become paramount. In this lesson, we venture into the burgeoning field of explainable AI, XAI, which aims to make AI decision-making more understandable to humans. We will explore the motivations behind XAI, examining the challenges of interpreting complex AI models and the benefits of explainability for trust, accountability, and debugging. We will delve into various XAI techniques, including model-agnostic methods like LIME and SHAP, and model-specific approaches like attention mechanisms, and discuss the trade-offs between explainability and accuracy. We will also consider the limitations of current XAI methods and explore future directions in this critical area of AI research. Prepare to unravel the mysteries of machine decisions and discover how XAI is paving the way for more transparent, trustworthy, and human-centered AI systems. The need for explainability, why we need to understand AI decisions. The increasing use of AI in high-stakes domains, such as healthcare, finance, and criminal justice, has brought the issue of explainability to the forefront. This section will explore the motivations behind the growing demand for explainable AI, highlighting the importance of understanding AI decisions for building trust, ensuring accountability, facilitating debugging and improvement, and complying with regulations. We will also discuss the different stakeholders who can benefit from XAI, including developers, users, and regulators. This establishes the importance of XAI in the context of real-world AI applications. As AI systems become more complex and autonomous, understanding how they arrive at their decisions becomes increasingly difficult. This opacity can erode trust in AI, particularly when these systems are used to make decisions that have significant consequences for individuals or society. Explainability is crucial for building trust. It allows users to understand the rationale behind AI decisions. Explainability is also essential for ensuring accountability. When an AI system makes a mistake or produces an undesirable outcome, it is important to be able to understand why that happened in order to assign responsibility, take corrective action, and prevent similar errors in the future. Explainability enables accountability. It helps to identify the causes of errors and assign responsibility. Understanding how an AI system works can also facilitate debugging and improvement. By identifying the factors that influence a model's decisions, developers can gain insights into its strengths and weaknesses, leading to more robust and reliable systems. Explainability aids in debugging and improvement. It provides insights into the model's behavior. In some domains, regulations and guidelines are emerging that require AI systems to be explainable. For example, the European Union's General Data Protection Regulation, GDPR, includes provisions related to the right to an explanation for decisions made by automated systems. Explainability is becoming a legal requirement in some cases. It is driven by regulations like the GDPR. Different stakeholders can benefit from XAI. Developers can use it to understand, debug, and improve their models. Users can use it to understand and trust the decisions made by AI systems. Regulators can use it to ensure that AI systems are fair, transparent, and compliant with relevant laws and guidelines. XAI benefits various stakeholders. It serves different needs and purposes. The challenges of interpreting complex AI models, the black box problem. Despite the clear need for explainability, interpreting complex AI models, particularly deep neural networks, present significant challenges. This section will explore the black box problem of deep learning, discussing the difficulties of understanding the internal representations and decision-making processes of these complex models. We will also examine the trade-offs between model complexity, accuracy, and interpretability, and discuss the challenges of providing explanations that are both faithful to the model and understandable to humans. This highlights the inherent difficulties in achieving explainability. Deep neural networks are often referred to as black boxes because their internal workings are difficult to understand. These models can have millions or even billions of parameters, and their decision-making processes involve complex, nonlinear interactions between these parameters. The black box nature of deep learning poses challenges for explainability. It is difficult to understand how these models arrive at their decisions. The complexity of deep learning models often comes at the cost of interpretability. While simpler models, such as linear regression or decision trees, are relatively easy to understand, they may not be as accurate as more complex models. Finding the right balance between complexity, accuracy, and interpretability is a key challenge in XAI. There is a trade-off between complexity and interpretability. More complex models are often less interpretable. Another challenge is the difficulty of providing explanations that are both faithful to the model and understandable to humans. An explanation that accurately reflects the model's internal computations may be too complex for a human to comprehend. On the other hand, a simplified explanation may not fully capture the nuances of the model's decision-making process. Explanations must be both accurate and understandable. They need to balance fidelity to the model with human comprehensibility. The concept of explainability itself is not always well defined. Different stakeholders may have different needs and expectations regarding explanations. For example, a developer may want a detailed explanation of the model's internal workings, while a user may just want to know the key factors that influenced a particular decision. Defining explainability is challenging. It depends on the context and the audience. Despite these challenges, the field of XAI is making rapid progress. Researchers are developing new techniques and tools for interpreting complex AI models, and the demand for explainability is driving innovation in this area. The challenges of XAI are being actively addressed. There is significant progress being made in the field. Model-agnostic XAI methods. Explaining any model-agnostic XAI methods are techniques that can be used to explain the predictions of any machine learning model, regardless of its internal structure. This section will explore two popular model-agnostic methods, LIME, Local Interpretable Model-Agnostic Explanations, and SHAP, Shapley Additive Explanations. We will examine how these methods work, their strengths and limitations, and their applications in various domains. This introduces versatile techniques for explaining diverse models. LIME aims to explain individual predictions of a complex model by approximating it locally with a simpler, interpretable model, such as a linear model or a decision tree. It works by perturbing the input data point and observing how the model's prediction changes. Based on these perturbations, LIME learns a local, interpretable model that approximates the behavior of the complex model around the data point being explained. LIME provides local explanations. It approximates the complex model with a simpler one around a specific input. SHAP is based on the concept of Shapley values from cooperative game theory. It aims to fairly distribute the credit for a model's prediction among the input features. SHAP values provide a unified measure of feature importance, indicating how much each feature contributed to the prediction compared to the average prediction. SHAP provides a unified measure of feature importance. It is based on game theory principles. Both LIME and SHAP have their strengths and limitations. LIME provides local explanations that are easy to understand but may not be globally consistent. SHAP provides a more global and consistent measure of feature importance but can be computationally expensive for complex models. The choice between LIME and SHAP depends on the specific application. They offer different trade-offs between locality and global consistency. Model-agnostic methods are particularly useful when dealing with black box models, where the internal structure is unknown or too complex to analyze directly. They can be applied to a wide range of models, from deep neural networks to random forests, and support vector machines. Model-agnostic methods are versatile. They can be applied to any machine learning model. These methods have found applications in various domains. In healthcare, they can be used to explain the predictions of diagnostic models, helping clinicians to understand and trust these systems. In finance, they can be used to explain credit scoring or loan approval decisions, providing transparency to customers and regulators. They have many practical applications. They can be used to explain decisions in various fields. Model-specific XAI methods, peeking inside the black box. While model-agnostic methods can be applied to any model, model-specific XAI methods are tailored to specific types of models, such as deep neural networks. This section will explore some of the model-specific techniques used to interpret deep learning models, including visualization techniques, attention mechanisms, and methods for analyzing the learned representations. We will also discuss the challenges of interpreting deep networks and the limitations of current model-specific XAI methods. This delves into techniques tailored for specific model types. Visualization techniques can provide insights into the inner workings of deep neural networks. For example, visualizing the filters learned by convolutional neural networks, CNNs, can reveal the types of features that the network is detecting at different layers. Visualizing the activation patterns of neurons can also help to understand how the network is processing information. Visualization provides insights into learned features. It can reveal what the network is focusing on. Attention mechanisms, which are increasingly used in deep learning models for natural language processing and computer vision, can also provide a form of interpretability. Attention allows the model to focus on specific parts of the input when making a prediction, and the attention weights can be visualized to show which parts of the input were most important. Attention provides a window into the model's focus. It can highlight the most relevant parts of the input. Analyzing the learned representations of deep networks is another approach to understanding their behavior. Techniques such as TSNE can be used to visualize the high-dimensional representations learned by the network in a lower-dimensional space, revealing clusters and relationships between different inputs. Analyzing learned representations can reveal hidden structures. It can provide insights into how the model is organizing information. Despite these techniques, interpreting deep networks remains a significant challenge. The high dimensionality and nonlinearity of these models make it difficult to fully understand their decision-making processes. Furthermore, current model-specific XAI methods often focus on individual components of the network, rather than providing a holistic understanding of the model's behavior. Interpreting deep networks is still challenging. It requires developing more comprehensive and holistic methods. The development of more powerful and interpretable model-specific XAI methods is an active area of research. As deep learning models become more widely used in high-stakes applications, the need for robust and reliable interpretation techniques will only grow. Model-specific XAI is a crucial area of research. It is essential for understanding and trusting complex models. The trade-offs between explainability and accuracy, balancing performance and interpretability. In many applications of AI, there is a perceived trade-off between the accuracy of a model and its interpretability. This section will explore this trade-off, discussing the challenges of developing models that are both highly accurate and easily understandable. We will examine different approaches to managing this trade-off, such as using inherently interpretable models, post-hoc explanation methods, and incorporating explainability constraints during model training. We will also discuss the importance of considering the specific context and needs of the application when choosing an appropriate balance between accuracy and interpretability. This addresses a key challenge in practical XAI development. Simpler, more interpretable models, such as linear regression and decision trees, are often easier to understand than complex models like deep neural networks. However, they may not be able to capture the complex patterns and relationships in the data that are necessary for achieving high accuracy on certain tasks. There is often a trade-off between interpretability and accuracy. Simpler models are easier to understand but may be less accurate. One approach to managing this trade-off is to use inherently interpretable models when possible. For example, if a linear model can achieve acceptable accuracy on a particular task, it may be preferred over a more complex model due to its simplicity and interpretability. Using inherently interpretable models is preferable when possible. It provides a direct and transparent understanding of the model. Another approach is to use post-hoc explanation methods, such as LIME or SHAP, to explain the predictions of a complex, high-accuracy model. This allows for the use of powerful models while still providing some level of interpretability. Post hoc methods provide explanations for complex models. They allow for the use of high-accuracy models while still providing insights. It is also possible to incorporate explainability constraints directly into the model training process. For example, researchers are exploring techniques for training deep neural networks that are encouraged to learn more interpretable representations or to produce explanations along with their predictions. Incorporating explainability constraints during training is a promising direction. It aims to develop models that are both accurate and interpretable. The appropriate balance between accuracy and interpretability depends on the specific application. In some cases, such as medical diagnosis or loan approvals, explainability may be just as important as accuracy, while in other cases, such as image recognition for self-driving cars, accuracy may be the primary concern. The context dictates the appropriate balance. It requires careful consideration of the specific needs and risks. Evaluating explainable AI, assessing the quality of explanations as XAI methods become more prevalent, it is important to have ways to evaluate the quality and effectiveness of the explanations they provide. This section will explore different approaches to evaluating XAI methods, including human evaluation, functional evaluation, and axiomatic evaluation. We will discuss the challenges of evaluating explanations, such as the subjectivity of human judgments and the lack of ground truth, and consider the properties of good explanations, such as fidelity, stability, and comprehensibility. This addresses the crucial issue of assessing explanation quality. Human evaluation involves asking humans to assess the quality of explanations generated by XAI methods. This can involve measuring how well humans understand the explanations, how much they trust the model based on the explanations, and whether the explanations help them to perform a task more effectively. Human evaluation is the most direct way to assess explanation quality. It captures the human perspective on understandability and usefulness. Functional evaluation aims to measure the performance of XAI methods on specific tasks, without requiring human involvement. For example, one could measure how well an explanation helps to identify errors in a model or how well it helps to detect bias. Functional evaluation provides objective measures of explanation quality. It can be automated and scaled more easily than human evaluation. Axiomatic evaluation involves defining a set of desirable properties or axioms that explanations should satisfy and then mathematically verifying whether a given XAI method satisfies these axioms. For example, one might require that explanations be consistent across similar inputs or that they assign importance to features in a way that is consistent with the model's behavior. Axiomatic evaluation provides a formal framework for reasoning about explanation quality. It can help to identify limitations of existing methods. Evaluating explanations is challenging due to the inherent subjectivity of human understanding and the lack of ground truth for what constitutes a good explanation. Different people may have different preferences and needs when it comes to explanations, and what is understandable to one person may be confusing to another. Evaluating explanations is challenging and subjective. It requires careful consideration of the evaluation criteria and methods. Despite these challenges, there is growing agreement on some general properties that good explanations should possess. These include fidelity, the explanation should accurately reflect the model's behavior; stability, similar inputs should receive similar explanations; and comprehensibility, the explanation should be understandable to the intended audience. These properties provide guidelines for developing and evaluating XAI methods. They are important considerations for designing effective explanations. The limitations of current XAI methods, challenges and open problems. While XAI has made significant progress, many challenges and open problems remain. This section will explore some of the limitations of current XAI methods, including the difficulty of providing explanations for complex, high-dimensional models, the potential for explanations to be misleading or manipulated, and the lack of consensus on evaluation metrics and standards. We will also discuss the need for more research into the fundamental principles of explainability and the development of more robust and reliable XAI techniques. This highlights the need for ongoing research and development in XAI. One of the key limitations of current XAI methods is the difficulty of providing explanations for complex, high-dimensional models, such as deep neural networks. While methods like LIME and SHAP can provide local explanations for individual predictions, understanding the global behavior of these models remains a challenge. Explaining complex models is a major challenge. It requires developing new techniques for understanding their global behavior. Another limitation is the potential for explanations to be misleading or manipulated. For example, an adversarial example could be crafted that causes the model to make an incorrect prediction while also generating a plausible explanation for that prediction. This could be used to deceive users or to conceal malicious behavior. Explanations can be misleading or manipulated. It is important to develop robust and trustworthy explanation methods. The lack of consensus on evaluation metrics and standards for XAI is also a challenge. While some general principles of good explanations have been proposed, there is no widely agreed upon set of metrics or benchmarks for comparing different XAI methods. This makes it difficult to assess progress in the field and to determine which methods are most effective for different applications. Standardized evaluation metrics are needed. They are essential for comparing and advancing XAI methods. Many current XAI methods focus on explaining individual predictions rather than providing a deeper understanding of the model's overall behavior or its learned representations. Developing methods that can provide more holistic and comprehensive explanations is an important area for future research. Current methods often provide local explanations. There is a need for more global and comprehensive understanding. Addressing these limitations requires more research into the fundamental principles of explainability, the development of new XAI techniques that are more robust, reliable, and comprehensive, and the establishment of clear evaluation standards and benchmarks. It also requires interdisciplinary collaboration between AI researchers, cognitive scientists, ethicists, and domain experts. Overcoming these limitations requires fundamental research. It is a collaborative and interdisciplinary effort. Explainable AI in practice, applications and case studies. Despite the challenges, XAI is already being applied in various domains, demonstrating its potential to improve the transparency, trustworthiness, and accountability of AI systems. This section will explore some real-world applications and case studies of XAI, showcasing how explainability is being used in practice to enhance decision-making, build trust, and facilitate collaboration between humans and AI. We will examine examples from different sectors, such as healthcare, finance, and law, and discuss the lessons learned from these applications. This showcases the practical value and impact of XAI. In healthcare, XAI is being used to explain the predictions of AI models for diagnosis, prognosis, and treatment planning. For example, XAI techniques have been applied to explain why a deep learning model classified a medical image as cancerous or benign, highlighting the regions of the image that were most influential in the decision. XAI can enhance trust and adoption of AI in healthcare. It can help clinicians understand and validate AI-based diagnoses. In finance, XAI is being used to explain credit scoring and loan approval decisions. By providing explanations for why a particular applicant was approved or denied, financial institutions can increase transparency, comply with regulations, and build trust with customers. XAI can also help to identify and mitigate potential biases in lending decisions. XAI can improve transparency and fairness in finance. It can help to explain and justify automated financial decisions. In the legal domain, XAI is being used to explain the predictions of AI systems used for legal research, document review, and risk assessment. For example, XAI techniques can be used to explain why a particular legal document was deemed relevant to a case or why a particular individual was flagged as high risk. XAI can enhance the use of AI in legal settings. It can provide insights into the reasoning behind AI-driven legal analysis. These are just a few examples of how XAI is being applied in practice. Other applications include explaining decisions in autonomous driving, fraud detection, and customer service. As XAI techniques continue to mature and become more widely adopted, we can expect to see even more applications across various domains. XAI is being applied across various domains. It is demonstrating its value in real-world settings. The lessons learned from these applications highlight the importance of considering the specific needs and expectations of the users when designing XAI systems. They also underscore the need for ongoing evaluation and refinement of XAI methods to ensure that they are providing useful and accurate explanations. Practical applications provide valuable lessons. They inform the development of more effective XAI techniques. The future of explainable AI, towards more transparent and trustworthy AI. The field of explainable AI is rapidly evolving, with ongoing research pushing the boundaries of what's possible and new applications emerging at an accelerating pace. This section will explore some of the most promising future directions and emerging trends in XAI, including the development of more powerful and general-purpose explanation methods, the integration of XAI into the AI development lifecycle, and the increasing focus on human-centered XAI. We will also discuss the potential for XAI to transform the way we interact with and understand AI systems. This provides a glimpse into the future of XAI. One important direction is the development of more powerful and general-purpose XAI methods. While current methods often focus on explaining individual predictions or specific types of models, the goal is to develop techniques that can provide more comprehensive explanations of complex AI systems and that can be applied across a wide range of models and domains. More powerful and general XAI methods are needed. They will enable a deeper understanding of complex AI systems. Another trend is the integration of XAI into the AI development lifecycle. Instead of treating explainability as an afterthought, researchers and developers are starting to incorporate XAI considerations from the outset, designing models and systems with explainability in mind. This can lead to more inherently interpretable models and facilitate ongoing monitoring and improvement of AI systems. Integrating XAI into the development lifecycle is crucial. It promotes a more proactive approach to explainability. Human-centered XAI is an emerging area that focuses on designing XAI systems that are tailored to the needs and cognitive abilities of human users. This involves considering factors such as the user's level of expertise, their specific goals and tasks, and the context in which the explanations will be used. Human-centered XAI aims to create explanations that are not only accurate but also understandable, useful, and actionable for the intended audience. Human-centered XAI is essential for effective communication. It tailors explanations to the needs of the user. The increasing use of AI in decision-making is also driving the need for more robust and reliable XAI methods. As AI systems are deployed in high-stakes domains, it becomes increasingly important to ensure that their decisions can be trusted and that they are aligned with human values and societal norms. XAI can play a crucial role in ensuring the responsible development and deployment of AI. Robust and reliable XAI is crucial for high-stakes applications. It promotes trust and accountability in AI systems. The future of XAI holds immense promise for transforming the way we interact with and understand AI systems. By making AI more transparent, interpretable, and accountable, XAI can help to build trust in these systems, facilitate their adoption, and ensure that they are used in a way that benefits humanity. As you continue your journey in AI, you will have the opportunity to contribute to these advancements and shape the future of this dynamic and impactful field. The future of XAI is bright. It is essential for the responsible development and deployment of AI. Lesson 14, Generative AI, Creating New Realities with Artificial Intelligence. Welcome back, creative minds, to the 14th lesson in our advanced exploration of artificial intelligence. In this lesson, we venture into the fascinating realm of generative AI, a branch of AI that focuses on creating new content, such as images, text, music, and even code. We will explore the key techniques driving generative AI, including generative adversarial networks, GANs, variational autoencoders, VAEs, and autoregressive models, and examine their applications in diverse fields such as art, design, entertainment, and scientific discovery. We will also delve into the challenges and limitations of generative models, including issues of quality, control, and potential misuse. Furthermore, we will discuss the ethical implications of generating synthetic data and the societal impact of AI-generated content. Prepare to explore the frontiers of AI-driven creativity and discover how generative AI is not just mimicking existing data but creating entirely new realities, pushing the boundaries of what's possible with artificial intelligence. The essence of generative AI, from imitation to creation. Generative AI represents a fundamental shift from using AI for analysis and decision-making to using AI for content creation. This section will explore the core concepts of generative AI, highlighting its unique capabilities and contrasting it with other branches of AI. We will also discuss the different types of generative models and the underlying principles that enable them to create novel and realistic outputs. This provides a foundational understanding of generative AI. Unlike discriminative models, which learn to classify or predict based on existing data, generative models learn the underlying structure of the data and can generate new samples that resemble the training data. This ability to create new content opens up a wide range of possibilities, from generating realistic images and text to composing music and designing new products. Generative AI goes beyond analysis. It enables the creation of novel content. Generative adversarial networks, GANs, are one of the most prominent and successful classes of generative models. GANs consist of two networks, a generator and a discriminator, that are trained in an adversarial manner. The generator tries to create realistic data samples, while the discriminator tries to distinguish between real and generated samples. This adversarial training process pushes the generator to produce increasingly realistic outputs. GANs are a powerful framework for generative modeling. They have achieved impressive results in various domains. Variational autoencoders, VAEs, are another important class of generative models. VAEs use a probabilistic approach to learn a latent representation of the data and then use this representation to generate new samples. They are often used for tasks such as image generation, anomaly detection, and data imputation. VAEs offer a probabilistic approach to generative modeling. They can learn a compact representation of the data. Autoregressive models are a class of generative models that generate data sequentially, one element at a time. They are commonly used for text generation, where they can generate coherent and contextually relevant sentences or paragraphs. Recurrent neural networks, RNNs, and transformers are often used as the underlying architecture for autoregressive models. Autoregressive models are well suited for sequential data. They are widely used in natural language processing. Generative models learn from existing data, but they are not simply copying or memorizing it. Instead, they learn the underlying patterns and structures of the data, allowing them to create new content that is similar to, but not identical to, the training data. This ability to generalize and create novel content is what makes generative AI so powerful and versatile. Generative AI learns the essence of the data. It can create new content that is both novel and realistic. Generative adversarial networks, GANs, a game of deception and creation. GANs have emerged as one of the most exciting and influential developments in generative AI, capturing the imagination of researchers and the public alike with their ability to generate strikingly realistic images, videos, and other types of data. This section will delve into the architecture and training dynamics of GANs, exploring the interplay between the generator and discriminator networks. We will examine different variants of GANs, such as conditional GANs and cycle GANs, and discuss their applications in image synthesis, style transfer, and data augmentation. We will also address the challenges of training GANs and the techniques used to stabilize and improve their performance. This provides an in-depth understanding of GANs. A GAN consists of two neural networks, a generator, G, and a discriminator, D. The generator's task is to create synthetic data samples that are indistinguishable from real data, while the discriminator's task is to distinguish between real data samples and those generated by the generator. The two networks are trained simultaneously in a competitive, adversarial process. GNNs are based on a game-theoretic framework. The generator and discriminator compete in a zero-sum game. The training process of a GAN can be viewed as a two-player minimax game. The generator tries to minimize the discriminator's ability to distinguish between real and generated samples, while the discriminator tries to maximize its ability to correctly classify the samples. This dynamic leads to a gradual improvement in the generator's ability to create realistic data. The adversarial training process drives the generator's improvement. It leads to increasingly realistic outputs. Conditional GANs, CGANs, extend the basic GAN framework by conditioning both the generator and the discriminator on some additional information, such as class labels or text descriptions. This allows for more control over the generated output, enabling the generation of specific types of data. CGANs enable conditional generation. They provide more control over the generated output. Cycle GANs are another important variant that can learn to translate images from one domain to another without paired training examples. For example, a cycle GAN can learn to translate a photograph into a painting in the style of Monet, or vice versa. Cycle GANs enable unpaired image-to-image translation. They can learn mappings between different domains. Training GANs can be challenging due to issues such as mode collapse, where the generator produces only a limited variety of samples, and instability during training. Researchers have developed various techniques to address these challenges, including modifications to the network architecture, the loss function, and the training procedure. Training GANs requires careful tuning and specialized techniques. It is an active area of research. GANs have found numerous applications, including generating realistic images of faces, objects, and scenes, performing style transfer, where the style of one image is applied to another, and augmenting datasets for training other machine learning models. They have also been used in scientific applications, such as generating images of galaxies and simulating particle physics events. GANs have diverse applications. They are a powerful tool for image generation and manipulation. Variational autoencoders, VAEs, probabilistic latent variable models for generation. While GANs have dominated the headlines in generative AI, variational autoencoders, VAEs, offer a different, probabilistic approach to generative modeling. This section will explore the architecture and principles of VAEs, highlighting their ability to learn a latent representation of the data and generate new samples by sampling from this latent space. We will examine the key components of a VAE, including the encoder, decoder, and the reparameterization trick, and discuss the applications of VAEs in image generation, anomaly detection, and representation learning. We will also compare and contrast VAEs with GANs, highlighting their respective strengths and weaknesses. This introduces a different approach to generative modeling. VAEs are a type of generative model that combines elements of autoencoders and variational inference. An autoencoder consists of an encoder network that maps the input data to a lower-dimensional latent representation, and a decoder network that reconstructs the one input data from the latent representation. VAEs extend this idea by introducing a probabilistic interpretation of the latent space. VAEs learn a probabilistic mapping. They combine autoencoders with variational inference. In a VAE, the encoder network outputs the parameters of a probability distribution over the latent space, typically a Gaussian distribution. The decoder network then takes a sample from this distribution as input and reconstructs the input data. The VAE is trained to maximize the likelihood of the data under this generative process, while also regularizing the latent space to ensure that it has desirable properties. VAEs learn a distribution over the latent space. They can generate new samples by sampling from this distribution. The reparameterization trick is a key technique used in training VAEs. It allows gradients to be backpropagated through the sampling process by expressing the latent variable as a deterministic function of the input and a noise variable. This enables the VAE to be trained end-to-end using standard gradient-based optimization methods. The reparameterization trick is crucial for training VAEs. It enables gradient-based optimization. VAEs have several advantages over traditional autoencoders. They can generate new data samples by sampling from the learned latent distribution, and they tend to learn more robust and meaningful latent representations. However, they can also produce blurry or less sharp images compared to GANs. VAEs have unique advantages. They offer a probabilistic approach to generative modeling. VAEs have found applications in various domains. In image generation, they can be used to create new images of faces, objects, and scenes. In anomaly detection, they can be used to identify unusual data points that do not conform to the learned distribution. They can also be used for representation learning, where the learned latent representation is used as input to other machine learning models. VAEs have diverse applications. They are a versatile tool for generative modeling and representation learning. Autoregressive models, generating sequences one step at a time. Autoregressive models are a class of generative models that generate data sequentially, one element at a time, conditioning each element on the previously generated elements. This section will explore the principles of autoregressive models and their applications in generating sequences such as text, audio, and music. We will examine how recurrent neural networks, RNNs, particularly LSTMs, and more recently, transformer networks, are used to build powerful autoregressive models. We will also discuss the challenges of generating long, coherent sequences and the techniques used to improve the quality and diversity of generated outputs. This introduces a powerful approach for sequence generation. Autoregressive models decompose the probability of a sequence into a product of conditional probabilities, where each element in the sequence is conditioned on the previous elements. For example, in text generation, an autoregressive model might generate a sentence one word at a time, with each word being conditioned on the previously generated words. Autoregressive models generate sequences step by step. They condition each element on the preceding elements. RNNs, particularly LSTMs, have been widely used for building autoregressive models. The recurrent nature of RNNs allows them to maintain a hidden state that summarizes the previously generated elements, which is then used to predict the next element in the sequence. RNNs can capture long-range dependencies in sequences. They are well suited for autoregressive modeling. More recently, transformer networks have emerged as a powerful alternative to RNNs for sequence modeling. Transformers use self-attention mechanisms to capture relationships between different elements in the sequence, allowing them to model long-range dependencies more effectively than RNNs. They have achieved state-of-the-art results in various sequence generation tasks. Transformers are powerful sequence models. They have achieved impressive results in autoregressive generation. Generating long, coherent sequences is a major challenge for autoregressive models. Small errors or inconsistencies early in the generation process can accumulate and lead to incoherent or nonsensical outputs. Techniques such as beam search, which maintains multiple candidate sequences during generation, and nucleus sampling, which samples from a restricted set of high-probability tokens, can help to improve the quality and coherence of generated sequences. Generating long, coherent sequences is challenging. It requires specialized techniques to maintain quality and consistency. Autoregressive models have numerous applications. In natural language processing, they are used for text generation, machine translation, and dialogue generation. In music generation, they can be used to compose new melodies and harmonies. They can also be used to generate audio waveforms, images, and even code. Autoregressive models have diverse applications. They are a powerful tool for sequence generation. Generative AI for images and video, creating and manipulating visual content. Generative AI has made remarkable progress in generating and manipulating visual content, enabling the creation of realistic images and videos that are difficult to distinguish from real ones. This section will explore the applications of generative models, such as GANs and VAEs, in image and video synthesis, editing, and manipulation. We will examine techniques for generating high-resolution images, creating deepfakes, performing style transfer, and generating video sequences. We will also discuss the potential impact of these technologies on art, entertainment, and other creative industries. This showcases the power of generative AI in visual content creation. GANs have demonstrated impressive capabilities in generating high-resolution, realistic images. Models such as StyleGAN and BigGAN can generate images of faces, objects, and scenes that are often indistinguishable from real photographs. These models have learned to capture the intricate details and statistical regularities of natural images. GANs can generate highly realistic images. They have set new standards for image synthesis. Generative models can also be used for image editing and manipulation. For example, they can be used to change the appearance of a person's face in an image, such as altering their age, expression, or hairstyle. They can also be used to paint missing or damaged parts of an image, or to enhance the resolution and quality of an image. Generative AI enables advanced image editing. It can manipulate and enhance images in various ways. Deepfakes, which are synthetic videos created by manipulating or generating facial images, are another application of generative AI that has gained significant attention. While deepfakes have raised concerns about their potential for misuse in spreading misinformation or creating non-consensual pornography, they also have potential applications in entertainment and filmmaking. Deepfakes are a powerful but controversial application. They raise ethical concerns but also offer creative possibilities. Style transfer is a technique that uses generative models to apply the style of one image to the content of another image. For example, a photograph can be transformed into a painting in the style of Van Gogh or Picasso. Style transfer has become a popular tool for artistic expression and creativity. Style transfer enables artistic image manipulation. It can create visually stunning and unique images. Generative models can also be used to generate video sequences. This is a more challenging task than image generation, as it requires maintaining temporal consistency and coherence across frames. However, recent advances in video generation models have shown promising results in generating short, realistic video clips. Video generation is a challenging but promising area. It has potential applications in entertainment and simulation. The advancements in generative AI for images and video are transforming creative industries, enabling new forms of artistic expression, and creating new possibilities for visual content creation. However, they also raise important ethical and societal questions, which we will discuss in a later section. Generative AI is transforming visual content creation. It is enabling new forms of creativity and expression. Generative AI for text and language, writing and transforming text with AI. Generative AI is also making significant strides in the domain of text and language, enabling machines to generate coherent and contextually relevant text, translate between languages, and even write creative stories or articles. This section will explore the applications of generative models, such as autoregressive models based on RNNs and transformers, in text generation, machine translation, and other language-related tasks. We will examine how these models can be used to create new forms of written content, automate writing tasks, and enhance human creativity. This highlights the power of generative AI in natural language processing. Autoregressive models, particularly those based on transformer networks, have achieved remarkable results in text generation. Models such as GPT-3 and its successors can generate long, coherent, and contextually relevant text passages that are often difficult to distinguish from human-written text. These models have learned to capture the statistical regularities of language and can generate text in various styles and formats. Transformer-based models have revolutionized text generation. They can produce remarkably human-like text. Generative models can be used for various text generation tasks, such as writing articles, stories, poems, and even code. They can also be used to generate dialogue for chatbots and virtual assistants, or to create personalized content for marketing and advertising. Generative AI can automate and enhance writing tasks. It can create new forms of written content. Machine translation is another area where generative models are having a significant impact. Neural machine translation (NMT) systems, which typically use sequence-to-sequence models with attention mechanisms, have achieved state-of-the-art results in translating between different languages. NMT can produce more fluent and accurate translations compared to previous statistical machine translation systems. Generative AI is transforming machine translation. It enables more accurate and natural translations. Generative models can also be used for text transformation tasks, such as paraphrasing, summarization, and style transfer. For example, a model can be trained to rewrite a sentence in a different style, such as converting formal language to informal language, or to summarize a long document into a shorter, more concise version. Generative AI can manipulate and transform text. It can perform tasks such as paraphrasing and summarization. The advancements in generative AI for text and language have the potential to transform the way we write, communicate, and consume information. They can automate many writing tasks, enhance human creativity, and enable new forms of human-machine interaction. However, they also raise important ethical questions, which we will discuss later. Generative AI is transforming the way we interact with language. It has the potential to enhance and augment human communication. Generative AI in music and art, creating and inspiring artistic expression. Generative AI is not limited to images, videos, and text, it is also making inroads into the realms of music and art, enabling new forms of creative expression and pushing the boundaries of artistic exploration. This section will explore how generative models are being used to compose music, generate novel melodies and harmonies, and create visual art in various styles. We will also discuss the potential of generative AI to assist and inspire human artists, as well as the philosophical questions surrounding AI-generated art and its impact on human creativity. This reveals how AI can augment and transform artistic creation. Generative models, such as RNNs and transformers, can be trained on large datasets of music to learn the underlying patterns and structures of musical composition. These models can then be used to generate new musical pieces, either from scratch or by providing a starting point or a set of constraints. AI can compose music in various styles. It can generate novel melodies, harmonies, and rhythms. Several AI-powered music generation systems have been developed, such as Google's Magenta project and OpenAI's MuseNet. These systems can generate music in various styles, from classical to jazz to pop, and can even collaborate with human musicians in real-time performances. AI-powered music generation is a growing field. It is enabling new forms of musical creativity. Generative AI is also being used to create visual art. It is leading to new forms of artistic collaboration. The impact of generative AI on the art world is likely to be profound. As these technologies become more accessible and sophisticated, we can expect to see even more innovative and groundbreaking applications of AI in art and music, further blurring the lines between human and machine creativity. Generative AI is transforming the art world. It is creating new possibilities for artistic creation and consumption. Challenges and limitations of generative AI: quality, control, and bias. While generative AI has made impressive progress, it also faces significant challenges and limitations. This section will explore some of the key challenges in developing and deploying generative models, including issues of quality, control, and potential biases. We will examine the difficulty of evaluating the quality of generated outputs, the challenges of controlling the generation process to achieve specific outcomes, and the potential for generative models to reflect and amplify biases present in the training data. This provides a critical perspective on the limitations of generative AI. One of the main challenges in generative AI is ensuring the quality and realism of the generated outputs. While models like GANs can generate impressive results, they can also produce outputs that are flawed, unrealistic, or nonsensical. Evaluating the quality of generated outputs is often subjective and can be difficult to automate. Ensuring the quality of generated content is challenging. It requires careful evaluation and refinement of the models. Controlling the generation process to achieve specific outcomes is another challenge. While some models, like conditional GANs, offer some degree of control, it remains difficult to precisely specify the desired attributes of the generated output or to guide the generation process in a fine-grained manner. Controlling the generation process is difficult. It is an active area of research. Generative models can also reflect and amplify biases present in the training data. For example, a model trained on a dataset of images that underrepresents certain demographic groups may generate outputs that are biased against those groups. Addressing bias in generative models is crucial for ensuring fairness and avoiding harmful stereotypes. Generative models can perpetuate biases. It is important to address these biases in the training data and the models themselves. The computational cost of training and deploying large generative models is also a significant limitation. Models like GPT-3 and large GANs require massive computational resources and energy consumption, which can limit their accessibility and raise environmental concerns. The computational cost of generative AI is significant. It has implications for accessibility and sustainability. Despite these challenges, researchers are actively working on developing new techniques and architectures to improve the quality, controllability, and fairness of generative models. Progress in this area will be crucial for realizing the full potential of generative AI across various domains. Addressing these challenges is crucial. It is essential for the responsible development and deployment of generative AI. Ethical implications of generative AI, deepfakes, misinformation, and creative ownership. The increasing capabilities of generative AI raise important ethical implications, particularly concerning the potential for misuse and the societal impact of AI-generated content. This section will explore the ethical concerns surrounding generative AI, including the creation of deepfakes and the spread of misinformation, the impact on creative industries and the concept of authorship, and the need for responsible development and deployment of these technologies. This encourages a thoughtful and ethical approach to generative AI. Deepfakes, which are synthetic media created using generative AI, have raised significant concerns about their potential for misuse. Deepfakes can be used to create realistic but fabricated videos of people saying or doing things they never actually said or did, which can be used for malicious purposes such as spreading misinformation, damaging reputations, or perpetrating fraud. Deepfakes pose a serious threat. They can be used to deceive and manipulate. The ease with which generative AI can create realistic and convincing content also raises concerns about the spread of misinformation and the erosion of trust in media. As it becomes increasingly difficult to distinguish between real and AI-generated content, the potential for deception and manipulation grows. Generative AI can exacerbate the problem of misinformation. It requires new methods for detecting and countering synthetic media. The impact of generative AI on creative industries and the concept of authorship is another important ethical consideration. As AI becomes more capable of generating art, music, and other forms of creative content, questions arise about the ownership and value of these creations. Who owns the copyright to an AI-generated artwork? How should we value AI-generated content compared to human-created content? Generative AI challenges traditional notions of authorship. It raises questions about ownership and the value of creative work. The responsible development and deployment of generative AI require careful consideration of these ethical implications. This includes developing techniques for detecting and labeling AI-generated content, educating the public about the capabilities and limitations of these technologies, and establishing ethical guidelines and best practices for their use. Responsible development and deployment are crucial. They require a proactive approach to addressing ethical concerns. Addressing these ethical challenges requires a multidisciplinary approach, involving not only technical solutions but also broader societal discussions about the values we want to embed in these systems and the kind of future we want to create with them. It requires collaboration between researchers, policymakers, ethicists, and the public. We must shape the future of generative AI responsibly. It is a collective responsibility. The future of generative AI, towards new frontiers of creativity and innovation. Generative AI is a rapidly evolving field, with new techniques and applications emerging at an accelerating pace. This section will explore some of the most promising future directions and emerging trends in generative AI, including the development of more powerful and versatile generative models, the integration of generative AI with other areas of AI and beyond, and the potential for generative AI to transform various industries and aspects of our lives. This provides a glimpse into the future of generative AI. One major trend is the development of larger and more powerful generative models. Models like GPT-3 have demonstrated the potential of scaling up generative models to billions of parameters, resulting in improved performance and more diverse capabilities. We can expect to see even larger and more sophisticated models in the future. Larger and more powerful models are on the horizon. They will push the boundaries of what's possible with generative AI. Another important direction is the development of more controllable and customizable generative models. This involves giving users more fine-grained control over the generation process, allowing them to specify desired attributes, styles, or constraints. It also involves developing models that can be easily adapted or fine-tuned for specific tasks or domains. Controllability and customization are key areas of research. They will make generative AI more useful and adaptable. The integration of generative AI with other areas of AI, such as reinforcement learning and robotics, is a promising area of research. For example, generative models can be used to create simulated environments for training reinforcement learning agents, or to enable robots to imagine and plan future actions. Integrating generative AI with other AI fields can lead to new capabilities. It can create more powerful and versatile AI systems. Generative AI also has the potential to transform various industries, from entertainment and design to scientific discovery and education. For example, generative models could be used to create personalized educational content, assist in drug discovery by generating novel molecules, or help design new materials with specific properties. Generative AI can transform various industries. It has the potential to revolutionize many aspects of our lives. Finally, the increasing accessibility of generative AI tools and platforms is likely to democratize the use of these technologies, empowering individuals and organizations to create and innovate in new ways. As generative AI becomes more user-friendly and accessible, we can expect to see a flourishing of creativity and innovation across various domains. The democratization of generative AI is an important trend. It will empower more people to create and innovate with AI. The future of generative AI is bright, with many exciting research directions and potential applications on the horizon. As you continue your journey in AI, you will have the opportunity to contribute to these advancements and shape the future of this dynamic field, creating intelligent systems that can generate new realities and push the boundaries of human creativity and innovation. The possibilities are vast. The future of generative AI is full of potential. Lesson 15: Multi-Agent Systems, Coordination, Cooperation, and Competition Among Agents. Welcome back, collaborative learners, to the 15th lesson in our Advanced Course to Artificial Intelligence series. In this lesson, we venture into the fascinating domain of multi-agent systems, MAS, where multiple autonomous agents interact with each other and their environment to achieve individual or common goals. We will explore the fundamental concepts of MAS, including agent architectures, communication protocols, and coordination mechanisms. We will examine different types of multi-agent interactions, such as cooperation, competition, and negotiation, and discuss how these interactions can give rise to complex collective behaviors. We will also delve into various applications of MAS, including distributed problem solving, resource allocation, and modeling social systems. Furthermore, we will discuss the challenges of designing and analyzing MAS, such as the difficulty of predicting emergent behavior and the need for robust and adaptive coordination mechanisms. Prepare to discover how MAS provide a powerful framework for understanding and building complex systems composed of multiple interacting entities, and how they are enabling new approaches to solving problems in distributed, dynamic, and uncertain environments. Introduction to Multi-Agent Systems, Agents, Environments, and Interactions. Multi-agent systems, MAS, are systems composed of multiple interacting intelligent agents. This section will introduce the fundamental concepts of MAS, defining what constitutes an agent and how agents interact with each other and their environment. We will discuss the key characteristics of MAS, such as autonomy, situatedness, and social ability, and explore the different types of agent architectures. We will also examine the various forms of interaction that can occur in MAS, including communication, coordination, cooperation, competition, and negotiation. This sets the stage for understanding the core principles of MAS. An agent is an autonomous entity that can perceive its environment through sensors and act upon that environment through actuators to achieve its goals. In a multi-agent system, multiple agents coexist and interact with each other, either directly or indirectly through the environment. Agents are autonomous entities that perceive and act. In MAS, multiple agents interact with each other and their environment. Agents in a MAS can have different characteristics. They can be homogeneous, with the same capabilities and goals, or heterogeneous, with different capabilities and goals. They can be cooperative, working together to achieve a common goal, or competitive, pursuing their own individual goals, which may conflict with those of other agents. Agents can also be self-interested or altruistic. Agents in a MAS can have different characteristics. They can be homogeneous or heterogeneous, cooperative or competitive. Agent architectures define the internal structure of an agent and how it processes information, makes decisions, and interacts with the world. Common agent architectures include reactive architectures, where agents respond directly to sensory inputs without maintaining internal state, deliberative architectures, where agents reason about their beliefs, goals, and plans, and hybrid architectures, which combine reactive and deliberative elements. Agent architectures define how agents process information and make decisions. They can be reactive, deliberative, or hybrid. Interactions between agents can take various forms. Communication is a fundamental form of interaction, where agents exchange information using a predefined language or protocol. Coordination involves organizing the agent's activities to achieve a common goal, while cooperation involves agents working together to achieve a shared objective. Competition arises when agents have conflicting goals, and negotiation involves agents trying to reach an agreement through a process of offers and counteroffers. Interactions between agents can take many forms. Communication, coordination, cooperation, competition, and negotiation are key types of interaction. Multi-agent systems provide a powerful framework for modeling and building complex systems in various domains. They are particularly well suited for applications that involve distributed problem solving, decentralized control, and the modeling of social and economic systems. MAS provide a powerful framework for complex systems. They are well suited for distributed and decentralized problems. Agent architectures, designing the internal structure of intelligent agents. The architecture of an agent defines its internal structure, how it processes information, makes decisions, and interacts with its environment. This section will explore different agent architectures, including reactive architectures, deliberative architectures, and hybrid architectures. We will discuss the strengths and limitations of each approach and examine how they are suited to different types of tasks and environments. We will also introduce the concept of belief desire intention, BDI, architectures, which provide a framework for modeling rational agents. This examines how agents are designed internally. Reactive architectures are the simplest type of agent architecture. Agents based on this architecture do not maintain internal state or models of the world but instead react directly to their sensory inputs. They use simple rules or mappings from percepts to actions. Reactive architectures are simple and fast. They react directly to sensory inputs without internal state. Reactive architectures are well suited for tasks that require fast, reflexive responses, such as avoiding obstacles or following a line. However, they are limited in their ability to handle complex tasks that require planning or reasoning about the future. Reactive architectures are good for fast, reflexive tasks. They are limited in their ability to handle complex tasks. Deliberative architectures, on the other hand, involve more complex reasoning and planning processes. Agents based on this architecture maintain internal models of the world, reason about their beliefs and goals, and plan sequences of actions to achieve their goals. Deliberative architectures are more powerful but can be slower and more computationally expensive than reactive architectures. Deliberative architectures involve reasoning and planning. They maintain internal models of the world and plan actions. Hybrid architectures combine reactive and deliberative elements to leverage the strengths of both approaches. For example, an agent might use a reactive layer for low-level control and a deliberative layer for high-level planning and decision-making. Hybrid architectures are common in complex agents. Hybrid architectures combine reactive and deliberative elements. They leverage the strengths of both approaches. The belief desire intention, BDI, architecture is a popular framework for modeling rational agents. BDI agents maintain beliefs about the world, desires or goals they want to achieve, and intentions, which are commitments to specific courses of action. BDI agents reason about their beliefs, desires, and intentions to select appropriate actions. BDI architectures model rational agents. They represent beliefs, desires, and intentions explicitly. The choice of agent architecture depends on the specific task and environment. Simple, reactive architectures may be sufficient for simple tasks in static environments, while more complex, deliberative architectures may be necessary for tasks that require planning and reasoning in dynamic and uncertain environments. The choice of architecture depends on the task and environment. Different architectures are suited for different types of problems. Communication and coordination in MAS, enabling agents to work together in many multi-agent systems. Agents need to communicate and coordinate their actions to achieve their goals. This section will explore different approaches to communication and coordination in MAS. We will discuss agent communication languages, such as KQML and FIPA-ACL, and examine different coordination mechanisms, including centralized coordination, distributed coordination, and market-based mechanisms. We will also explore the challenges of designing effective communication and coordination protocols for MAS. This examines how agents communicate and coordinate. Communication is a fundamental aspect of multi-agent systems. Agents often need to exchange information to coordinate their actions, share knowledge, or negotiate with each other. Agent communication languages provide a standardized way for agents to communicate, regardless of their internal architectures or programming languages. Communication enables agents to share information and coordinate. Agent communication languages provide a standardized way to communicate. KQML, Knowledge Query and Manipulation Language, and FIPA-ACL, Foundation for Intelligent Physical Agents, Agent Communication Language, are two examples of agent communication languages. These languages define a set of performatives or speech acts, such as inform, request, and query, that agents can use to communicate their intentions and exchange information. KQML and FIPA-ACL are examples of agent communication languages. They define performatives for agent communication. Coordination is the process of organizing the activities of multiple agents to achieve a common goal. Coordination can be centralized, where a single agent or coordinator makes decisions for the entire system, or distributed, where agents make decisions independently but take into account the actions and intentions of other agents. Coordination organizes agent activities. It can be centralized or distributed. Market-based mechanisms, such as auctions and contract nets, provide a way for agents to coordinate their actions in a decentralized manner. In these mechanisms, agents can bid for resources or tasks, and the allocation is determined based on the bids. Market-based mechanisms are a decentralized approach to coordination. They use auctions and contract nets to allocate resources and tasks. Designing effective communication and coordination protocols for MAS is a challenging task. The protocols need to be efficient, robust, and scalable, and they need to take into account the specific characteristics of the agents and the environment. They also need to address issues such as trust, security, and privacy. Designing effective communication and coordination protocols is challenging. It requires considering efficiency, robustness, and security. Coordination and communication are essential for many MAS applications, including distributed problem-solving, multi-robot systems, and automated negotiation. As the complexity and scale of MAS increase, the need for more sophisticated and adaptive communication and coordination mechanisms will continue to grow. Coordination and communication are essential for MAS. They enable agents to work together effectively. Cooperation and competition in MAS, balancing individual and collective goals. Multi-agent systems can involve agents with different goals and motivations, leading to cooperative or competitive interactions. This section will explore the dynamics of cooperation and competition in MAS, examining how agents can work together to achieve common goals or compete with each other to achieve individual goals. We will discuss different approaches to fostering cooperation, such as team formation and task allocation, and explore different models of competition, such as zero-sum games. We will also examine the concept of Nash equilibrium and its relevance to MAS. This examines the interplay of cooperation and competition in MAS. In cooperative MAS, agents work together to achieve a shared goal. Cooperation often requires agents to coordinate their actions, share information, and potentially sacrifice their individual interests for the benefit of the group. Cooperation is essential for many MAS applications, such as distributed problem-solving, multi-robot coordination, and collaborative filtering. Cooperation involves agents working together towards a common goal. It requires coordination and potentially sacrificing individual interests. Team formation is an important aspect of cooperative MAS, where agents need to form teams or coalitions to effectively achieve their goals. This can involve selecting agents with complementary skills or resources, assigning roles and responsibilities, and establishing communication and coordination protocols. Team formation is crucial for effective cooperation. It involves selecting agents with complementary skills and establishing coordination protocols. Task allocation is another key aspect of cooperative MAS, where tasks or subgoals need to be allocated among the agents in a way that maximizes the overall performance of the team. This can involve considering factors such as agent capabilities, resource availability, and task dependencies. Task allocation distributes tasks among agents. It aims to maximize overall team performance. In competitive MAS, agents have conflicting goals and may compete with each other to achieve their individual objectives. Competition can arise in various contexts, such as resource allocation, auctions, and games. Game theory provides a powerful framework for analyzing competitive interactions and predicting the behavior of rational agents. Competition arises when agents have conflicting goals. Game theory provides tools for analyzing competitive interactions. Zero-sum games are a specific type of competitive interaction where the total payoff to all agents is constant, meaning that one agent's gain is another agent's loss. Many classic games, such as chess and checkers, can be modeled as zero-sum games. In zero-sum games, one agent's gain is another's loss. They are a specific type of competitive interaction. The Nash equilibrium is a fundamental concept in game theory that describes a stable state in a game where no player can benefit by unilaterally changing their strategy, given the strategies of the other players. In a Nash equilibrium, each player's strategy is a best response to the strategies of the other players. The Nash equilibrium 1 describes a stable state in a game. No player can benefit by unilaterally changing their strategy. Understanding the dynamics of cooperation and competition is crucial for designing effective multi-agent systems. By carefully considering the incentives and motivations of the agents, as well as the mechanisms for communication and coordination, it is possible to create MAS that can achieve complex goals and exhibit robust and adaptive behavior. Understanding cooperation and competition is crucial for designing effective MAS. It involves considering agent incentives and coordination mechanisms. Negotiation and argumentation in MAS, reaching agreements and resolving conflicts. Negotiation and argumentation are essential capabilities for agents in many multi-agent systems, enabling them to reach agreements, resolve conflicts, and make joint decisions. This section will explore different approaches to negotiation and argumentation in MAS, including automated negotiation techniques, such as auctions and bargaining, and argumentation-based communication, where agents exchange arguments to persuade each other or to reach a consensus. We will also discuss the challenges of designing negotiation and argumentation protocols that are fair, efficient, and robust. This examines how agents can negotiate and argue. Negotiation is the process by which agents with potentially conflicting interests try to reach an agreement. Automated negotiation techniques allow agents to negotiate autonomously, without human intervention. Automated negotiation enables agents to reach agreements autonomously. It is used in various applications like e-commerce and resource allocation. Auctions are a common mechanism for automated negotiation, particularly in settings where resources or tasks need to be allocated among multiple agents. Different auction protocols, such as English auctions, Dutch auctions, and Vickrey auctions, have different properties in terms of efficiency, fairness, and strategic behavior. Auctions are a common mechanism for automated negotiation. Different protocols have different properties. Bargaining is another form of negotiation where agents make offers and counteroffers until an agreement is reached. Bargaining models, such as the Rubinstein bargaining model, can be used to analyze the strategic aspects of negotiation and to predict the likely outcomes of negotiation processes. Bargaining involves making offers and counteroffers. It can be analyzed using formal models. Argumentation-based communication allows agents to exchange arguments for and against different options or beliefs. This can be a powerful way for agents to persuade each other, to resolve conflicts, or to reach a consensus. Argumentation frameworks provide a formal way to represent and reason about arguments and their relationships. Argumentation allows agents to exchange and evaluate arguments. It can be used for persuasion, conflict resolution, and consensus building. Designing negotiation and argumentation protocols that are fair, efficient, and robust is a challenging task. The protocols need to take into account the strategic behavior of the agents, the potential for deception or manipulation, and the computational complexity of the negotiation or argumentation process. This examines how agents can learn in multi-agent settings. Multi-agent reinforcement learning, MARL, is an extension of reinforcement learning to settings with multiple agents. In MARL, each agent learns a policy that maximizes its own cumulative reward, while taking into account the actions and potential learning of other agents. MARL extends reinforcement learning to multiple agents. Each agent learns a policy while considering the actions of others. One challenge in MARL is the non-stationarity of the environment from the perspective of each individual agent. As other agents learn and change their policies, the environment appears to change from the perspective of any single agent, making it difficult to learn a stable policy. The non-stationarity of the environment is a key challenge in MARL. It arises from the concurrent learning of multiple agents. Another challenge is the difficulty of coordinating learning among multiple agents. If each agent learns independently, they may end up with incompatible policies or may interfere with each other's learning. Techniques such as centralized learning, where a single controller learns a joint policy for all agents, or decentralized learning, where agents share information or coordinate their learning processes, can help to address this challenge. Coordinating learning among multiple agents is challenging. Centralized or decentralized learning can be used. Evolutionary algorithms can also be applied to learning in MAS. In this approach, a population of agents is evolved over time, with the fittest agents being selected to reproduce and pass on their traits to the next generation. Evolutionary algorithms can be used to evolve both individual agent behaviors and collective strategies. Evolutionary algorithms can evolve agent populations over time. They can learn both individual and collective behaviors. Learning from communication is another important aspect of learning in MAS. Agents can learn from each other by exchanging information, sharing experiences, or providing advice. This can speed up the learning process and allow agents to benefit from the knowledge and experience of others. Learning from communication enables agents to learn from each other. It can accelerate learning and improve performance. Learning in multi-agent systems is a complex and challenging problem, but it is also crucial for developing MAS that can adapt to dynamic environments, interact effectively with other agents, and improve their performance over time. As multi-agent systems become more prevalent, the need for effective and efficient multi-agent learning algorithms will only continue to grow. Learning is crucial for adaptive MAS. It is an active area of research with many open challenges. Game theory and multi-agent systems. Analyzing strategic interactions. Game theory is a branch of mathematics that studies strategic interactions between rational agents. This section will explore the connections between game theory and multi-agent systems, examining how game-theoretic concepts such as Nash equilibrium, Pareto efficiency, and the prisoner's dilemma can be used to analyze and design MAS. We will also discuss different types of games, including normal-form games and extensive-form games, and their relevance to MAS. This examines the use of game theory to understand strategic interactions in MAS. Game theory provides a formal framework for modeling and analyzing situations where multiple agents interact and their actions affect each other's outcomes. It has been widely used in economics, political science, biology, and computer science, and it is particularly relevant to the study of multi-agent systems. Game theory models strategic interactions between agents. It is highly relevant to multi-agent systems. Game theory and multi-agent systems, analyzing strategic interactions. Continued, normal-form games, also known as strategic-form games, are a basic representation in game theory. They are typically represented by a matrix that shows the players, strategies, and payoffs. Each player chooses a strategy, and the combination of strategies chosen by all players determines the outcome and the payoffs for each player. Normal-form games are a basic representation in game theory. They are represented by a matrix of players, strategies, and payoffs. Extensive-form games are a more detailed representation that includes the order of moves in a game, the information available to each player at each decision point, and the probabilities of any chance events. Extensive-form games can be represented by a game tree, where each node represents a decision point, each branch represents an action, and each leaf represents an outcome. Extensive-form games model the order of moves and information available. They can be represented by a game tree. The Nash equilibrium is a fundamental concept in game theory. It is a set of strategies, one for each player, such that no player can benefit by unilaterally changing their strategy, given the strategies of the other players. In other words, each player's strategy is one of best response to the strategies of the other players. The Nash equilibrium is a stable state in a game. No player can benefit by unilaterally deviating from their strategy. Pareto efficiency is another important concept in game theory. An outcome is Pareto efficient if there is no other outcome that would make at least one player better off without making any other player worse off. In other words, a Pareto efficient outcome is one where it is impossible to improve one player's payoff without hurting another player. Pareto efficiency is about maximizing overall welfare. It is an outcome where no player can be made better off without making another worse off. The Prisoner's Dilemma is a classic example of a game that illustrates the tension between individual rationality and collective well-being. In this game, two prisoners are interrogated separately and each has the choice to cooperate with the other prisoner or to defect. The Nash equilibrium of the game is for both prisoners to defect, even though they would both be better off if they cooperated. The Prisoner's Dilemma illustrates the tension between individual and collective interests. It shows how individually rational choices can lead to suboptimal outcomes. Game theory provides valuable tools for analyzing and designing multi-agent systems. By understanding the strategic interactions between agents, it is possible to design systems that incentivize desirable behaviors, promote cooperation, and avoid undesirable outcomes such as deadlock or instability. Game theory provides tools for analyzing strategic interactions in MAS. It helps to design systems that incentivize desirable behaviors. Applications of multi-agent systems, from distributed problem-solving to social simulation. Multi-agent systems, MAS, have been applied to a wide range of real-world problems, from distributed control and resource allocation to social simulation and electronic commerce. This section will explore some of the key applications of MAS, showcasing the versatility and power of the multi-agent approach. We will examine how MAS can be used to solve complex problems in a decentralized and adaptive manner, and how they can provide insights into the behavior of social and economic systems. This highlights the diverse applications of MAS. One important application of MAS is in distributed problem solving, where a group of agents work together to solve a problem that is too complex or too large to be solved by a single agent. For example, in distributed sensor networks, multiple sensor agents can cooperate to monitor an area, share information, and coordinate their actions to achieve a common goal, such as tracking a target or detecting an event. MAS can be used for distributed problem solving. Agents can cooperate to solve complex problems. Another application is in resource allocation, where multiple agents need to share limited resources, such as bandwidth, energy, or computational resources. Market-based mechanisms, such as auctions, are often used in these scenarios to allocate resources efficiently and fairly among self-interested agents. MAS can be used for resource allocation. Auctions and other market-based mechanisms can allocate resources efficiently. MAS are also used to model and simulate social and economic systems. By creating artificial societies of agents that interact according to certain rules, researchers can study the emergence of social phenomena, such as cooperation, conflict, and the formation of norms. Agent-based modeling is a powerful tool for understanding complex social systems. MAS can be used to model social and economic systems. Agent-based modeling can provide insights into social phenomena. In electronic commerce, MAS are used to create automated trading agents, recommendation systems, and negotiation platforms. These systems can help to automate and optimize various aspects of online commerce, such as bidding in auctions, recommending products to customers, and negotiating prices and terms of service. MAS are used in electronic commerce. They can automate trading, recommendations, and negotiations. Robotics is another important application area for MAS. Multi-robot systems can be used to perform tasks that are difficult or impossible for a single robot to accomplish, such as exploring hazardous environments, assembling complex structures, or playing team sports. Coordination and cooperation among robots are crucial for the success of these applications. MAS are used in multi-robot systems. They enable robots to coordinate and cooperate on complex tasks. The applications of MAS are diverse and constantly expanding. As AI techniques continue to advance and as more domains recognize the benefits of a multi-agent approach, we can expect to see even more innovative and impactful applications of MAS in the years to come. MAS have a wide range of applications. They are used in many domains and their use is expanding. Challenges and future directions in multi-agent systems, towards robust, adaptive, and scalable MAS. Despite the many successes of multi-agent systems, significant challenges remain to be addressed. This section will explore some of the key challenges in MAS research, including the difficulty of designing robust and adaptive coordination mechanisms, the problem of emergent behavior and its unpredictability, and the need for scalable MAS that can handle large numbers of agents and complex interactions. We will also discuss some of the promising future directions in MAS research, such as the development of more sophisticated learning and adaptation techniques for multi-agent settings. This examines the limitations and future research directions in MAS. One of the main challenges in MAS is designing robust and adaptive coordination mechanisms. As the number of agents and the complexity of their interactions increase, it becomes increasingly difficult to design coordination protocols that can handle all possible situations and that can adapt to changes in the environment or in the agent's goals. Robust and adaptive coordination is a key challenge. It is difficult to design coordination mechanisms that can handle complex interactions. Another challenge is the problem of emergent behavior. In complex MAS, the interactions between agents can give rise to unexpected and unpredictable global behaviors, some of which may be undesirable or even harmful. Understanding and controlling emergent behavior is a major challenge in MAS research. Emergent behavior can be unpredictable and difficult to control. It is a challenge in complex MAS. Scalability is also a significant challenge in MAS. Many MAS techniques that work well with a small number of agents do not scale well to systems with hundreds or thousands of agents. Developing MAS that can handle large numbers of agents and complex interactions is an important area of research. Scalability is a challenge for MAS. Many techniques do not scale well to large numbers of agents. Learning and adaptation are crucial for creating MAS that can operate effectively in dynamic and uncertain environments. However, multi-agent learning is a challenging problem due to the non-stationarity of the environment, the difficulty of coordinating learning among multiple agents, and the potential for instability and oscillations in the learning process. Learning and adaptation are crucial but challenging in MAS. The non-stationarity of the environment and coordination issues pose difficulties. Despite these challenges, the field of MAS is rapidly advancing. Researchers are developing new techniques for coordination, communication, learning, and adaptation in multi-agent settings. There is also a growing interest in applying MAS to new domains, such as the Internet of Things, smart grids, and social robotics. MAS research is rapidly advancing. New techniques and applications are constantly emerging. The future of MAS is likely to involve closer integration with other areas of AI, such as deep learning, reinforcement learning, and natural language processing. This will enable the development of more sophisticated and capable MAS that can learn from data, interact with humans in natural ways, and operate in complex, real-world environments. The future of MAS involves integration with other AI techniques. It will lead to more sophisticated and capable systems. As multi-agent systems become more powerful and pervasive, it will be increasingly important to address the ethical and societal implications of these technologies. This includes issues such as the potential for autonomous weapons systems, the impact on employment and the economy, and the need for appropriate regulations and safeguards to ensure that MAS are used responsibly and for the benefit of humanity. The ethical and societal implications of MAS must be addressed. They require careful consideration and proactive measures. Lesson 16, AI-driven personal assistants and conversational agents, transforming human-computer interaction. Welcome back, forward-thinking learners, to the 16th lesson in our advanced exploration of artificial intelligence. In this lesson, we delve into the realm of AI-driven personal assistants and conversational agents, technologies that are transforming the way humans interact with computers and access information. We will explore the underlying technologies that power these agents, including natural language processing, machine learning, and dialogue management, and examine their applications in various domains, such as customer service, personal productivity, and healthcare. We will also discuss the challenges of building effective and engaging conversational agents, including natural language understanding, context awareness, and personality design. Furthermore, we will consider the ethical implications of these technologies, such as privacy, security, and the potential impact on human relationships. Prepare to discover how AI is enabling more natural, intuitive, and personalized interactions with technology, and how these conversational agents are poised to become increasingly integrated into our daily lives. The rise of conversational agents, from simple chatbots to intelligent assistants. Conversational agents, also known as chatbots or virtual assistants, have evolved significantly from simple rule-based systems to sophisticated AI-powered entities capable of engaging in complex conversations. This section will trace the evolution of conversational agents, highlighting the key technological advancements that have enabled their development. We will also discuss the different types of conversational agents and their applications, and examine the factors driving their increasing adoption in various domains. This sets the stage for understanding the transformative potential of conversational AI. Early conversational agents, such as ELIZA developed in the 1960s, relied on simple pattern matching and pre-programmed responses. These systems had limited ability to understand or generate natural language and were often unable to maintain a coherent conversation beyond a few turns. Early chatbots were based on simple rules. They had limited conversational abilities. The development of more advanced natural language processing (NLP) techniques, such as statistical language modeling and machine translation, paved the way for more sophisticated conversational agents. These agents could handle a wider range of inputs and generate more varied and contextually appropriate responses. Advances in NLP improved language understanding. They enabled more flexible and dynamic conversations. The rise of machine learning, particularly deep learning, has further accelerated the development of conversational agents. Deep learning models, such as recurrent neural networks, RNNs, and transformers, can learn complex patterns in language data and generate more natural and human-like responses. Machine learning enables data-driven learning. It has significantly improved the performance of conversational agents. Today, conversational agents are used in a wide range of applications, from customer service and technical support to personal assistants and companions. They can be found in various platforms, including websites, messaging apps, smart speakers, and mobile devices. Conversational agents are becoming ubiquitous. They are used in many different applications and platforms. Several factors are driving the increasing adoption of conversational agents. These include the growing demand for 24/7 customer service, the increasing comfort of users with interacting with AI, and the potential cost savings and efficiency gains for businesses. The adoption of conversational agents is driven by various factors. It is fueled by user demand and business needs. Conversational agents offer numerous benefits, such as improved customer satisfaction, increased efficiency, and reduced operational costs. However, they also present challenges, such as the need for robust natural language understanding, effective dialogue management, and seamless integration with other systems. Conversational agents offer many benefits but also pose challenges. They require careful design and implementation. Natural language understanding for conversational agents, interpreting human language. Natural language understanding, NLU, is a crucial component of conversational agents, enabling them to interpret and understand human language inputs. This section will delve into the key techniques used in NLU, including intent recognition, entity extraction, and sentiment analysis. We will examine how these techniques are used to extract meaning from user utterances and map them to actions or responses. We will also discuss the challenges of NLU, such as handling ambiguity, variability, and context in natural language. This provides an in-depth understanding of how conversational agents understand language. Intent recognition is the task of identifying the underlying intention or goal behind a user's utterance. For example, if a user says, "What's the weather like in London?" the intent might be, "get_weather," with a parameter, location equals London. Intent recognition is crucial for understanding user goals. It enables the agent to take appropriate actions. Entity extraction involves identifying and classifying key entities mentioned in the user's utterance, such as names, locations, dates, and times. For example, in the sentence, "Book me a flight to New York on Friday," the entities are New York, location, and Friday, date. Entity extraction provides structured information. It helps the agent to fulfill the user's request. Sentiment analysis can also be used in NLU to gauge the user's emotional state or attitude towards a particular topic. This can help the agent to tailor its responses and provide a more personalized and empathetic interaction. Sentiment analysis adds an emotional dimension to NLU. It can improve the user experience. NLU systems often use machine learning models, such as support vector machines, SVMs, recurrent neural networks, RNNs, and more recently, transformer-based models like BERT, to perform intent recognition and entity extraction. These models are trained on large datasets of labeled examples and can learn to generalize to new, unseen inputs. Machine learning powers NLU. It enables robust and accurate interpretation of user inputs. Despite the progress in NLU, many challenges remain. Natural language is inherently ambiguous, with words and phrases often having multiple meanings depending on the context. It is also highly variable, with the same meaning being expressed in many different ways. Handling ambiguity and variability is a major challenge in NLU. It requires sophisticated models and techniques. Context plays a crucial role in NLU. Understanding the meaning of an utterance often requires considering the previous turns in the conversation, as well as the user's profile, preferences, and current situation. Incorporating context into NLU is essential for effective communication. It is a complex and ongoing research problem. Dialogue management, orchestrating coherent and engaging conversations. While NLU focuses on understanding individual user inputs, dialogue management is responsible for orchestrating the overall flow of the conversation and ensuring that it is coherent, engaging, and goal-oriented. This section will explore different approaches to dialogue management, including rule-based systems, statistical models, and reinforcement learning. We will also discuss the key challenges in dialogue management, such as maintaining context, handling user initiative, and generating appropriate responses. This examines how conversational agents manage the flow of conversation. Dialogue management involves several key tasks, including tracking the state of the conversation, deciding what action the agent should take next, and generating appropriate responses. The dialogue manager must maintain a representation of the current context, including the user's goals, the history of the conversation, and any relevant external information. Dialogue management is the control center of the conversation. It guides the interaction and ensures coherence. Rule-based dialogue managers rely on a set of predefined rules to determine the agent's actions. These rules are typically handcrafted by developers and can be effective for simple, well-defined domains. However, they can be difficult to scale and maintain for more complex or open-ended conversations. Rule-based systems are simple but inflexible. They are suitable for limited domains. Statistical dialogue managers, on the other hand, learn from data. They use machine learning models to predict the best action to take given the current state of the conversation. These models can be trained on large datasets of human-human or human-machine conversations. Statistical methods enable data-driven learning. They can adapt to different conversational styles. Reinforcement learning, RL, has emerged as a promising approach for dialogue management. In this approach, the agent learns a dialogue policy by interacting with users and receiving rewards based on the success of the conversation. RL can potentially learn more complex and adaptive dialogue strategies compared to supervised learning approaches. RL offers a powerful framework for dialogue management. It allows agents to learn through interaction. Maintaining context is a key challenge in dialogue management. The agent must be able to track the conversation history, remember relevant information from previous turns, and resolve anaphoric references, e.g., pronouns referring to previously mentioned entities. Maintaining context is crucial for coherent conversation. It requires sophisticated memory and reasoning mechanisms. Handling user initiative, where the user takes control of the conversation or introduces new topics, is another challenge. The agent must be able to gracefully handle unexpected inputs, adapt to changes in the user's goals, and guide the conversation back to a productive path. Handling user initiative requires flexibility. It is essential for natural and engaging interactions. Response generation, crafting natural and relevant responses. Once the conversational agent has understood the user's input and determined the appropriate action, it needs to generate a response that is natural, relevant, and engaging. This section will explore different approaches to response generation, including template-based methods, retrieval-based methods, and generative models based on deep learning. We will also discuss the challenges of generating responses that are not only grammatically correct and contextually appropriate but also exhibit the desired personality and tone. This examines how conversational agents create their responses. Template-based response generation involves using predefined templates with slots that can be filled in with specific information. For example, a template for responding to a weather query might be, the weather in, location, is currently, temperature, degrees, and condition. Template-based methods are simple and ensure grammatical correctness. They can produce repetitive and inflexible responses. Retrieval-based methods select a response from a predefined set of responses based on the current conversational context. These methods often use information retrieval techniques to find the most relevant response given the user's input and the conversation history. Retrieval-based methods can produce more varied responses than template-based methods. They are limited to the predefined set of responses. Generative models, particularly those based on deep learning, can generate novel responses that are not limited to a predefined set of templates or responses. These models, such as sequence-to-sequence models based on RNNs or transformers, learn to generate responses word by word, conditioned on the input and the conversation history. Generative models can produce more flexible and diverse responses. They can generate novel and creative text. Generating responses that are not only grammatically correct and relevant but also exhibit the desired personality and tone is a significant challenge. The agent's personality can be conveyed through its choice of words, its tone of voice, and its overall conversational style. Creating a consistent and engaging personality is important for user experience. It requires careful design and fine-tuning of the response generation models. Another challenge is ensuring that the generated responses are factually correct and consistent with the agent's knowledge base. This is particularly important for agents that provide information or answer questions. Researchers are exploring techniques for grounding response generation in external knowledge sources and for verifying the factual accuracy of generated responses. Ensuring factual correctness is crucial. It is particularly important for information-providing agents. Personalization and adaptation in conversational agents, tailoring the interaction to individual users. One of the key promises of AI-driven conversational agents is the ability to personalize the interaction and adapt to individual users' needs, preferences, and styles. This section will explore techniques for personalization and adaptation in conversational agents, including user modeling, preference learning, and adaptive dialogue strategies. We will also discuss the challenges of learning from limited user interactions and the importance of balancing personalization with privacy concerns. This highlights the importance of tailoring interactions to individual users. Personalization involves tailoring the agent's behavior, language, and content to individual users. This can include adapting the agent's responses based on the user's past interactions, their stated preferences, their demographic information, or their current emotional state. Personalization can improve user engagement and satisfaction. It can make the interaction more efficient and effective. User modeling is a key component of personalization. It involves building and maintaining a representation of the user's characteristics, preferences, and goals. This model can be constructed explicitly, by asking the user questions, or implicitly, by learning from the user's interactions with the agent. User modeling is essential for personalization. It provides the basis for tailoring the interaction to the user. Preference learning is a specific type of user modeling that focuses on learning the user's preferences over different options or outcomes. This can involve techniques such as collaborative filtering, which recommends items based on the preferences of similar users, or reinforcement learning, which learns the user's preferences through their feedback on the agent's actions. Preference learning can enhance personalization. It enables the agent to make recommendations and choices that align with the user's preferences. Adaptive dialogue strategies involve adjusting the agent's conversational behavior based on the user's characteristics and the ongoing interaction. For example, the agent might use different language styles or levels of detail depending on the user's expertise or adapt its questioning strategy based on the user's responses. Adaptive dialogue strategies can improve the effectiveness of the interaction. They can make the conversation more natural and engaging. Learning from limited user interactions is a major challenge in personalization and adaptation. Conversational agents often need to make decisions based on sparse data, particularly when interacting with new users. Techniques such as transfer learning, which leverages data from other users or tasks, and active learning, which intelligently selects which questions to ask the user, can help to address this challenge. Learning from limited data is crucial. It is a key challenge in personalization. Evaluation of conversational agents, measuring performance and user satisfaction. Evaluating the performance of conversational agents is crucial for their development and improvement. This section will explore different approaches to evaluating conversational agents, including automatic metrics, human evaluations, and user studies. We will discuss the strengths and limitations of each approach and the challenges of measuring complex conversational phenomena, such as engagement, coherence, and user satisfaction. We will also examine the importance of considering the specific goals and context of the agent when choosing evaluation methods. This addresses the critical issue of assessing conversational agent quality. Automatic evaluation metrics can provide a quick and inexpensive way to assess certain aspects of a conversational agent's performance. For example, metrics such as BLEU and Rouge, originally developed for machine translation, can be used to measure the overlap between the agent's responses and human-generated responses. Automatic metrics are efficient and scalable. They can provide a quantitative measure of performance. However, automatic metrics often fail to capture the nuances of human conversation and may not correlate well with human judgments of quality. For example, a response that has a high BLEU score may still be irrelevant or nonsensical in the context of the conversation. Automatic metrics have limitations. They may not fully capture the quality of the interaction. Human evaluations, where human judges assess the quality of the conversation based on various criteria, such as relevance, coherence, fluency, and engagement, are often considered the gold standard for evaluating conversational agents. Human evaluations can provide more nuanced and reliable assessments of conversational quality. They are more aligned with human judgments. User studies, where real users interact with the agent and provide feedback on their experience, can provide valuable insights into the agent's performance in a realistic setting. User studies can measure user satisfaction, task completion rates, and other metrics that reflect the overall effectiveness of the interaction. User studies provide real-world evaluation. They capture the user experience and task effectiveness. Evaluating conversational agents is challenging due to the complexity and subjectivity of human conversation. Different users may have different expectations and preferences, and the quality of a conversation can depend on many factors, including the user's goals, the agent's personality, and the specific context of the interaction. Evaluating conversational agents is complex and multifaceted. It requires considering various factors and perspectives. Choosing the appropriate evaluation methods depends on the specific goals and context of the agent. For example, a task-oriented agent might be evaluated primarily on its ability to help users complete tasks efficiently, while a social chatbot might be evaluated on its ability to engage users in natural and enjoyable conversations. The ability of conversational agents to mimic human conversation raises concerns about the potential for manipulation or deception. Users may not always be aware that they are interacting with an AI and not a human, which could lead to misunderstandings or even exploitation. Transparency about the nature of the agent is important for ethical interaction. Users should be informed when they are interacting with an AI. The increasing sophistication of conversational agents also raises questions about their potential impact on human relationships and social interactions. Some researchers have expressed concerns that over-reliance on AI companions could lead to social isolation or a decrease in human empathy. It is important to consider the potential societal impacts of these technologies. The impact on human relationships must be considered. We need to design agents that promote positive social interactions. The potential for bias in conversational agents is another ethical concern. If these agents are trained on biased data or reflect the biases of their developers, they may perpetuate or even amplify harmful stereotypes and discrimination. Addressing bias in conversational agents is crucial. It requires careful attention to training data and algorithms. Developing ethical guidelines and best practices for conversational AI is essential for ensuring that these technologies are developed and deployed responsibly. This includes principles such as transparency, accountability, fairness, and respect for user autonomy. Ethical guidelines are essential for responsible development. They should address issues such as privacy, bias, and transparency. The future of conversational AI, towards more human-like and empathetic agents. The field of conversational AI is rapidly advancing, with ongoing research pushing the boundaries of what's possible in natural language understanding, dialogue management, and response generation. This section will explore some of the most promising future directions and emerging trends in conversational AI, including the development of more human-like and empathetic agents, the integration of conversational AI with other technologies, and the potential for conversational agents to transform various industries and aspects of our lives. This section will explore some of the most promising future directions and emerging trends in conversational AI, including the development of more human-like and empathetic agents, the integration of conversational AI with other technologies, and the potential for conversational agents to transform various industries and aspects of our lives. This provides a glimpse into the future of conversational AI. One major trend is the development of more human-like and empathetic conversational agents. Researchers are exploring techniques for enabling agents to better understand and respond to human emotions, to exhibit more natural and engaging conversational styles, and to build long-term relationships with users. More human-like and empathetic agents are on the horizon. They will be able to understand and respond to emotions. Another important direction is the integration of conversational AI with other technologies, such as computer vision, robotics, and augmented reality. This convergence will enable the creation of multimodal conversational agents that can interact with users through various modalities, including speech, text, gestures, and facial expressions. The integration of conversational AI with other technologies is transformative. It will enable more natural and intuitive interactions. The increasing use of conversational agents in various industries, such as healthcare, education, and entertainment, is also driving innovation in the field. For example, in healthcare, conversational agents are being used to provide mental health support, medication reminders, and personalized health coaching. Conversational agents are transforming various industries. They are enabling new applications and services. The development of more robust and reliable conversational AI systems is a key priority. This includes improving the ability of agents to handle unexpected or out-of-domain inputs, to recover from errors gracefully, and to maintain coherence and consistency over long conversations. Robustness and reliability are crucial for real-world deployment. They are essential for user trust and adoption. Finally, the ethical and societal implications of conversational AI will continue to be an important area of focus. As these agents become more sophisticated and integrated into our lives, it will be crucial to address issues such as privacy, security, bias, and the impact on human relationships and social interactions. Ethical considerations must remain at the forefront. They are essential for responsible development and deployment. The future of conversational AI holds immense promise for transforming the way we interact with technology and access information. As you continue your journey in AI, you will have the opportunity to contribute to these advancements and shape the future of this dynamic field, creating intelligent agents that can understand, reason, and communicate in increasingly human-like ways. The possibilities are vast. The future of conversational AI is full of potential. Lesson 17, AI in Education and Learning Sciences, Transforming the Landscape of Learning and Teaching. Welcome back, knowledge-seeking learners, to the 17th lesson in our advanced exploration of artificial intelligence. In this lesson, we venture into the transformative realm of AI in education and learning sciences, where AI is poised to revolutionize the way we learn, teach, and understand the learning process itself. We will explore how AI techniques, such as machine learning, natural language processing, and intelligent tutoring systems, are being used to personalize learning experiences, automate assessment and feedback, and provide insights into student learning and engagement. We will also examine the challenges and ethical considerations associated with deploying AI in education, including issues of equity, privacy, and the role of the teacher in an AI-enhanced classroom. Furthermore, we will discuss the potential of AI to transform not only the practice of education but also our understanding of how humans learn, paving the way for more effective and engaging learning experiences for all. Prepare to discover how AI is reshaping the landscape of education, offering the potential for more personalized, adaptive, and data-driven approaches to learning and teaching, while also raising important questions about the future of education in the age of intelligent machines. The promise of AI in education, personalizing and enhancing the learning experience. AI has the potential to transform education by providing personalized learning experiences, automating time-consuming tasks, and offering new insights into student learning and engagement. This section will explore the various ways in which AI is being applied across the educational spectrum, from K-12 to higher education and professional training. We will also discuss the potential benefits of AI in education, including increased student engagement, improved learning outcomes, and greater access to educational opportunities. This sets the stage for understanding the transformative potential of AI in education. One of the most promising applications of AI in education is personalized learning. AI-powered systems can adapt to each student's individual needs, pace, and learning style, providing customized content, feedback, and support. This can lead to more effective and engaging learning experiences, as each student can focus on the areas where they need the most help. AI can personalize learning at scale. It can tailor educational experiences to individual students. Intelligent tutoring systems, ITS, are another important application of AI in education. These systems provide one-on-one tutoring to students, guiding them through complex problems, providing hints and feedback, and adapting to their individual learning needs. ITS have been shown to be effective in improving student learning outcomes in various domains, such as mathematics and science. Intelligent tutoring systems provide personalized instruction. They can act as virtual tutors for students. AI can also be used to automate assessment and feedback, freeing up teachers' time and providing students with more immediate and detailed feedback on their work. For example, AI-powered systems can automatically grade essays, provide feedback on writing style and grammar, and identify areas where students are struggling. AI can automate assessment and feedback. It can provide timely and detailed feedback to students. Natural language processing, NLP, is playing an increasingly important role in educational applications. NLP techniques can be used to analyze student writing, provide feedback on essays, and even power conversational agents that can interact with students and answer their questions. NLP enables new forms of interaction and assessment. It can analyze and understand student language. The use of AI in education offers numerous potential benefits. It can help to personalize learning, improve student engagement and motivation, provide more timely and detailed feedback, and automate time-consuming tasks for teachers. It can also help to identify students who are at risk of falling behind and provide them with targeted interventions. AI has the potential to improve educational outcomes. It can make learning more effective and engaging. Intelligent tutoring systems, providing personalized guidance and support. Intelligent tutoring systems, ITS, are one of the most well-established and impactful applications of AI in education. This section will delve deeper into the design and functionality of ITS, exploring how these systems use AI techniques to model student knowledge, provide personalized instruction, and adapt to individual learning needs. We will examine different approaches to building ITS, including cognitive tutors and constraint-based tutors, and discuss their effectiveness in various educational settings. We will also explore the challenges of developing and deploying ITS at scale. This provides an in-depth understanding of ITS. ITS are computer-based instructional systems that aim to provide personalized tutoring to students, similar to what a human tutor would provide. They use AI techniques to model the student's knowledge, track their progress, and provide tailored instruction, feedback, and support. ITS aim to mimic the benefits of one-on-one tutoring. They adapt to the individual needs of each learner. Cognitive tutors are a type of ITS that are based on cognitive psychology and learning science principles. They model the cognitive processes involved in problem solving and provide step-by-step guidance to students as they work through problems. Cognitive tutors have been particularly successful in domains such as mathematics and computer programming. Cognitive tutors are based on cognitive principles. They provide detailed guidance and support during problem solving. Constraint-based tutors are another type of ITS that focus on identifying and correcting student errors. They use a set of constraints that define correct solutions and provide feedback when students violate these constraints. Constraint-based tutors have been used in various domains, including physics and database design. Constraint-based tutors focus on error detection and correction. They provide targeted feedback on student mistakes. ITS often use a variety of AI techniques, including knowledge representation, automated reasoning, and machine learning, to model student knowledge, track their progress, and adapt the instruction. For example, Bayesian knowledge tracing is a popular technique for modeling student learning over time and predicting their future performance. ITS use various AI techniques to personalize instruction. They model student knowledge and adapt to their learning progress. Research has shown that well-designed ITS can be as effective as human tutors in improving student learning outcomes. They have been shown to be particularly effective for teaching well-defined skills and procedures, such as those found in mathematics and science. ITS can be highly effective in improving learning outcomes. They have demonstrated effectiveness comparable to human tutors. Developing and deploying ITS at scale presents several challenges. These include the high cost of developing high-quality ITS, the need for extensive testing and validation, and the challenges of integrating ITS into existing educational settings and curricula. Scaling up ITS is a major challenge. It requires addressing issues of cost, development, and integration. Automated assessment and feedback, leveraging AI for efficient and timely evaluation. Assessment and feedback are crucial components of the learning process, but they can be time-consuming and labor-intensive for teachers. This section will explore how AI can be used to automate various aspects of assessment and feedback, including automated essay scoring, automated grading of programming assignments, and providing personalized feedback on student writing. We will also discuss the limitations and ethical considerations of automated assessment, such as the potential for bias and the importance of human judgment in evaluation. This examines how AI can streamline and enhance assessment. Automated essay scoring, AES, is one of the most well-known applications of AI in assessment. AES systems use natural language processing, NLP, and machine learning techniques to automatically evaluate and grade student essays. These systems can assess various aspects of writing, such as grammar, style, organization, and content. AES can save teachers time and provide faster feedback. It can evaluate essays based on various criteria. AI can also be used to automatically grade programming assignments. These systems can analyze student code, identify errors, and provide feedback on code quality, efficiency, and correctness. Automated grading of programming assignments can be particularly useful in large computer science courses. AI can automate the grading of programming assignments. It can provide detailed feedback on code quality and correctness. AI-powered systems can also provide personalized feedback on student writing. For example, these systems can identify areas where students are struggling with grammar or style and provide targeted suggestions for improvement. They can also help students to develop their ideas and improve the overall structure and coherence of their writing. AI can provide personalized feedback on writing. It can help students improve their writing skills. However, automated assessment also has limitations. Current AI systems may struggle with evaluating higher-order thinking skills, creativity, and originality. They may also be susceptible to bias if they are trained on data that reflects existing societal biases. Automated assessment has limitations. It may not be suitable for all types of assessment. The use of AI for assessment also raises ethical considerations. It is important to ensure that these systems are fair, transparent, and unbiased, and that they do not disadvantage certain groups of students. The potential impact on student motivation and learning should also be considered. Ethical considerations are crucial in automated assessment. They must be addressed to ensure fairness and positive learning outcomes. Despite these challenges, the potential benefits of automated assessment and feedback are significant. By automating routine grading tasks, AI can free up teachers' time to focus on more individualized instruction and support. It can also provide students with more frequent and detailed feedback, helping them to improve their learning and performance. AI can enhance assessment and feedback. It can make these processes more efficient and effective. Learning analytics and educational data mining, uncovering insights into student learning. That increasing use of technology in education generates vast amounts of data about student learning and engagement. This section will explore the field of learning analytics and educational data mining, which involves using AI and data mining techniques to analyze educational data and uncover insights into student learning, behavior, and performance. We will examine how these techniques can be used to identify at-risk students, personalize learning pathways, and evaluate the effectiveness of educational interventions. We will also discuss the challenges of working with educational data and the importance of protecting student privacy. This examines how data can be used to understand and improve learning. Learning analytics involves the measurement, collection, analysis, and reporting of data about learners and their contexts, one for purposes of understanding and optimizing learning and the environments in which it occurs. 2. Educational data mining, EDM, is a related field that focuses on developing methods for exploring the unique types of data that come from educational settings. Learning analytics and EDM use data to improve learning. They provide insights into student behavior and performance. 1. Faras. Musfi. Compfiras. Musfi. Com2. www.uu. NLWWW. UU. NLAI and data mining techniques can be applied to various types of educational data, including data from learning management systems, LMS, intelligent tutoring systems, ITS, online courses, and even social media. This data can include information about student demographics, course enrollment, grades, assessment results, interactions with learning materials, and online discussions. Educational data comes from various sources. It provides a rich source of information about learning. One application of learning analytics is to identify students who are at risk of failing or dropping out of a course. By analyzing patterns in student behavior and performance, AI models can identify early warning signs and flag students who may need additional support. Learning analytics can identify at-risk students. It can enable early interventions and support. Learning analytics can also be used to personalize learning pathways for individual students. By analyzing a student's strengths, weaknesses, and learning preferences, AI systems can recommend specific learning resources, activities, or interventions that are tailored to the student's needs. Learning analytics can personalize learning. It can create customized learning paths for each student. Another important application is evaluating the effectiveness of educational interventions, such as new teaching methods or educational technologies. By analyzing data on student performance and engagement before and after the intervention, researchers can assess its impact and identify areas for improvement. Learning analytics can evaluate educational interventions. It can provide evidence of their effectiveness. Working with educational data presents unique challenges. Educational data is often complex, heterogeneous, and longitudinal, requiring specialized techniques for analysis. Protecting student privacy and ensuring the ethical use of educational data is also of paramount importance. Educational data requires careful handling. It raises important ethical and privacy considerations. AI for accessibility and inclusive education, supporting diverse learners. AI has the potential to make education more accessible and inclusive for all learners, including those with disabilities or diverse learning needs. This section will explore how AI-powered tools and technologies can be used to support students with disabilities, such as text-to-speech and speech-to-text software, personalized learning platforms, and assistive technologies. We will also discuss the potential of AI to address issues of equity and access in education, such as by providing personalized support to students from disadvantaged backgrounds or by enabling access to quality education in remote or underserved areas. This highlights how AI can promote equity and inclusion in education. AI-powered text-to-speech, TTS, and speech-to-text, STT, technologies can be invaluable for students with visual or hearing impairments. TTS can convert written text into spoken words, while STT can convert spoken words into written text, enabling students with disabilities to access and interact with digital learning materials. TTS and STT can support students with disabilities. They can make learning materials more accessible. Personalized learning platforms, powered by AI, can adapt to the specific needs of students with disabilities, providing customized content, pacing, and feedback. These platforms can also incorporate features such as alternative input methods, customizable interfaces, and multimedia supports to accommodate diverse learning styles and needs. AI can personalize learning for students with disabilities. It can provide tailored support and accommodations. AI-powered assistive technologies can also help students with disabilities in various ways. For example, AI-powered wheelchairs can navigate complex environments, while robotic assistants can help students with physical tasks. Brain-computer interfaces, BCIs, can even enable students with severe physical disabilities to control computers and other devices using their brainwaves. AI-powered assistive technologies can enhance independence. They can enable students with disabilities to participate more fully in education. AI also has the potential to address issues of equity and access in education more broadly. By providing personalized support and resources to students from disadvantaged backgrounds, AI can help to close achievement gaps and promote educational equity. AI-powered platforms can also enable access to quality education in remote or underserved areas, where educational resources may be limited. AI can promote educational equity. It can provide personalized support and expand access to quality education. However, the use of AI in education also raises ethical concerns, particularly regarding the potential for bias and discrimination. It is crucial to ensure that AI systems used in education are fair, unbiased, and do not perpetuate existing inequalities. Addressing these ethical challenges requires careful consideration of the design, development, and deployment of AI in education. Ethical considerations are crucial in AI for education. They must be addressed to ensure fairness and equity. The role of the teacher in the age of AI, redefining pedagogy and practice. As AI becomes increasingly integrated into education, the role of the teacher is likely to evolve. This section will explore how AI can augment and support the work of teachers, rather than replacing them. We will discuss how AI can free up teachers' time from routine tasks, allowing them to focus on more complex and human-centric aspects of teaching, such as mentoring, coaching, and fostering social-emotional learning. We will also examine the new skills and competencies that teachers may need to develop to effectively integrate AI into their practice. This examines the evolving role of teachers in an AI-enhanced educational landscape. AI can automate many of the time-consuming and repetitive tasks that teachers currently perform, such as grading assignments, providing feedback, and managing administrative tasks. This can free up teachers' time to focus on more high-impact activities, such as designing engaging learning experiences, providing individualized support to students, and fostering their social-emotional development. AI can augment the work of teachers. It can automate routine tasks and free up time for more meaningful interactions. In an AI-enhanced classroom, the role of the teacher may shift from being primarily a dispenser of information to being a facilitator, mentor, and coach. Teachers can use AI-powered tools to personalize learning for each student, while also providing the human connection, guidance, and support that are essential for student success. The role of the teacher is evolving. It is becoming more focused on facilitation, mentoring, and coaching. AI can also provide teachers with valuable insights into student learning and engagement. By analyzing data from AI-powered learning platforms, teachers can gain a deeper understanding of each student's strengths, weaknesses, and learning patterns. This can help them to tailor their instruction and provide more targeted support. AI can provide insights into student learning. It can help teachers to better understand and support their students. To effectively integrate AI into their practice, teachers may need to develop new skills and competencies. These may include data literacy, the ability to interpret and act upon insights from AI systems, and the ability to design and implement learning experiences that leverage the strengths of both AI and human intelligence. Teachers need new skills to effectively use AI. They must become proficient in using AI tools and interpreting data. The integration of AI into education also raises questions about the professional development and training of teachers. Teachers will need ongoing support and training to effectively use AI tools and to adapt their teaching practices to the changing educational landscape. Professional development is crucial for successful AI integration. It requires ongoing support and training for teachers. Ethical considerations in AI for education, privacy, bias, and transparency. The use of AI in education raises important ethical considerations, particularly regarding student privacy, algorithmic bias, and transparency. This section will explore these ethical challenges in greater depth, examining how the collection and use of student data for AI systems can impact privacy, how biases in training data or algorithms can lead to unfair or discriminatory outcomes, and the importance of transparency and explainability in AI for education. We will also discuss the need for ethical guidelines and regulations to ensure the responsible development and deployment of AI in education. This encourages a thoughtful and ethical approach to AI in education. Student privacy is a paramount concern in the context of AI in education. AI systems often collect and analyze large amounts of student data, including personal information, academic performance, and online behavior. It is crucial to ensure that this data is collected, stored, and used in a way that protects student privacy and complies with relevant regulations, such as the Family Educational Rights and Privacy Act, FERPA, in the United States. Student privacy must be protected. It requires careful data handling and compliance with regulations. Algorithmic bias is another critical issue in AI for education. If AI systems are trained on biased data or incorporate biased assumptions, they can perpetuate and even amplify existing educational inequalities. For example, an AI system that predicts student success based on historical data may unfairly disadvantage students from groups that have historically been underrepresented in higher education. Bias in AI can perpetuate inequalities. It must be addressed through careful design and evaluation. Transparency and explainability are also important considerations in AI for education. Teachers, students, and parents should be able to understand how AI systems are being used, what data they are collecting, and how they are making decisions that affect students. This is particularly important for high-stakes applications, such as admissions or grading. Transparency and explainability are essential for trust. They are crucial for understanding how AI is being used. Ethical considerations in AI for education, privacy, bias, and transparency. Continued, transparency and explainability are also important considerations in AI for education. Teachers, students, and parents should be able to understand how AI systems are being used, what data they are collecting, and how they are making decisions that affect students. This is particularly important for high-stakes applications, such as admissions or grading. Transparency and explainability are essential for trust. They are crucial for understanding how AI is being used in education. The use of AI in education also raises questions about the appropriate role of technology in the classroom and the potential impact on the teacher-student relationship. It is important to ensure that AI is used to enhance, rather than replace, the essential human elements of teaching and learning. The role of technology must be carefully considered. It should support, not replace, human interaction and connection. Addressing these ethical challenges requires a multifaceted approach, involving not only technical solutions, such as privacy-preserving AI techniques and bias detection methods, but also broader societal discussions about the values we want to embed in these systems and the kind of educational future we want to create with them. It requires collaboration between researchers, educators, policymakers, and the public. We must shape the future of AI in education responsibly. It is a collective responsibility. The future of AI in education, towards intelligent learning ecosystems. The field of AI in education is rapidly evolving, with new techniques and applications emerging at an accelerating pace. This section will explore some of the most promising future directions and emerging trends in AI for education, including the development of more integrated and intelligent learning ecosystems, the use of AI to support lifelong learning and professional development, and the potential for AI to transform not only how we learn but also what we learn. We will also discuss the challenges of realizing this future vision and the need for ongoing research and collaboration. This provides a glimpse into the future of AI in education. One major trend is the development of more integrated and intelligent learning ecosystems. These systems will combine various AI-powered tools, such as intelligent tutoring systems, learning analytics dashboards, and personalized learning platforms, to create a more seamless and adaptive learning experience for students. Intelligent learning ecosystems will integrate various AI tools. They will provide a more holistic and personalized learning experience. The use of AI to support lifelong learning and professional development is another important direction. As the pace of technological change accelerates, the need for continuous learning and upskilling will become increasingly important. AI-powered platforms can provide personalized learning pathways, recommend relevant courses and resources, and support on-the-job learning. AI can support lifelong learning. It can enable continuous upskilling and reskilling. AI also has the potential to transform not only how we learn but also what we learn. As AI systems become more sophisticated, they may be able to help us identify new areas of knowledge and inquiry, generate new learning materials and assessments, and even help us to develop new cognitive skills and abilities. AI can transform the content of learning. It can help us to discover and learn new things. The increasing availability of large-scale educational data and the development of new AI techniques, such as deep learning and reinforcement learning, are likely to continue to drive progress in AI for education. As these trends converge, we can expect to see even more transformative applications of AI in education in the years to come. Advances in data and AI techniques will fuel innovation. They will enable new and more powerful applications. However, realizing the full potential of AI in education will also require addressing the technical, pedagogical, and ethical challenges discussed in previous sections. It will also require ongoing collaboration between researchers, educators, policymakers, and the private sector to ensure that AI is used to create more effective, equitable, and engaging learning experiences for all. Realizing the full potential of AI in education requires ongoing effort. It is a collaborative and interdisciplinary endeavor. The future of AI in education holds immense promise for transforming the way we learn, teach, and understand the learning process itself. As you continue your journey in AI, you will have the opportunity to contribute to these advancements and shape the future of this dynamic field, creating intelligent systems that can empower learners, support teachers, and unlock new possibilities for human development and flourishing. The possibilities are vast. The future of AI in education is full of potential. Lesson 18: AI and Cybersecurity, Fortifying Defenses and Combating Threats in the Digital Age. Welcome back, vigilant learners, to the 18th lesson in our advanced exploration of artificial intelligence. In this lesson, we delve into the critical intersection of AI and cybersecurity, a domain where AI is being used to fortify digital defenses, detect and respond to cyber threats, and enhance the security of our increasingly interconnected world. We will explore how AI techniques, such as machine learning, anomaly detection, and natural language processing, are being applied to various aspects of cybersecurity, including intrusion detection, malware analysis, vulnerability assessment, and threat intelligence. We will also examine the challenges and limitations of using AI in cybersecurity, such as the potential for adversarial attacks and the need for robust and reliable AI systems. Furthermore, we will discuss the ethical implications of deploying AI in security contexts and the importance of balancing security with privacy and other human values. Prepare to discover how AI is transforming the landscape of cybersecurity, offering new tools and capabilities for protecting against sophisticated cyber threats, while also raising important questions about the responsible use of AI in safeguarding our digital future. The evolving threat landscape. Why AI is essential for modern cybersecurity. The cybersecurity landscape is constantly evolving, with cyber threats becoming increasingly sophisticated, frequent, and impactful. This section will explore the changing nature of cyber threats and the challenges they pose to traditional security approaches. We will discuss why AI is becoming essential for modern cybersecurity, highlighting its ability to analyze vast amounts of data, detect subtle patterns, and adapt to new and evolving threats. We will also introduce the key areas where AI is being applied in cybersecurity. This sets the stage for understanding the critical role of AI in cybersecurity. Cyber threats are growing in sophistication and scale. Attackers are using increasingly advanced techniques, such as polymorphic malware, zero-day exploits, and social engineering, to bypass traditional security defenses. The sheer volume of attacks is also increasing, making it difficult for human analysts to keep up. Cyber threats are becoming more sophisticated and numerous. They are outpacing traditional security measures. Traditional security approaches, which often rely on signature-based detection and manual analysis, are struggling to keep pace with the evolving threat landscape. These approaches are often reactive rather than proactive and can be easily circumvented by new or modified attacks. Traditional security approaches are struggling to keep up. They are often reactive and easily evaded. AI is becoming essential for modern cybersecurity because of its ability to analyze vast amounts of data from various sources, such as network traffic, logs, and threat intelligence feeds, to identify patterns and anomalies that may indicate malicious activity. AI can detect subtle patterns that humans might miss. It can analyze data at a scale and speed that is impossible for humans. Machine learning algorithms can be trained to detect known threats and, crucially, to identify new and previously unseen attacks by learning the underlying patterns and characteristics of malicious behavior. This ability to generalize and adapt is essential for combating evolving threats. AI can detect both known and unknown threats. It can adapt to new and evolving attack methods. AI is being applied to various aspects of cybersecurity, including intrusion detection, malware analysis, vulnerability assessment, threat intelligence, and incident response. By automating and augmenting these tasks, AI can help organizations to better protect their systems and data, respond more quickly to threats, and reduce the burden on human security analysts. AI is being applied across the cybersecurity spectrum. It is enhancing various security functions. The increasing adoption of AI in cybersecurity is driven by the need for more proactive and adaptive defenses, the growing volume and complexity of cyber threats, and the shortage of skilled cybersecurity professionals. AI can help to address these challenges and improve the overall security posture of organizations. AI is becoming essential for cybersecurity. It is driven by the need for more effective and scalable defenses. Intrusion detection and prevention, identifying and blocking malicious activity. Intrusion detection systems, IDS, and intrusion prevention systems, IPS, are crucial components of an organization's security infrastructure, designed to detect and block malicious network activity. This section will explore how AI techniques, particularly machine learning and anomaly detection, are being used to enhance the capabilities of IDS/IPS. We will examine how AI can help to identify novel attacks, reduce false positives, and adapt to evolving threats. We will also discuss the challenges of deploying AI-based IDS/IPS and the importance of combining AI with other security measures. This showcases a key application of AI in cybersecurity. Traditional IDS/IPS often rely on signature-based detection, where they compare network traffic to a database of known attack signatures. While effective against known threats, this approach is limited in its ability to detect new or modified attacks. Signature-based detection is limited to known threats. It is ineffective against novel or modified attacks. AI-based IDS/IPS use machine learning algorithms to learn the normal patterns of network traffic and identify deviations from this baseline that may indicate malicious activity. These systems can detect novel attacks that do not match any known signature, providing a more proactive defense. AI can detect anomalies and unknown threats. It provides a more proactive and adaptive defense. Anomaly detection techniques, such as clustering and outlier detection, are often used in AI-based IDS/IPS. These techniques can identify unusual patterns in network traffic, such as sudden spikes in traffic volume, unusual port activity, or communication with known malicious IP addresses. Anomaly detection can identify unusual patterns. It can flag potentially malicious activity. Machine learning models, such as decision trees, support vector machines, and neural networks, can also be trained to classify network traffic as benign or malicious based on various features extracted from the traffic data. These models can learn complex patterns and relationships in the data, improving the accuracy of intrusion detection. Machine learning can classify network traffic. It can distinguish between benign and malicious activity. Deploying AI-based IDS/IPS presents several challenges. These include the need for large amounts of labeled training data, the potential for false positives and false negatives, and the computational resources required to process network traffic in real time. Addressing these challenges requires careful selection of algorithms, features, and training data. Deploying AI-based IDS/IPS requires careful planning. It involves addressing issues of data, accuracy, and performance. AI-based IDS/IPS are typically used in conjunction with other security measures, such as firewalls, antivirus software, and security information and event management (SIEM) systems. This layered approach to security provides a more comprehensive defense against cyber threats. AI enhances IDS/IPS but is part of a broader security strategy. It is most effective when combined with other security measures. Malware analysis and detection, unmasking and neutralizing malicious software. Malware, or malicious software, is a constant threat to individuals and organizations, with new and increasingly sophisticated malware variants emerging. This section will explore how AI techniques, particularly machine learning and deep learning, are being used to analyze and detect malware. We will examine how AI can help to identify new malware families, classify malware based on its behavior, and automate the process of malware analysis. We will also discuss the challenges of malware detection, such as code obfuscation and polymorphism, and the ongoing arms race between malware authors and security researchers. This highlights how AI can combat the growing threat of malware. Traditional malware detection often relies on signature-based methods, where files are scanned for known malware signatures. However, this approach is ineffective against new or modified malware that does not match any existing signature. Signature-based methods are limited to known malware. They are ineffective against new or modified variants. AI-based malware detection uses machine learning algorithms to learn the characteristics of malicious software and to identify new malware based on these characteristics. These algorithms can analyze various features of a file, such as its code structure, API calls, and behavior when executed in a sandbox environment. AI can detect new and unknown malware. It learns the characteristics of malicious software. Deep learning, particularly the use of deep neural networks, has shown promise in malware detection. These networks can learn complex patterns and relationships in malware data, enabling them to detect even heavily obfuscated or polymorphic malware. Deep learning can detect sophisticated malware. It can learn complex patterns in malware data. AI can also be used to classify malware into different families or categories based on its behavior and characteristics. This can help security analysts to understand the nature of the threat, prioritize their response, and develop more effective countermeasures. AI can classify malware into different families. It can help in understanding and responding to threats. Automated malware analysis is another important application of AI. By automating the process of analyzing malware samples, security researchers can analyze a larger number of samples more quickly and efficiently. This can help to speed up the development of signatures and other countermeasures. AI can automate malware analysis. It can accelerate the analysis process and improve efficiency. The use of AI in malware analysis and detection is an ongoing arms race between malware authors and security researchers. As security researchers develop new AI-based detection methods, malware authors develop new techniques to evade detection, such as using AI themselves to generate polymorphic or adversarial malware. It's a constant battle between attackers and defenders. AI is used on both sides of the conflict. Vulnerability assessment and management, identifying and remediating security weaknesses. Vulnerability assessment and management are crucial for maintaining the security of software systems and networks. This section will explore how AI can be used to automate and enhance the process of identifying, prioritizing, and remediating vulnerabilities. We will examine how AI can help to discover new vulnerabilities, predict the likelihood of exploitation, and recommend appropriate mitigation strategies. We will also discuss the challenges of vulnerability management and the role of AI in improving the efficiency and effectiveness of this critical security function. This demonstrates how AI can proactively improve security posture. Vulnerabilities are weaknesses in software or systems that can be exploited by attackers to gain unauthorized access or cause harm. Identifying and patching these vulnerabilities is essential for maintaining security. Vulnerability assessment involves scanning systems for known vulnerabilities. Vulnerability management is the ongoing process of identifying, prioritizing, and remediating vulnerabilities. AI can be used to automate and enhance various aspects of vulnerability management. For example, machine learning algorithms can be trained on vulnerability databases and exploit data to predict the likelihood that a particular vulnerability will be exploited. This can help organizations to prioritize their patching efforts and focus on the most critical vulnerabilities first. AI can prioritize vulnerabilities based on exploitability. It can help organizations focus their remediation efforts. AI can also assist in the discovery of new vulnerabilities. By analyzing code or binaries using techniques such as fuzzing and symbolic execution, AI systems can identify potential vulnerabilities that may have been missed by traditional static and dynamic analysis methods. AI can help discover new vulnerabilities. It can augment traditional code analysis techniques. Natural language processing, NLP, can be used to analyze vulnerability reports, security advisories, and other textual data to extract relevant information about vulnerabilities, such as their severity, affected systems, and available patches. This can help organizations to stay informed about new threats and take appropriate action. NLP can extract insights from vulnerability reports. It can help organizations stay informed about new threats. AI can also recommend appropriate mitigation strategies for identified vulnerabilities. By analyzing the characteristics of the vulnerability, the affected system, and the available patches or workarounds, AI systems can suggest the most effective and efficient way to remediate the vulnerability. AI can recommend mitigation strategies. It can help organizations respond to vulnerabilities more effectively. Despite the potential benefits, the use of AI in vulnerability management also presents challenges. Ensuring the accuracy and reliability of AI-powered vulnerability assessment tools is crucial, as false positives or false negatives can have serious consequences. The need for transparency and explainability is also important, as security teams need to understand why a particular vulnerability was flagged and how the recommended mitigation strategy was chosen. Accuracy, reliability, and explainability are crucial. They are essential for trust and effective use of AI in vulnerability management. Machine learning algorithms can be trained to identify patterns and anomalies in security data that may indicate malicious activity. Natural language processing, NLP, can be used to analyze unstructured data sources, such as threat reports and security blogs, to extract relevant information about new threats and vulnerabilities. AI can automate threat intelligence analysis. It can process and analyze large datasets to identify threats. AI can also help to correlate events from different sources and identify relationships between seemingly unrelated events. This can help to uncover complex, multi-stage attacks that might otherwise be missed. By connecting the dots between different events, AI can provide a more complete picture of the threat landscape. AI can correlate events and uncover complex attacks. It can provide a more holistic view of the threat landscape. Threat intelligence platforms that incorporate AI can provide actionable insights to security analysts, such as prioritizing alerts, recommending response actions, and providing context about the threat actors and their tactics, techniques, and procedures, TTPs. This can help analysts to respond more quickly and effectively to threats. AI-powered threat intelligence provides actionable insights. It can help analysts prioritize and respond to threats. However, the use of AI in threat intelligence also presents challenges. The effectiveness of AI models depends on the quality and relevance of the training data, and it can be difficult to obtain comprehensive and up-to-date threat data. The need for explainability and transparency is also important, as analysts need to understand why a particular threat was flagged and how the AI system arrived at its conclusions. Data quality and explainability are key challenges. They are essential for effective and trustworthy threat intelligence. The combination of AI and human expertise is crucial for effective threat intelligence. While AI can automate many of the routine tasks involved in threat analysis, human analysts are still needed to interpret the results, make decisions about how to respond, and provide strategic guidance. AI and human expertise are complementary. They work together to provide a more comprehensive and effective defense. Adversarial attacks and defenses in cybersecurity. The AI arms race. As AI becomes more widely used in cybersecurity, it is also being used by attackers to develop more sophisticated and evasive attacks. This section will explore the concept of adversarial attacks against AI systems, where attackers manipulate inputs to AI models to cause them to make incorrect predictions or classifications. We will examine different types of adversarial attacks, such as evasion attacks, poisoning attacks, and model extraction attacks, and discuss techniques for defending against these attacks. We will also discuss the broader implications of the AI arms race in cybersecurity. This highlights the dual-use nature of AI in cybersecurity. Adversarial attacks involve crafting inputs to AI models that are specifically designed to cause the model to make a mistake. For example, in the context of image recognition, an attacker might add a small amount of carefully crafted noise to an image that is imperceptible to humans but causes the AI model to misclassify the image. Adversarial attacks exploit vulnerabilities in AI models. They can cause misclassification or incorrect predictions. Evasion attacks are the most common type of adversarial attack, where an attacker tries to evade detection by modifying a malicious input to make it appear benign. For example, an attacker might modify a malware sample to make it undetectable by an AI-based malware detection system. Evasion attacks aim to bypass detection. They are a major threat to AI-based security systems. Poisoning attacks involve manipulating the training data used to train an AI model, with the goal of causing the model to make incorrect predictions or to behave in a way that benefits the attacker. For example, an attacker might inject malicious data into the training set of a spam filter to cause it to classify spam emails as legitimate. Poisoning attacks target the training data. They can compromise the integrity of the model. Model extraction attacks aim to steal or replicate an AI model by querying it and observing its outputs. This can allow an attacker to create a copy of the model and then use it to develop adversarial attacks or to bypass the original model. Model extraction attacks aim to steal the model itself. They are a threat to the intellectual property and security of AI systems. Defending against adversarial attacks is an active area of research. Techniques such as adversarial training, where the model is trained on both normal and adversarial examples, and defensive distillation, where the model is trained to be more robust to small perturbations, have shown promise in improving the resilience of AI models to these attacks. Defenses against adversarial attacks are being developed. They aim to make AI models more robust and secure. The use of AI by both attackers and defenders in cybersecurity is often described as an arms race, with each side constantly developing new techniques to try to outmaneuver the other. This highlights the dynamic and evolving nature of the cybersecurity threat landscape and the need for ongoing research and development in AI for cybersecurity. The AI arms race in cybersecurity is ongoing. It requires continuous innovation and adaptation. Ethical considerations in AI for cybersecurity. Balancing security and privacy. The use of AI in cybersecurity raises important ethical considerations, particularly concerning the balance between security and privacy. This section will explore the ethical challenges associated with deploying AI in security contexts, including the potential for increased surveillance, the risks of algorithmic bias, and the need for transparency and accountability. We will also discuss the importance of developing ethical guidelines and best practices for the use of AI in cybersecurity. This encourages a thoughtful and ethical approach to AI in cybersecurity. The use of AI for cybersecurity often involves the collection and analysis of large amounts of data, which may include sensitive personal information. This raises concerns about privacy and the potential for increased surveillance. It is crucial to ensure that AI systems used for cybersecurity are designed and implemented in a way that respects individual privacy rights. Privacy is a major concern in AI for cybersecurity. It requires careful consideration of data collection and use. Algorithmic bias is another important ethical consideration. If AI systems used for security are trained on biased data or incorporate biased assumptions, they may unfairly target certain individuals or groups, leading to discriminatory outcomes. For example, an AI system used for predictive policing might unfairly target certain neighborhoods or demographic groups based on biased historical crime data. Bias in AI can lead to unfair outcomes. It must be addressed through careful design, training, and evaluation. Transparency and accountability are also crucial in the context of AI for cybersecurity. It is important for individuals to understand how AI systems are being used to make security decisions that may affect them and to have mechanisms for challenging or appealing these decisions if necessary. Transparency and accountability are essential for trust. They are crucial for ensuring fairness and due process. The use of AI in cybersecurity also raises questions about the appropriate role of automation in security decision-making. While AI can enhance the speed and efficiency of threat detection and response, it is important to maintain human oversight and control, particularly in high-stakes situations. The appropriate balance between automation and human oversight must be considered. It depends on the specific context and the potential consequences of errors. Developing ethical guidelines and best practices for the use of AI in cybersecurity is essential for ensuring that these technologies are deployed responsibly and in a manner that respects human rights and societal values. This requires collaboration between researchers, industry practitioners, policymakers, and civil society organizations. Ethical guidelines are essential for responsible development. They should address issues such as privacy, bias, transparency, and accountability. The ethical considerations surrounding AI in cybersecurity highlight the need for a thoughtful and balanced approach to the development and deployment of these technologies. While AI offers powerful new tools for enhancing security, it is crucial to consider the potential risks and to ensure that these systems are used in a way that is consistent with our values and respects fundamental rights. A balanced approach is needed. It requires careful consideration of both the benefits and risks of AI in cybersecurity. The future of AI in cybersecurity, towards autonomous and adaptive security systems. The field of AI in cybersecurity is rapidly evolving, with ongoing research pushing the boundaries of what's possible in threat detection, prevention, and response. This section will explore some of the most promising future directions and emerging trends in AI for cybersecurity, including the development of more autonomous and adaptive security systems, the use of AI for proactive threat hunting, and the potential for AI to transform the economics of cybersecurity. We will also discuss the challenges of realizing this future vision and the need for continued research and innovation. This provides a glimpse into the future of AI in cybersecurity. One major trend is the development of more autonomous and adaptive security systems. These systems will be able to detect and respond to threats in real time, without the need for human intervention. They will also be able to learn and adapt to new threats and changing conditions, making them more resilient and effective over time. Autonomous and adaptive security systems are a key goal. They promise more proactive and resilient defenses. The use of AI for proactive threat hunting is another important direction. Instead of simply reacting to known threats, AI can be used to proactively search for indicators of compromise or malicious activity within an organization's network or systems. This can help to identify and neutralize threats before they cause significant damage. AI can enable proactive threat hunting. It can help to identify and neutralize threats earlier. The increasing use of AI by attackers is also driving the need for more advanced AI-based defenses. As attackers develop more sophisticated AI-powered attack methods, defenders will need to develop correspondingly sophisticated AI-based defenses to counter them. This ongoing arms race between attackers and defenders will shape the future of AI in cybersecurity. The arms race between attackers and defenders is a key driver. It requires continuous innovation in AI-based defenses. The potential for AI to transform the economics of cybersecurity is also significant. By automating many of the tasks currently performed by human analysts, AI can help to reduce the cost of security and make advanced security capabilities more accessible to a wider range of organizations. AI can make cybersecurity more efficient and cost-effective. It can help to address the shortage of cybersecurity professionals. However, realizing the full potential of AI in cybersecurity will also require addressing the technical, ethical, and practical challenges discussed in previous sections. It will also require ongoing investment in research and development, as well as collaboration between academia, industry, and government. Realizing the full potential of AI in cybersecurity requires ongoing effort. It is a collaborative and interdisciplinary endeavor. The future of AI in cybersecurity holds immense promise for improving our ability to defend against increasingly sophisticated cyber threats. As you continue your journey in AI, you will have the opportunity to contribute to these advancements and shape the future of this dynamic and critical field, creating intelligent systems that can protect our digital infrastructure and safeguard our increasingly connected world. The possibilities are vast. The future of AI in cybersecurity is full of potential. Lesson 19: AI in Scientific Discovery and Research, Accelerating the Pace of Scientific Breakthroughs. Welcome back, intellectually curious learners, to the 19th lesson in our advanced exploration of artificial intelligence. In this lesson, we venture into the exciting realm of AI in scientific discovery and research, where AI is becoming an increasingly indispensable tool for accelerating the pace of scientific breakthroughs and expanding the frontiers of human knowledge. We will explore how AI techniques, such as machine learning, data mining, and automated reasoning, are being used to analyze vast scientific datasets, generate hypotheses, design experiments, and even automate the process of scientific discovery itself. We will examine applications of AI across various scientific disciplines, including genomics, materials science, astronomy, and climate science. We will also discuss the challenges and limitations of using AI in science, such as the need for large, high-quality datasets, the difficulty of interpreting complex AI models, and the importance of combining AI with human expertise and intuition. Prepare to discover how AI is transforming the practice of science, offering new tools and methods for understanding the natural world and enabling discoveries that would have been impossible with traditional methods alone. The role of AI in scientific discovery, augmenting human intellect in the pursuit of knowledge. Science has always been driven by the desire to understand the world around us, and AI is now becoming a powerful tool in this pursuit. This section will explore the various ways in which AI is augmenting human intellect in scientific discovery, enabling researchers to analyze data, generate hypotheses, and make predictions at a scale and speed previously unimaginable. We will also discuss the changing nature of scientific research in the age of AI and the new opportunities for collaboration between humans and machines in the quest for scientific understanding. This sets the stage for understanding the transformative potential of AI in science. Traditionally, scientific discovery has been a slow and laborious process, involving manual data analysis, hypothesis generation, and experimental testing. AI has the potential to accelerate this process by automating many of these tasks and by enabling researchers to explore much larger and more complex datasets. AI can accelerate scientific discovery. It can automate tasks and analyze vast datasets. Machine learning algorithms can be used to analyze large scientific datasets, such as genomic data, astronomical observations, or climate simulations, to identify patterns, correlations, and anomalies that may not be apparent to human researchers. These patterns can then be used to generate new hypotheses or to guide further investigation. AI can identify patterns and generate hypotheses. It can uncover hidden relationships in scientific data. AI can also assist in the design of experiments by suggesting optimal experimental parameters, predicting the outcomes of experiments, and even autonomously controlling experimental equipment. This can help to reduce the time and cost of experimentation and to explore a wider range of experimental possibilities. AI can optimize and automate experimentation. It can accelerate the experimental process. Automated reasoning and knowledge discovery systems can help researchers to make sense of the vast and growing body of scientific literature. These systems can extract information from scientific papers, identify relationships between different concepts, and even generate new hypotheses based on existing knowledge. AI can assist in knowledge discovery. It can help researchers navigate and synthesize scientific literature. The use of AI in scientific discovery is changing the nature of scientific research. It is enabling a more data-driven and computationally intensive approach to science, where AI algorithms and human researchers work together to explore complex scientific questions. AI is changing the practice of science. It is enabling new forms of collaboration between humans and machines. The partnership between humans and AI in scientific research has the potential to greatly accelerate the pace of discovery and to lead to breakthroughs that would not have been possible with either humans or AI alone. By combining the strengths of human intuition and creativity with the power of AI to analyze data and automate tasks, we can unlock new frontiers of scientific understanding. Human-AI collaboration is key to future scientific progress. It leverages the strengths of both humans and machines. AI for data analysis and pattern recognition, extracting insights from complex scientific data. Scientific research often involves analyzing large and complex datasets to identify patterns, correlations, and underlying structures. This section will explore how AI techniques, particularly machine learning and data mining, are being used to extract insights from complex scientific data across various disciplines. We will examine how AI can help to identify hidden relationships, classify and cluster data, and make predictions based on learned patterns. We will also discuss the challenges of working with scientific data and the importance of domain expertise in guiding the application of AI. This showcases how AI can unlock the value of scientific data. Many scientific disciplines are generating vast amounts of data. Genomics, astronomy, climate science, and materials science are just a few examples of fields where researchers are grappling with massive datasets that are beyond the capacity of humans to analyze manually. AI provides tools for making sense of this data deluge. Scientific data is often complex and high-dimensional. AI can help to analyze and interpret this data. Machine learning algorithms, such as clustering, dimensionality reduction, and classification, can be used to identify patterns and structures in scientific data. For example, clustering algorithms can be used to group similar genes or proteins based on their expression patterns, while dimensionality reduction techniques can help to visualize complex datasets and identify key variables. AI can reveal hidden structures in data. It can identify patterns and relationships that are not readily apparent. Deep learning, in particular, has shown great promise in analyzing scientific data. Convolutional neural networks, CNNs, can be used to analyze images, such as those from microscopes or telescopes, while recurrent neural networks, RNNs, can be used to analyze sequential data, such as time series from sensors or simulations. Deep learning can handle complex scientific data. It can learn intricate patterns and representations. AI can also be used to make predictions based on scientific data. For example, machine learning models can be trained to predict the properties of new materials based on their chemical composition or to forecast the behavior of complex systems, such as the Earth's climate. AI can make predictions based on scientific data. It can help to guide research and inform decision-making. However, applying AI to scientific data also presents challenges. Scientific datasets can be noisy, incomplete, and heterogeneous, requiring careful preprocessing and cleaning. Furthermore, the interpretation of AI models in a scientific context requires domain expertise to ensure that the results are meaningful and not spurious. Working with scientific data requires careful preprocessing. Domain expertise is essential for guiding the analysis and interpreting the results. The combination of AI and human expertise is crucial for extracting meaningful insights from scientific data. AI can help to automate the process of data analysis and pattern recognition, but human researchers are still needed to formulate the right questions, interpret the results, and guide the overall research direction. AI and human expertise are complementary. They work together to advance scientific understanding. AI-driven experimentation and hypothesis generation, automating the scientific method. Traditionally, the scientific method has involved a cycle of observation, hypothesis generation, experimental testing, and analysis. This section will explore how AI is being used to automate and enhance various stages of this process, from generating novel hypotheses based on existing data to designing and even executing experiments autonomously. We will examine how AI can accelerate the cycle of scientific inquiry and enable the exploration of more complex and ambitious research questions. This demonstrates how AI can automate and enhance the scientific process. AI can be used to generate new scientific hypotheses by identifying patterns and relationships in data that may not be apparent to human researchers. For example, machine learning algorithms can be trained on large datasets of scientific literature to identify potential connections between different concepts or to suggest new research directions based on gaps in existing knowledge. AI can generate novel hypotheses. It can identify new research directions based on data patterns. AI can also assist in the design of experiments. By simulating the outcomes of different experimental designs, AI can help researchers to optimize their experiments and to identify the most promising experimental parameters to investigate. This can save time and resources and increase the likelihood of obtaining meaningful results. AI can optimize experimental design. It can help researchers to design more efficient and effective experiments. In some cases, AI can even be used to automate the execution of experiments. For example, robotic systems equipped with AI algorithms can perform laboratory experiments, such as mixing chemicals, growing cells, or testing materials, with minimal human intervention. This can greatly accelerate the experimental process and enable high-throughput experimentation. AI can automate experimental execution. It can enable faster and more scalable experimentation. The combination of AI-driven hypothesis generation, experimental design, and automated execution has the potential to create a closed-loop system for scientific discovery, where AI systems can autonomously propose, test, and refine scientific hypotheses. This could dramatically accelerate the pace of scientific progress. AI can create a closed-loop system for scientific discovery. It can automate the entire cycle of scientific inquiry. However, the development of such systems also raises important questions about the role of human researchers in the scientific process. While AI can automate many routine tasks, human creativity, intuition, and domain expertise are still essential for formulating important research questions, interpreting results, and guiding the overall direction of scientific inquiry. Human researchers remain essential. They provide creativity, intuition, and domain expertise. The use of AI to automate and enhance the scientific method is still in its early stages, but it holds immense promise for accelerating the pace of discovery and enabling researchers to tackle more complex and challenging scientific problems. As AI techniques continue to advance, we can expect to see even more transformative applications of AI in scientific research. AI is poised to revolutionize the scientific method. It has the potential to greatly accelerate scientific progress. AI in genomics and bioinformatics, unlocking the secrets of life. The field of genomics, which involves the study of an organism's complete set of DNA, has been revolutionized by the advent of high-throughput sequencing technologies. This section will explore how AI is being used to analyze genomic data, identify disease-related genes, and understand the complex relationships between genes, environment, and disease. We will also examine the applications of AI in bioinformatics, including protein structure prediction, sequence analysis, and the prediction of gene function. This showcases how AI is transforming our understanding of biology and genetics. Genomic data is vast, complex, and high-dimensional, making it an ideal application for AI techniques. Machine learning algorithms can be trained on large genomic datasets to identify patterns and relationships that are associated with specific diseases or traits. For example, AI can be used to identify genetic variants that increase the risk of developing cancer or Alzheimer's disease. AI can analyze genomic data at scale. It can identify disease-related genes and genetic variants. AI is also being used to understand the complex interplay between genes, environment, and disease. By integrating genomic data with other types of data, such as environmental exposures and lifestyle factors, AI models can provide a more holistic view of disease risk and progression. This can lead to more personalized and effective prevention and treatment strategies. AI can integrate diverse data types. It can provide a more comprehensive understanding of disease. In bioinformatics, AI is being used to predict the 3D structure of proteins based on their amino acid sequence. This is a fundamental problem in biology, as a protein structure determines its function. Deep learning models, such as AlphaFold, have recently achieved remarkable accuracy in protein structure prediction, potentially revolutionizing the field. AI can predict protein structure. It has made significant breakthroughs in this challenging area. AI is also used for analyzing biological sequences, such as DNA, RNA, and protein sequences. Machine learning algorithms can be trained to identify functional elements in these sequences, such as genes, regulatory regions, and binding sites. This information can be used to understand gene function, regulation, and evolution. AI can analyze biological sequences. It can identify functional elements and understand their roles. The application of AI in genomics and bioinformatics has the potential to transform our understanding of biology and medicine. By enabling the analysis of vast amounts of biological data, AI can help to identify new drug targets, develop personalized therapies, and ultimately improve human health. AI is transforming genomics and bioinformatics. It is accelerating the pace of biological discovery. AI in materials science and chemistry, designing new materials and molecules. Materials science and chemistry are fields that involve the discovery, design, and synthesis of new materials and molecules with desired properties. This section will explore how AI is being used to accelerate the discovery and design of new materials and molecules, from predicting the properties of novel compounds to optimizing chemical reactions and designing new synthetic pathways. We will examine how AI can help to navigate the vast chemical space and identify promising candidates for various applications, such as energy storage, catalysis, and drug development. This highlights how AI can accelerate materials and chemical discovery. The traditional process of materials and molecular discovery is often slow, expensive, and reliant on trial-and-error experimentation. AI offers the potential to accelerate this process by using machine learning models to predict the properties of new materials and molecules based on their structure or composition. This can help to guide the search for new materials and reduce the need for costly and time-consuming experiments. AI can accelerate materials and molecular discovery. It can predict properties and guide the search for new compounds. Machine learning models can be trained on large databases of known materials and their properties to learn the relationships between structure, composition, and properties. These models can then be used to predict the properties of new, hypothetical materials, allowing researchers to screen vast numbers of potential candidates in silico before synthesizing and testing them in the lab. AI can predict the properties of new materials. It can screen large numbers of candidates computationally. AI can also be used to optimize chemical reactions and design new synthetic pathways. By analyzing data from past experiments, machine learning models can learn to predict the yield, selectivity, and other parameters of chemical reactions under different conditions. This can help chemists to design more efficient and cost-effective synthetic routes to desired molecules. AI can optimize chemical reactions. It can improve the efficiency of chemical synthesis. Generative AI models, such as VAEs and GANs, are being used to design new molecules with specific properties. These models can learn the underlying rules of chemical structure and generate novel molecules that are likely to have the desired properties, such as drug-likeness or catalytic activity. Generative AI can design new molecules. It can explore new chemical spaces beyond traditional methods. The use of AI in materials science and chemistry is still relatively new, but it has already shown promising results in accelerating the discovery of new materials for various applications, including batteries, solar cells, and catalysts. As AI techniques continue to advance and more data becomes available, we can expect to see even more significant impacts in this field. AI is poised to transform materials science and chemistry. It has the potential to greatly accelerate the discovery and design process. AI in astronomy and astrophysics, exploring the universe with intelligent machines. Astronomy and astrophysics are fields that deal with vast amounts of data from telescopes and other instruments, making them ripe for the application of AI. This section will explore how AI is being used to analyze astronomical data, classify celestial objects, detect anomalies, and even simulate the evolution of the universe. We will examine how AI can help to process and interpret the massive datasets generated by modern telescopes and how it can assist in making new discoveries about the cosmos. This showcases how AI can enhance our understanding of the universe. Astronomical surveys, such as the Sloan Digital Sky Survey and the upcoming Large Synoptic Survey Telescope, LSST, are generating petabytes of data on stars, galaxies, and other celestial objects. AI techniques, particularly machine learning and deep learning, are being used to automatically analyze this data, classify objects, and identify interesting or unusual phenomena. AI can analyze vast astronomical datasets. It can classify objects and detect anomalies. AI can also be used to detect and characterize exoplanets, which are planets orbiting stars other than our Sun. By analyzing the light curves of stars, which show the dimming of starlight as a planet passes in front of it, AI algorithms can identify potential exoplanets and estimate their size, orbital period, and other properties. AI can detect and characterize exoplanets. It can help in the search for planets outside our solar system. Deep learning models have been used to analyze images of galaxies, classifying them based on their morphology and identifying features such as spiral arms and galactic nuclei. This can help astronomers to understand the formation and evolution of galaxies and to study the large-scale structure of the universe. AI can analyze images of galaxies. It can classify them and identify important features. AI is also being used to simulate the evolution of the universe. By training machine learning models on the results of cosmological simulations, researchers can develop faster and more efficient methods for simulating the formation of galaxies and other cosmic structures. This can help to test different cosmological models and to gain insights into the fundamental laws of physics. AI can simulate the evolution of the universe. It can help to test cosmological models and understand the laws of physics. The use of AI in astronomy and astrophysics is enabling researchers to process and interpret the vast amounts of data being generated by modern telescopes and instruments. It is also helping to automate many of the tasks involved in astronomical research, freeing up astronomers to focus on the more creative and interpretive aspects of their work. AI is transforming astronomy and astrophysics. It is enabling new discoveries and insights into the universe. AI in climate science and environmental research, understanding and addressing global challenges. Climate change and environmental degradation are among the most pressing challenges facing humanity, and AI is increasingly being used to understand these complex phenomena and to develop solutions. This section will explore how AI techniques are being applied to climate science and environmental research, from analyzing climate data and modeling the Earth's climate system to monitoring deforestation, predicting extreme weather events, and optimizing resource management. We will also discuss the limitations and ethical considerations of using AI in these contexts. This highlights how AI can contribute to addressing critical environmental challenges. Climate science involves analyzing vast amounts of data from various sources, including satellites, weather stations, and ocean buoys. AI techniques, such as machine learning and deep learning, can be used to analyze this data, identify patterns and trends, and improve the accuracy of climate models. AI can analyze climate data and improve climate models. It can help to identify patterns and trends in climate data. AI is also being used to predict extreme weather events, such as hurricanes, floods, and droughts. By analyzing historical weather data and using machine learning models to identify the precursors to these events, researchers can develop early warning systems that can help to save lives and reduce economic losses. AI can predict extreme weather events. It can enable early warning systems and disaster preparedness. Deforestation is a major contributor to climate change and biodiversity loss. AI techniques, particularly computer vision, are being used to monitor deforestation by analyzing satellite imagery and detecting changes in forest cover. This information can be used to track illegal logging, monitor conservation efforts, and inform policy decisions. AI can monitor deforestation. It can help to track changes in forest cover and combat illegal logging. AI is also being used to optimize resource management, such as water and energy use. For example, AI-powered systems can be used to optimize irrigation schedules in agriculture, reducing water consumption while maintaining crop yields. In the energy sector, AI can be used to optimize the operation of smart grids, integrating renewable energy sources and improving energy efficiency. AI can optimize resource management. It can help to reduce environmental impact and improve sustainability. Despite the potential benefits, the use of AI in climate science and environmental research also presents challenges. Climate data can be complex, noisy, and incomplete, requiring sophisticated techniques for analysis and interpretation. The ethical implications of using AI for environmental decision-making, such as the potential for bias and the need for transparency, must also be carefully considered. Working with climate data is challenging. It requires addressing issues of data quality, bias, and transparency. The application of AI to climate science and environmental research is a rapidly growing field, with the potential to significantly enhance our understanding of these complex systems and to inform more effective policies and interventions. By combining the power of AI with the expertise of climate scientists and environmental researchers, we can develop new tools and strategies for addressing some of the most pressing challenges facing our planet. AI can contribute to climate action. It can help us to understand, mitigate, and adapt to climate change. Challenges and limitations of AI in scientific discovery, data, interpretability, and the role of human expertise. While AI has the potential to transform scientific discovery and research, it also faces significant challenges and limitations. This section will explore some of the key challenges in applying AI to science, including the need for large, high-quality datasets, the difficulty of interpreting complex AI models in a scientific context, and the importance of combining AI with human expertise and intuition. We will also discuss the limitations of current AI techniques and the need for new approaches that are better suited to the unique demands of scientific inquiry. This provides a critical perspective on the challenges of using AI in science. One of the main challenges is the need for large, high-quality datasets to train AI models. In many scientific domains, obtaining such datasets can be difficult, expensive, or even impossible. Furthermore, scientific data can be complex, heterogeneous, and may contain errors or biases that need to be carefully addressed. Data availability and quality are major challenges. They are crucial for training effective AI models for science. The interpretability of AI models is another major challenge in scientific applications. While deep learning models can achieve impressive performance on various tasks, understanding how they arrive at their predictions or classifications can be difficult. This black box nature of deep learning can be problematic in science, where understanding the underlying mechanisms and causal relationships is often as important as making accurate predictions. Interpretability is crucial in science. It is essential for understanding the reasoning behind AI-driven discoveries. The need to combine AI with human expertise and intuition is also crucial in scientific discovery. While AI can automate many tasks and analyze vast datasets, human researchers are still needed to formulate the right questions, design experiments, interpret results, and develop new theories. The interplay between AI and human intelligence is key to scientific progress. AI should augment, not replace, human expertise. It requires a collaborative approach between AI and scientists. Current AI techniques also have limitations in terms of their ability to generalize to new, unseen data or to incorporate prior knowledge and physical constraints. Developing AI methods that are better suited to the unique demands of scientific research, such as the need for causal inference, uncertainty quantification, and the ability to learn from small datasets, is an active area of research. Current AI techniques have limitations in scientific contexts. They require new approaches tailored to the needs of science. Despite these challenges, the potential of AI to transform scientific discovery is immense. By addressing these challenges and developing new AI techniques that are better aligned with the goals and methods of science, we can unlock new frontiers of knowledge and accelerate the pace of scientific breakthroughs. Addressing these challenges is crucial. It will unlock the full potential of AI for scientific discovery. Ethical considerations in AI for scientific research, bias, transparency, and responsibility. The increasing use of AI in scientific research raises important ethical considerations. This section will explore the ethical challenges associated with deploying AI in scientific contexts, including the potential for bias in scientific AI systems, the need for transparency and reproducibility in AI-driven research, and the responsible use of AI in scientific decision-making. We will also discuss the broader societal implications of AI-driven scientific discovery and the importance of public engagement in shaping the future of AI in science. This encourages a thoughtful and ethical approach to AI in scientific research. Bias is a significant concern in AI for science, as it is in other domains. AI models trained on biased data can perpetuate and even amplify existing biases in scientific knowledge. For example, if a machine learning model used to analyze medical data is trained on a dataset that underrepresents certain demographic groups, it may produce results that are less accurate or even harmful for those groups. Bias in AI can perpetuate inequalities in science. It must be addressed through careful data curation, model development, and evaluation. Transparency and reproducibility are also crucial in the context of AI for scientific research. Given the complexity of many AI models, it is important that researchers provide clear and detailed information about their methods, data, and code to enable others to reproduce and validate their results. This is essential for maintaining the integrity and trustworthiness of AI-driven scientific discoveries. Transparency and reproducibility are essential for scientific integrity. They are crucial for ensuring the reliability of AI-driven research. The use of AI in scientific decision-making, such as in the allocation of research funding or the selection of research priorities, raises questions about fairness, accountability, and the appropriate role of AI in these processes. It is important to ensure that AI systems used in these contexts are fair, unbiased, and aligned with broader societal values. The use of AI in scientific decision-making must be carefully considered. It requires ethical guidelines and human oversight. The broader societal implications of AI-driven scientific discovery must also be considered. As AI accelerates the pace of scientific breakthroughs, it is important to engage in a public dialogue about the potential impacts of these discoveries, both positive and negative, and to ensure that they are used for the benefit of all humanity. Public engagement is crucial for responsible innovation. It helps to align AI-driven scientific progress with societal values. Addressing these ethical challenges requires a multidisciplinary approach, involving not only AI researchers but also ethicists, social scientists, policymakers, and the public. By working together, we can develop ethical guidelines, best practices, and regulations that promote the responsible development and use of AI in scientific research. Ethical considerations must be integrated into AI research. They require a collaborative and proactive approach. The future of AI in science, towards a new era of discovery and innovation. The intersection of AI and scientific research is a rapidly evolving field, with new techniques and applications emerging at an accelerating pace. This section will explore some of the most promising future directions and emerging trends in AI for science, including the development of more general and powerful AI systems for scientific discovery, the integration of AI with other emerging technologies, and the potential for AI to transform our understanding of the natural world and our place in it. This provides a glimpse into the future of AI in science. One major trend is the development of more general and powerful AI systems for scientific discovery. While current AI systems are often tailored to specific scientific domains or tasks, researchers are working towards developing AI systems that can be applied across a wide range of scientific disciplines and that can autonomously generate hypotheses, design experiments, and interpret results. More general and powerful AI systems for science are on the horizon. They will be able to tackle a wider range of scientific problems. The integration of AI with other emerging technologies, such as high-performance computing, quantum computing, and advanced robotics, is another important direction. This convergence will enable researchers to tackle even more complex scientific problems, such as simulating the behavior of complex systems at the molecular or even quantum level, and automating large-scale experimental facilities. The integration of AI with other technologies will be transformative. It will enable new levels of scientific inquiry. The increasing use of AI in interdisciplinary research is also likely to shape the future of science. By combining AI techniques with domain expertise from various fields, researchers can tackle complex, multifaceted problems that require insights from multiple disciplines, such as climate change, drug discovery, and personalized medicine. AI can facilitate interdisciplinary research. It can help to solve complex problems that require diverse expertise. The development of more interpretable and explainable AI systems for science is also a key priority. As AI becomes more integrated into the scientific process, it is crucial that researchers can understand how these systems work and trust their results. This will require new techniques for visualizing and interpreting complex AI models and for communicating their findings in a way that is accessible to scientists. Interpretable and explainable AI is crucial for science. It is essential for building trust and understanding in AI-driven discoveries. Finally, the ethical and societal implications of AI-driven scientific discovery will continue to be an important area of focus. As AI accelerates the pace of scientific progress, it is essential to ensure that these advances are used for the benefit of all humanity and that they are guided by ethical principles and societal values. The ethical and societal implications must be carefully considered. They require ongoing dialogue and responsible innovation. The future of AI in science holds immense promise for accelerating the pace of discovery, expanding the frontiers of human knowledge, and addressing some of the most pressing challenges facing our world. As you continue your journey in AI, you will have the opportunity to contribute to these advancements and shape the future of this dynamic and impactful field, creating intelligent systems that can help us to better understand the universe and our place in it. The possibilities are vast. The future of AI in science is full of potential. Lesson 20. Emerging Trends and Future Directions in AI, Charting the Course for the Next Generation of Intelligent Systems. Welcome back, visionary learners, to the 20th and final lesson in our advanced exploration of artificial intelligence. In this culminating lesson, we gaze into the future of AI, exploring the emerging trends and future directions that are poised to shape the next generation of intelligent systems. We will examine cutting-edge research in areas such as neurosymbolic AI, quantum machine learning, and embodied AI, and discuss the potential for these technologies to transform various industries and aspects of our lives. We will also consider the challenges and opportunities that lie ahead, including the need for more robust, generalizable, and human-centered AI, and the importance of addressing the ethical and societal implications of increasingly powerful AI systems. As we conclude this course, prepare to expand your horizons and envision the future of AI, a future that you are now prepared to help create. This lesson provides a forward-looking perspective on the rapidly evolving field of AI. Neurosymbolic AI, bridging the gap between connectionism and symbolism. Neurosymbolic AI is an emerging paradigm that seeks to combine the strengths of connectionist, neural network-based, and symbolic, logic-based, approaches to AI. This section will explore the motivations behind neurosymbolic AI, highlighting the limitations of current deep learning systems in terms of reasoning, explainability, and data efficiency, and the potential for symbolic methods to address these limitations. We will examine different approaches to integrating neural networks and symbolic reasoning, and discuss the potential applications of neurosymbolic AI in areas such as natural language understanding, computer vision, and robotics. This introduces a hybrid approach to AI. Deep learning has achieved remarkable success in various domains, but it also has limitations. Deep neural networks often require vast amounts of data to train, can be difficult to interpret, and often struggle with tasks that require explicit reasoning or the use of prior knowledge. Deep learning has limitations in terms of data efficiency, explainability, and reasoning. It excels at pattern recognition but struggles with symbolic manipulation. Symbolic AI, on the other hand, excels at logical reasoning and knowledge representation but often struggles with the complexities of real-world, noisy data. Neurosymbolic AI aims to combine the best of both worlds, leveraging the strengths of each approach to create more powerful and versatile AI systems. Symbolic AI is good at reasoning and knowledge representation. Neurosymbolic AI aims to combine the strengths of both approaches. One approach to neurosymbolic AI involves using neural networks to perform perceptual tasks, such as object recognition or speech recognition, and then using symbolic reasoning to process the output of these networks and make higher-level inferences. For example, a neurosymbolic system for visual question answering might use a neural network to identify objects in an image and then use a symbolic reasoning engine to answer questions about the relationships between those objects. Neural networks can be combined with symbolic reasoning. This allows for perceptual grounding of symbolic representations. Another approach involves using neural networks to learn symbolic representations or rules directly from data. For example, a neural network might be trained to learn a set of logical rules that describe a particular domain or to learn a symbolic program that can solve a specific task. Neural networks can learn symbolic representations. This allows for data-driven learning of symbolic knowledge. Neurosymbolic AI is still in its early stages of development, but it holds great promise for addressing some of the key limitations of current AI systems. By combining the strengths of neural networks and symbolic reasoning, neurosymbolic AI could lead to more robust, explainable, and data-efficient AI systems. Neurosymbolic AI is a promising direction for future research. It could lead to more powerful and versatile AI systems. Potential applications of neurosymbolic AI include natural language understanding, where neural networks can be used to process raw text and symbolic methods can be used to reason about the meaning of sentences and perform inference, computer vision, where neural networks can be used to identify objects and symbolic methods can be used to reason about their relationships, and robotics, where neurosymbolic systems can enable robots to learn from data while also incorporating prior knowledge. And common sense reasoning. Neurosymbolic AI has many potential applications. It can enhance various AI tasks by combining learning and reasoning. Quantum machine learning, harnessing the power of quantum computation for AI. Quantum computing is an emerging technology that leverages the principles of quantum mechanics to perform computations that are impossible for classical computers. This section will explore the intersection of quantum computing and AI, a field known as quantum machine learning. We will examine how quantum algorithms can potentially enhance machine learning tasks, such as optimization, clustering, and pattern recognition, and discuss the challenges and limitations of current quantum computing hardware. We will also explore the potential impact of quantum machine learning on various applications, such as drug discovery, materials science, and cryptography. This introduces a cutting-edge area at the intersection of AI and quantum computing. Quantum computing utilizes the principles of quantum mechanics, such as superposition and entanglement, to perform computations in a fundamentally different way than classical computers. Quantum computers use quantum bits, or qubits, which can represent both 0 and 1 simultaneously, allowing them to explore many possibilities at once. Quantum computing offers new computational capabilities. It can potentially solve certain problems much faster than classical computers. Quantum machine learning aims to leverage the power of quantum computation to enhance machine learning algorithms. For example, quantum algorithms can potentially speed up optimization tasks, such as training deep neural networks, or improve clustering and pattern recognition algorithms by exploiting the unique properties of quantum superposition and entanglement. Quantum machine learning can potentially enhance machine learning. It can speed up computations and improve algorithm performance. One area where quantum machine learning could have a significant impact is in optimization. Many machine learning algorithms rely on solving complex optimization problems, which can be computationally expensive. Quantum algorithms, such as the Quantum Approximate Optimization Algorithm, QAOA, could potentially solve these problems more efficiently than classical algorithms. Quantum optimization algorithms could accelerate machine learning. They can potentially solve optimization problems more efficiently. Quantum machine learning could also enhance unsupervised learning tasks, such as clustering and dimensionality reduction. Quantum algorithms for clustering and principal component analysis, PCA, have been proposed, which could potentially outperform their classical counterparts in certain cases. Quantum algorithms can potentially improve unsupervised learning. They can offer new approaches to clustering and dimensionality reduction. However, the field of quantum machine learning is still in its early stages. Current quantum computers are limited in size and are prone to errors, making it challenging to implement and test quantum machine learning algorithms. Furthermore, it is not yet clear whether quantum algorithms will offer a significant advantage for all types of machine learning problems. Quantum machine learning is still in its early stages. It faces significant challenges in terms of hardware and algorithm development. Despite these challenges, quantum machine learning is a rapidly growing area of research, with potential applications in various fields, such as drug discovery, materials science, and cryptography. As quantum computing hardware continues to improve and new quantum algorithms are developed, we may see significant breakthroughs in this area in the coming years. Quantum machine learning has potential long-term impact. It could revolutionize various fields that rely on machine learning. Embodied AI and robotics. Creating intelligent agents that learn and interact in the real world. Embodied AI is a paradigm that emphasizes the importance of the body and physical interaction with the environment for the development of intelligence. This section will explore the latest advancements in embodied AI and robotics, focusing on how AI techniques are being used to create robots that can learn from real-world experience, adapt to new situations, and interact with humans in natural and intuitive ways. We will also discuss the challenges of building embodied AI systems, such as the need for robust perception, real-time control, and safe human-robot interaction. This highlights the importance of physical embodiment for intelligence. Embodied AI posits that intelligence is not solely a product of abstract computation but is deeply intertwined with the body and its interactions with the physical world. This perspective suggests that intelligent behavior emerges from the dynamic interplay between an agent's brain, body, and environment. Embodied AI emphasizes the role of physical interaction. It argues that intelligence is grounded in sensory-motor experience. Robotics provides a natural platform for exploring and developing embodied AI. By building robots that can perceive their environment, make decisions, and act in the real world, researchers can study how intelligence emerges from the interaction between an agent and its environment. Robotics is a key application area for embodied AI. It provides a testbed for studying embodied intelligence. Deep reinforcement learning has emerged as a powerful technique for training robots to perform complex tasks through trial and error. By combining deep neural networks with reinforcement learning algorithms, robots can learn directly from raw sensory inputs, such as camera images and sensor readings, and can develop sophisticated control policies for tasks such as grasping, locomotion, and navigation. Deep reinforcement learning enables robots to learn from experience. It allows for end-to-end learning of complex behaviors. However, building embodied AI systems presents many challenges. Robots must be able to perceive and interpret complex, noisy sensory data in real time, make decisions under uncertainty, and control their movements and actions with precision and adaptability. They must also be able to interact safely and effectively with humans and other agents in their environment. Building embodied AI systems is challenging. It requires robust perception, real-time control, and safe human-robot interaction. Despite these challenges, embodied AI and robotics are rapidly advancing. Researchers are developing new algorithms and architectures for robot learning, perception, and control, as well as new methods for human-robot interaction. As these technologies continue to mature, we can expect to see increasingly capable and autonomous robots that can assist humans in various domains, from manufacturing and logistics to healthcare and domestic assistance. Embodied AI and robotics are rapidly advancing. They are creating new possibilities for intelligent embodied agents. The development of embodied AI also raises important ethical and societal questions. As robots become more integrated into our lives, it will be crucial to consider issues such as safety, privacy, autonomy, and the potential impact on employment and human relationships. Addressing these questions will require interdisciplinary collaboration and public dialogue. Embodied AI raises important ethical and societal questions. They require careful consideration and proactive engagement. AI and the Internet of Things. Creating intelligent and connected environments. The Internet of Things, IoT, refers to the growing network of physical objects embedded with sensors, software, and connectivity, enabling them to collect and exchange data. This section will explore the intersection of AI and the IoT, examining how AI can be used to analyze IoT data, automate decision-making, and create intelligent and connected environments. We will discuss applications of AI in smart homes, smart cities, industrial automation, and environmental monitoring, and consider the challenges of deploying AI in large-scale IoT systems. This highlights the synergy between AI and the IoT. The IoT generates vast amounts of data from a wide range of devices, such as smart appliances, wearable sensors, industrial equipment, and environmental monitors. AI techniques, particularly machine learning and deep learning, can be used to analyze this data, identify patterns, and make predictions or decisions. The combination of AI and IoT enables intelligent and connected environments. AI can unlock the value of IoT data. In smart homes, AI can be used to automate and optimize various functions, such as lighting, heating, and security, based on the occupant's preferences and behavior patterns. AI-powered personal assistants can also be integrated into smart home systems, providing a natural language interface for controlling devices and accessing information. AI can make homes more intelligent and responsive. It can enhance comfort, convenience, and energy efficiency. In smart cities, AI can be used to analyze data from various urban systems, such as traffic, public transportation, and energy grids, to optimize their performance and improve the quality of life for citizens. For example, AI-powered traffic management systems can adjust traffic signals in real time to reduce congestion and improve traffic flow. AI can make cities smarter and more sustainable. It can optimize urban systems and improve the quality of life. In industrial automation, AI can be used to monitor and control manufacturing processes, predict equipment failures, and optimize supply chains. By analyzing data from sensors on the factory floor, AI systems can identify inefficiencies, predict maintenance needs, and improve overall productivity. AI can enhance industrial automation. It can improve efficiency, quality, and safety in manufacturing. In environmental monitoring, AI can be used to analyze data from sensors that measure air and water quality, weather conditions, and wildlife populations. This information can be used to detect pollution, track endangered species, and monitor the impacts of climate change. AI can support environmental monitoring and protection. It can provide insights into environmental changes and help to mitigate risks. Deploying AI in large-scale IoT systems presents several challenges. These include the need for scalable and efficient AI algorithms that can handle the volume and velocity of IoT data, the need for robust and secure communication and data management infrastructure, and the need to address privacy concerns related to the collection and use of personal data. Deploying AI in IoT systems is challenging. It requires addressing issues of scalability, security, and privacy. Human-centered AI, designing AI systems that align with human values and needs. As AI systems become more integrated into our lives, it is increasingly important to ensure that they are designed and used in a way that aligns with human values, needs, and expectations. This section will explore the concept of human-centered AI, which emphasizes the importance of designing AI systems that are not only intelligent but also ethical, transparent, and beneficial to humans. We will discuss the principles of human-centered AI design, the challenges of incorporating human factors into AI development, and the role of interdisciplinary collaboration in creating AI systems that are both powerful and human-compatible. This emphasizes the importance of designing AI that serves human needs. Human-centered AI is an approach to AI development that places human needs, values, and well-being at the center of the design process. It recognizes that AI systems are not just technical artifacts but also social and cultural ones, and that their design and use have profound implications for individuals and society. Human-centered AI prioritizes human needs and values. It aims to create AI systems that are beneficial and aligned with human interests. One of the key principles of human-centered AI is the need for transparency and explainability. Users should be able to understand how AI systems work, how they make decisions, and what factors they are considering. This is particularly important in applications where AI systems are used to make decisions that have significant consequences for individuals, such as in healthcare, finance, and the legal system. Transparency and explainability are key principles. They are essential for building trust and ensuring accountability. Another important principle is the need to design AI systems that are fair and unbiased. As discussed in previous lessons, AI systems can inherit and amplify biases present in the data they are trained on, leading to discriminatory outcomes. Human-centered AI requires careful attention to the potential for bias and the development of techniques to mitigate it. Fairness and non-discrimination are crucial. They require proactive measures to prevent and address bias in AI systems. Human-centered AI also emphasizes the importance of designing AI systems that are aligned with human values, such as autonomy, privacy, and dignity. This involves considering the broader societal implications of AI and engaging in a public dialogue about the kind of future we want to create with these technologies. Value alignment is a key challenge. It requires careful consideration of the ethical and societal implications of AI. Incorporating human factors into AI development is challenging. It requires interdisciplinary collaboration between AI researchers, designers, social scientists, ethicists, and domain experts. It also requires developing new methods and tools for understanding human needs and values and for translating these into design requirements for AI systems. Human-centered AI requires interdisciplinary collaboration. It involves understanding and incorporating human factors into AI design. The development of human-centered AI is an ongoing process that requires continuous reflection, evaluation, and refinement. As AI systems become more integrated into our lives, it will be increasingly important to ensure that they are designed and used in a way that promotes human well-being and flourishing. Human-centered AI is an ongoing process. It requires continuous reflection and improvement. The future of AI, towards artificial general intelligence and beyond. While most current AI research focuses on narrow AI, which excels at specific tasks, the long-term aspiration of many researchers is to develop artificial general intelligence, AGI, systems that possess human-level or even superhuman general intelligence. This section will explore the concept of AGI, discussing the potential pathways to its development, the challenges involved, and the profound implications it could have for humanity. We will also consider the potential risks and benefits of AGI and discuss the importance of foresight and responsible innovation in guiding its development. This explores the long-term aspirations and challenges of AI research. AGI is often defined as an AI system that can perform any intellectual task that a human being can, including learning, reasoning, problem-solving, and interacting with the world. Some researchers also envision superintelligence, which refers to systems that surpass human intelligence in all or most domains. AGI is a long-term goal of AI research. It represents a fundamental shift from narrow AI. The development of AGI, if achievable, could have transformative consequences for humanity. It could lead to unprecedented scientific breakthroughs, economic growth, and solutions to some of the world's most pressing problems. However, it could also pose existential risks if not developed and managed responsibly. AGI has the potential for both immense benefit and risk. It requires careful consideration of its potential impacts. One potential pathway to AGI is to continue advancing the state-of-the-art in deep learning and other current AI techniques, gradually expanding their capabilities and generality. Another approach is to focus on developing more integrated AI architectures that combine different AI techniques, such as perception, reasoning, and learning, into a unified system. There are different approaches to achieving AGI. Each has its own challenges and potential. The challenges of developing AGI are immense. They include not only technical challenges, such as developing algorithms for general-purpose learning and reasoning, but also conceptual challenges, such as understanding the nature of consciousness and intelligence itself. Developing AGI requires fundamental breakthroughs. It is a problem of unprecedented complexity. The potential risks of AGI, particularly superintelligence, have been the subject of much debate and speculation. Some researchers have warned that an uncontrolled superintelligence could pose an existential threat to humanity, either through intentional malevolence or through the pursuit of goals that are misaligned with human values. The risks of AGI must be taken seriously. They require careful consideration and proactive measures. Ensuring that AGI, if developed, is beneficial to humanity requires a concerted effort from researchers, policymakers, and the public. This includes research on value alignment, AI safety, and the ethical and societal implications of AGI, as well as the development of appropriate governance structures and international cooperation. The development of beneficial AGI is a global challenge. It requires international collaboration and foresight. The future of AI holds both immense promise and significant challenges. As we continue to advance the capabilities of AI systems, it is crucial to engage in a thoughtful and informed dialogue about the kind of future we want to create with these technologies. By combining technical expertise with ethical wisdom, we can strive to ensure that AI remains a powerful tool for human flourishing. The future of AI is in our hands. We must shape it responsibly and wisely. As you conclude this advanced course on artificial intelligence, you are now equipped with a deep understanding of the state-of-the-art in AI, its transformative potential across various domains, and the ethical and societal implications that accompany its development. You are prepared to become leaders in the field, driving innovation, contributing to cutting-edge research, and shaping the future of AI in a responsible and beneficial manner. The knowledge and skills you have acquired will serve as a strong foundation for your future endeavors in the exciting and rapidly evolving world of AI. You are now prepared to lead and innovate in AI. You have a deep understanding of the field and its implications. The journey of learning in AI never truly ends. The field is constantly evolving, with new breakthroughs, challenges, and opportunities emerging at an accelerating pace. As you move forward, remember to stay curious, keep learning, and engage with the vibrant AI community. By continuing to expand your knowledge and skills, you will be well positioned to make meaningful contributions to the field and to help realize the full potential of AI for the betterment of humanity. Lifelong learning is essential in AI. The field is constantly evolving and requires continuous learning. As you embark on your future endeavors in AI, remember that you are not just technologists but also shapers of the future. The decisions you make and the systems you build will have a profound impact on individuals, organizations, and society as a whole. Approach your work with a sense of responsibility, a commitment to ethical principles, and a deep respect for the human element in all technological advancements. You are shapers of the future of AI. You have a responsibility to develop and use AI for good. The Grand Academy of Artificial Intelligence has provided you with a strong foundation in AI. But this is just the beginning. The future of AI is vast, exciting, and full of possibilities. It is now up to you to take the knowledge and skills you have gained and apply them to create a better future with AI. Embrace the challenges, seize the opportunities, and never stop learning. The future of AI is in your hands. Go forth and shape it with wisdom, creativity, and a deep commitment to human flourishing. This is just the beginning of your AI journey. The future is yours to create. Conclusion. Congratulations, Advanced AI Explorers, on completing the Advanced Course to Artificial Intelligence. Throughout this course, you have journeyed to the forefront of AI research and development, delving into the intricacies of cutting-edge techniques and grappling with the complex challenges and opportunities presented by advanced AI systems. You have expanded your knowledge far beyond the fundamentals, equipping yourselves with a sophisticated understanding of the state-of-the-art in this rapidly evolving field. In this course, we have unveiled the power of generative AI, exploring techniques like GANs, VAEs, and autoregressive models, and witnessing their ability to create new and realistic content, from images and videos to text and music. Ventured into the realm of explainable AI, XAI, developing methods for interpreting and understanding the decisions of complex AI models, and addressing the crucial need for transparency and accountability. Investigated the fascinating domain of multi-agent systems, learning how multiple AI agents can interact, coordinate, cooperate, and compete to achieve their goals. Explored the world of robotics and embodied AI, bridging the gap between intelligent agents and the physical world, and examining how AI is enabling the creation of increasingly autonomous and adaptive robots. Examine the transformative applications of AI in specialized domains, including healthcare, finance, autonomous systems, scientific discovery, and education, gaining insights into how AI is reshaping these fields. Delved into the critical issues of AI safety and robustness, learning how to build AI systems that are reliable, secure, and resilient to adversarial attacks and unexpected situations. Looked ahead to the future of AI, exploring emerging trends such as neurosymbolic AI, quantum machine learning, and human-centered AI, and envisioning the potential of AI to transform society in profound ways. Throughout this advanced course, we have emphasized not only the technical aspects of AI but also the ethical and societal implications of these powerful technologies. We have grappled with questions of bias, fairness, privacy, security, and the impact of AI on employment, autonomy, and human well-being. As you conclude this course, you are no longer just learners of AI, you are now prepared to become leaders, innovators, and responsible stewards of this transformative technology. You possess the advanced knowledge and skills to contribute to cutting-edge research, develop innovative applications, and shape the future of AI in a way that aligns with human values and promotes the common good. The journey of learning in AI is a continuous one. The field is constantly evolving, with new breakthroughs, challenges, and opportunities emerging at an accelerating pace. Stay curious, continue to explore new ideas, and engage with the vibrant AI community. Remember, the future of AI is not predetermined. It is being shaped by the choices we make today. As you move forward, I encourage you to embrace the principles of "no human left behind" AI, working to ensure that the benefits of AI are broadly shared and that these powerful technologies are developed and used in a way that enhances human flourishing and creates a more just and equitable future for all. Thank you for your dedication, your hard work, and your commitment to learning. The future of AI is in your hands. Go forth and shape it with wisdom, creativity, and a deep sense of responsibility.